Hey, 100. Hey. Hey, 100. Hey.
Hey everyone! Sorry. 5 minutes. Just start wandering in. We're gonna begin in just 5 minutes. Hello? There we go. Fantastic. Hi, everyone. Thank you so much. This is like an unheard of hour to start Protocol Labs conference. Like genuinely unheard of. I've never seen anything starting before 10. But we have so much content to get through. Thanks for coming out and listening to me. I'm the least interesting person of the day. So actually, I'm not the least interesting person. The least interesting person is me the second time. But I promise. I will do my best to make it rewarding to come out so early. So today I'm going to talk about a lot of the subject that we're here to talk about today. Compute over data is a really transformative thing. In my opinion, there are plenty of things that came before it, but and I know speakers tend to do this when they get up here and talk about new efforts, but it really feels like we are at the advent of something transformative for everyone. And one of the reasons that we're at this, here we are. One of the reasons we're here is because the growth of data is absurd. You can see here a quick look at what it looks like every second on the web. The amount of Instagram and messages, videos streamed, and so on is just going up, and going up extremely fast. There's a projection that we're going to be at 175 zettabytes by 2025. Just an obscene number. It's hard to even fathom. And I guess I just have to turn around. And you may say to yourself, well, I don't have a big data problem. And that may be true for now. But I was going through this, and I was trying to figure out and rationalize exactly what it takes to have a big data problem. And so, for example, if you wanted to generate for yourself 100 terabytes in 100 100 days, you could do it with any of these things. 100 or 1,000 nodes generating a gigabyte of logs a day, 100 VMs with 10 services each one's only generating 100 megabytes, that's not that big per day, 20,000 users times 5 videos times 5 minutes long, a fleet of 10,000 vehicles. The average vehicle today has about 70 sensors, and they're maybe generating 150 megabits a day. Or IoT devices, right? Think about how many IoT devices. That's going up just as fast, maybe faster, than that data thing. And if each one of them only generate a megabyte a day, that is that is 100 terabytes in 100 days. And it's just such a huge number. And the reason I pick 100 terabytes is the amount of time it takes to move 100 terabytes over 10 gigabit per second connection, a very fast connection with no instability, is 1 day. That means when you get to a point where you're generating 100 terabytes a day, and I promise you, you're going to record this, and in 5 years, 100 terabytes is going to sound like 640K, right? Every day, you will be generating 100 terabytes so fast that if you have any delay in processing that after moving, you're going to start falling behind. And that's why compute over data is so important. And I haven't even gotten to the cost, right? A lot of people are like, well, I'm just going to throw, about 1,000 hard drives in a cage and call it. But the truth is that that's not free either. Sure, hard drives are cheap, but then the systems, the racks, the ability to wire it together, let alone the administration and maintenance, over 5 years, that's $1.3 million. It's not cheap to be able to do that. So I would argue that compute over data isn't just recommended, it's the law. Law of physics, but law nonetheless. Now today you have a lot of options for doing things like compute over data, and they're great. I don't want to take anything away from this, but they definitely are targeted at a different use case. The use case that they're targeted at is the idea that you're going to have a central, very efficient processing cluster, and you're going to continually stream or move your data into that processing cluster in order to work it. Which is fine, but it's not where we are today when it comes to this greatly distributed set of data generation. And the truth is, I like to joke about this, but the truth is data scientists don't really want that either. They are great, but if you take the standard housing prices example, this is the hello world for data scientists. Looks like this, few lines of code to group and sort and your data. If you want to do it in Hadoop, it looks like this, in Java, right? Not Python. And this isn't even all of it, right? This isn't even all of it, right? We haven't even talked about setup. We haven't even talked about your DevOps cluster, all that kind of stuff. It's a lot, and especially a lot if you're just trying to process these very large things. And these things are everywhere, right? You go out to any hyperscale cloud, and they're going to have an entire open data registry. This is not just, whatever, Caltech or someone like that who's, maintaining these things. It's average people who want to make these decisions on this very large amount of data. So then you say, okay, well, does it have to be decentralized? It's a fair point. But if you look at the definition of decentralized, I was doing this the other day too, it's kind of funny. Organizations whose activities are not performed in one central place, but happen in many different places. I would argue that data, if you look at all those things, many machines, many devices, many users, all of them decentralized. No one lives in a data center. Well, I mean, I do, but most people do not live in a data center. So I would argue that the data is already decentralized, and all that matters is moving the compute to where the data is in order to take advantage of that. To take you through this, if you haven't gone through these kind of exercises, it's really fascinating. If you think about this in just a pure cluster format, you have all these nodes. Here I've drawn it out as 3 different clusters, each node pushing their data to a local store, which is very, very standard. And your data scientist says to that central cluster, okay, I'd like to go and run this processing job. And the data cluster says, okay, time to go. The first thing they have to do is move all that data over, run that processing job. And then finally she says, okay, finally I can start. So she begins that later when it's finally all streamed in. And then she gets the answer and she says, oh no, I've made a mistake, which happens all the time. I'd like to start over. Or excuse me, I'd like to go again. Whatever. There we go, that. And it's true, that is the case. Again, you're like, okay, well maybe I'll just stream constantly to this very expensive cluster, or maybe I'll move it. But then you're saturating your pipes, you're taking up precious space in this very expensive, very useful cluster. And that's not ideal either. She's blocking out, the next data scientist who wants to come along. So you say, well, aren't things better on hyperscale cloud? Sort of. They are, and they're, highly efficient, and they're more decentralized, but they're not where your data is. They're not in the car. They're not on the IoT device. They're not in your, home on the laptops and things like that. You're still going to need to get it in. And by the way, you're now going to pay ingress and egress costs every time you move stuff around. So that's hugely expensive too. Now the funny part is, again, you look at the costs of doing this. If you go and look at the cloud vendors and what that looks like, it's actually more expensive. I was really shocked to see that. And I think they're even understating this if you go and really do the math. The ingress egress costs of this actually get really, really expensive. Or worse, they saturate your pipes and prevent your machines from doing other things. Again, neither is ideal. Now, I talked about this just as storage here. I actually am giving them a break, because if you actually go and look at what it costs to run processing over that data, it quadruples, right? You spin up an EMR, a Hadoop cluster, or other big data cluster, and oftentimes the disk is far more expensive. Oops, there you are. Okay. So what we need to do is map to a system that how we collect and store data today. Again, we're not inventing anything new about collecting this data, generating this data. It's already out there. And all it is up to us is map the way we do this processing into this new world. The way I think about it is it comes down to 3 big vectors. The first is local to data reproducible execution. That makes sense. You want to have some code or some execution or something that you're able to push to where it is and know that you're doing it in a reproducible way. The worst thing in the world would be to continually push and realize it's not idempotent and rerun the same job over and over again. You want to be able to be smart enough to know that you've already run this processing job at the edge, not in some central orchestrated layer. Second, you really do need to think about a new incentive model, right? Again, a lot of these commercial opportunities and commercial executions are about charging for the centralized compute and the centralized storage of that data. And we're really going to need to change that, right? If I already own 1 million IoT devices, and each one of those have an x86 processor on it, it seems silly that I'd be charging you, or I'd be paying you to store the data, it's already there, or run the data. I already have a x86. Why would I charge? We need to have a new model to support that. And I want to be clear, we're not saying the existing platforms are out of date by any stretch. It's just they serve a different function. When I've done the initial processing job, filtering, transformation, whatever it might be, compression, that's when these things should take over. Not when they're just, unzipping files or, downscaling your images or whatever it might be. And the third, and is critically important and really undelivered by the marketplace today, is have it be provably secure and verifiable. How can we have a system where there's no open buckets? How can we have a system where I can actually verify at the edge, at that point of computation, that the job was executed on correctly, and go back and reproduce it if necessary? Have the code be visible, have everything be tied together with lineage and rich understanding of exactly what was executed. That's what I'm looking for when we have compute over data. So what we are building, and by we, I mean the entire compute over data community summit, and why we're here to talk about this today, looks like this. First, I need to be able to declare my execution and really a pipeline format, right? So don't think about these as single executions, but think about them as a series of executions that might occur on the edge. So we need a way to reproduce the job packaging and reproduce the pipeline packaging that we can deploy anywhere, basically to anything that can run x86, ARM, whatever it might be, the same places you can execute binaries today. Second, we need to create a way to orchestrate and decentralize that orchestration, or execution, excuse me. So you take that execution, I say, okay, this is the job. I want to run on all these myriad devices. Go out and do it. When device number 741,620 fails, I want you to watch that one. I want you to restart it. When 910,000 gives me back a non-verifiable answer, I want you to go rerun that or knock that node off the network because it's it's been compromised, so on and so forth. The system has to take care of that itself. And third, once it's done, we need to ensure consistency and we need to ensure verifiability. Taking those things that we were talking about earlier, that as you go and potentially duplicate effort, do redundant, executions to ensure you're doing it properly, the system should be able to pick that up and run it for you. So that's what I want out of a compute over data network. Now, what does that look like? So we go back to our data scientist. She said she's like one data processing job. The compute over data network, don't think of this as a central cluster. She submits it to the network. And the network says, here's the job. It's got a content addressed ID. It's in 3 chunks. Great. Take it if you can. So node 1 says, I got it. I have this chunk. I'm going to go. Node 2 says, I have that chunk too. Node 3 says, well, I have the chunk, but I'm out of CPU, so I can't do it right now. And node 4 says, well, I have CPU, but I don't have the chunk. So the two figure out how to deal with that. They move the chunk from one place to another, and then they run the processing. And then when they're done, they get it all together. They say, all right, we're done. We're ready to give it back to you. But then the network itself says, hey, you know what? That's great. I'm glad you have answers. I'm going to check to make sure that you all did it right. So I need to re-execute it if necessary. After that, the node says, here it is. Here's the verified. Here's the cryptographic proof. Off you go. And the data scientist says, awesome, I'm ready to go. And only then does she download it, and not from a single source, but in fact from those original things that worked on it. Again, signed, verified, ready to go. So while there certainly is some movement of data, we should always expect things to move around as nodes come up and down and things fall over. A resilient network will always support that. We didn't have a situation where everything needed to be aggregated and all data needed to be moved. And most importantly, we didn't have a central point of failure here. The data scientist, she was able to submit it to the network, and the network was able to take care of it from there. So, in my opinion, I think this pays off across many vectors. I think you have certainly easier to manage. As I said, the network picked up everything. There was no central authority having to deal with, downtime, API upgrades, whatever it might be. It was self-organizing. Each node said what they were going to do as part of this overall flow. It was compatible with existing tools. You want things that run, your average binary, Python, Docker containers, WASM, whatever it might be. Anything that can run on these things should be allowed to run on these things. And it's got built-in verification. In the middle, cost-effectively, it's serverless-ish. Nothing is serverless, but this is as close as you get. You have efficient bin packing. The things that have resources are able to shift between them. You're able to move jobs as necessary. Greatly reduced ingress-egress. Again, can't promise we're ever going to get it to zero. It's impossible to get it to zero because you are going to have to move the data around. But the extent to which you can target just the things you need is incredibly important about moving things around, and certainly saves time as well. And finally, reproducible and collaborative. Content addressable. Everything is content addressable. Everything is written to a place, a permanent place, on Filecoin, on IPFS, anything else you'd like. But content addressability is key. We don't want to have the network having to reproduce work that has already been done, and we want this to be valuable forever. We want the content to speak for itself. We don't want a central authority saying, oh, I have an index of all the content that's out there. I'll tell you where it is. Second, what you saw here, a network must have automated metadata and lineage. The number of times I will see people with terrible behavior around this, I get it. They need to get job done, but they'll throw something, they'll export it from a table at one point, they'll drop it as a CSV into an S3 bucket, they'll run a job on it, and they'll produce a model, and presto, you're done. Where did that CSV come from? What was the PII? When that person leaves the company, where did it, what happened there? Because this is content addressable, you get lineage for free. You get metadata for free. It's all part of it. And finally, like I said, communal funding models. Now, so you could certainly have someone take over and say, well, I'm going to pay for this all. But you could also have a collaboration of people do this. Networks like this are far more built in to support that kind of flexibility instead of having a central point that makes all the decisions for you. Now, like I said, it's we who are building it. I will never say that we are the ones who, I know what the right answer here. We already have a Computer for Data working group. We highly encourage you to come and join us. 15 current member companies. We are working on standards. We're working on all sorts of things. And again, for us, we want to establish what the standards, the norms, the expectations of data scientists and end users are going to be so that we can work on the things that make sense together, but then focus on the things that make sense for each of our particular end users. And you might say, which one is the right one-to-one? But there isn't one, right? It's up to you for your use case. You may have seen this. We're tentatively calling it Juan's triangle. He came up with this. And it's the idea that you can have these various vectors that you will measure your computer over data networks or your particular needs. How much privacy do you need? How much verifiability do you need? And how much performance do you need? And unfortunately, like anything else, you really only get to pick two if you want it like anything. But you can work along a spectrum. You can't sit dead center, don't get me wrong, but you will sacrifice some performance, you will sacrifice some privacy, you will sacrifice some verifiability. If you're in, for example, HIPAA, you may say, you know what, privacy has to be off the scale, everything else doesn't matter, and you can make that decision. But the options really do start from there. And when you think about, so those are really the infrastructure layer. When you go one level up, when you think about businesses that are being built around this, you think about other things that you might be able to tweak around your business as well. So you can think of incentives. Maybe I take a credit card. Maybe I take cryptography or cryptocurrency. Crypto means cryptography, to be clear. Cryptocurrency is a different thing. Collaborations, organizations joining together, that might be an incentive model. You can certainly think of a social good one where, again, we're not thinking of anything new here. SETI at home, folding at home, these were all collaborative things that people join together to execute compute for the good of humanity. Segmentation, you can have a breadth focused where you're just looking at that very thin top layer that trying to touch every Python developer in the world. Maybe you're depth focused. We're going to understand exactly what's required for PCI compliance, and we're going to understand that end to end and be able to deliver that as a company. Regulated industries, extending that even further. If you have to produce audits and reports that the SEC has to read, that's an entirely different vector as well. And then finally, requirements. Beyond just privacy verifiability, maybe you have a locality or a security requirement, and you could deliver that to an end user. You can certainly think of different hardware types. Every workload is not the same, obviously. If you have video processing, perhaps you have a particular accelerator that is unique in the industry, and you can deliver that. Or green. Again, I've heard many customers seeking out green. Today, it's actually quite hard. Even at the hyperscale cloud level, I have to pick a zone, but like what is in that zone and what happens. Imagine me being able to dial up and down exactly how green it is willing to be, and me targeting only workloads, only vendors who deliver that with auditability. So, you might think this is a lot to think about, and you're not wrong. It is a lot to think about. Would you like to learn a whole bunch more? I have great news for you. So this is what it looks like over the next day. Our schedule looks like this. So on the left-hand side there, and again, you can just pop up with the QR code. I know this is a bit of an eye chart, but on the left-hand side there, you have all of our talks over the course of the day. It's all gonna be in this room, and we're gonna go one at a time through all the various people. Each one of those speakers is going to talk about what they see in the world and hopefully pass on what they've learned. Everything you see there on the left is already doing compute over data in some kind. And it was like crazy to think about how many of those people there were. And we couldn't even fit them all in today, which leads me to the second day. So on the second day, you see 2 tracks. That's much more of an unconference style format. I would love over the course of today to figure out what we would like to talk about as a community. Now, I have a bunch of prompts here, and we do have some talks for some folks who are very excited to pass on their knowledge that we felt like were good, appropriate things. But the current working theory is on the left-hand side, or excuse me, right there in the middle, you have what we're calling the platform track. These are people who are building platforms for other people to build on with concepts around those kind of things. And on the right-hand column, you will see what we're calling the data track, which is people taking the compute over data and doing interesting things. And again, I can't stress enough, this was just early thinking from the compute over data working group. We would love to tweak it if there are particular things. If you would like to talk at one of these, we would like to give you the space to go there. You can throw up slides and things like that. We'll let each group decide what they'd like to be. Now, I want to be very, very clear. It is not here. Do not come back here. I will not be here. Maybe you do want to come back here because I won't be here. But regardless, it will be at the Hyatt Regency. Everyone? Hyatt Regency, not Time Out Market. Just want to be incredibly clear. Okay. And with that, that's me. I have just a couple minutes for questions, or we can go right into more important talks. Anyone have any thoughts? It's very bright up here. I can't see anyone. Yes? Can you please go back to that slide that had the 3 columns with the numbers and the pricing? Yeah. Yeah. No worries. Everything's going to be recorded. Everything's going to be online. Sorry, he just wanted to take a picture of this to badmouth, I don't know, hyperscale cloud. He didn't. He just wanted to take a picture of it. Yeah. Sorry? Oh, yeah. I can repeat until we go. Yeah, go ahead. Oh, sorry.
Hi, I'm Greg. I'm with Picnic. I'm a mechanical engineer, and so bear with me on this.
No worries.
Right? So you had a slide that kind of outlined like 3 value props for this. And usually, right, you don't get better, faster, and cheaper. Yeah. So which one do we not get now, and when might it come?
Well, I'm happy to answer that. Which one? Because I did a couple.
Yeah, it was later than that. Keep going. Sorry.
Juan's triangle? Yes. This thing is.
You had like.
I know. It's just not very responsive. I can't jump that forward.
Okay. Oh, there it is.
This one?
That one.
This one or this one?
No.
Okay.
It was yeah.
Yes. Got it.
Yeah, essentially, right, you have easier, so faster, yeah.
So you're right. You don't get all three. To deliver, well, I will take that back. On this one, I think this is the price of entry. I do not think you will be a successful computer over data network if you don't deliver against all three of these. If you are not easier to manage than existing computer over data solutions today, you're dead. If you are not more cost effective, why would they ever change? Unless it was dramatically easier to manage. And if it's not reproducible and collaborative, it will be I don't know, it's like doing computation and having no idea what the answer is. Like there's just no way this is the price of entry. In my opinion. I don't know, happy to be wrong. Anyone else? Anyone other questions? Okay, with that, we are going to hand it off to our first speaker, who is Brooklyn from Fission. Brooklyn, are you out there? Fission. Thank you. The clicker, I don't know. Oh, sorry.
Okay, I'll just use the... Okay. Whoop. Mm-hmm. Excellent. Great. All right. Hi, everyone. Thanks for coming out today. I'm going to be talking about decentralized authorization, plumbing, and permissionless operation. One of my all-time favorite quotes about distributed systems is that the limitation of local knowledge, the fact that data and information in general lives in a particular place and can only move at the speed of light, is the fundamental challenge that we have to contend with, and increasingly in the industry sort of in general. My name is Brooklyn Zelenka. You can find me anywhere on the internet as Xpeed. I'm the co-founder and CTO at a company called Fission, where we're working on tools and protocols for Edge and Web3 apps. And I work on a whole suite of things. I wish that we had more today to say about the interplanetary VM, which is essentially a AWS Lambda competitor that we're starting to work on. Also, private data with web native file system and dialog, so file system, database, and UCAN, which I'm here to talk about today. And I'm the editor of the UCAN spec. It's being used by a bunch of companies, but I guess that means that I'm, despite not being the only one designing this thing, I might know a thing or two about it. So in Web3, broadly, we're now talking about doing nothing less than connecting all of the world's users and services in an open, interoperable way, which is something that we haven't seen since HTTP, right? TCP/IP, HTTP are pretty much it. And then we've waited now 30 years to get any more innovation on things that are open, interoperable, and everywhere, right? For all this stuff to work, just like David was just saying, this all has to be substantially better than Web 2, right? It can't be just decentralized. We have to actually make it work for real workloads, for real people today, faster, ideally cheaper. We want to get that whole triangle done, right? So how do we power a new internet? The internet, as I just mentioned, is about 30 years old and really comes from an era where your cell phone had a telescoping antenna that you had to pull out, right? Where all of your compute happened on a beige box under your desk that didn't have the power to run anything, and that you always had to talk to essentially a mainframe, right, to get results back. That's no longer the case. But we still have to now contend with the fact that there's locality, and especially data locality. So as we know, obviously from physics, you're stuck in a light cone, right? And even if we send messages or data between things, that can only move so fast and only over such a certain size of pipe, right? So even if I send messages in multiple places in giant scare quotes, the same time, they still may arrive in different order and can only move so fast. Once you have enough gravity of data, they literally can't move it fast enough around because of physics. This isn't something that we can solve with fancier computer science. So we're here because we want to do compute over data. So in order to do any kind of compute, you obviously need data. And to do data in production, you have to have some kind of auth. So talking about auth today, it's a little strange in some ways to talk about auth in a compute setting. But in order to do any of this stuff, you have to have auth. Typical picture today looks something like this. You have a developer. They want to interact with some services. Maybe some of these have access to data and the others don't. And they'll connect to one of these. And then maybe these are all networked together so that they can get access to that data, right? And so each of the services have to have individual agreements with each other. And the developer has to pre-negotiate some tokens with all of these. But this isn't what we want, right? This is just how it happens to work. And with things like content addressing, we can liberate this picture from needing access in a particular place, right? We've made it now universal location. And with capability models, like what we're going to talk about today with UCAN, we don't need pre-negotiation either. So we can just move and freely move around both the compute and the data around a network. Historically, people have used things like OAuth to solve this problem, which this is a typical OAuth flow. It has four agents in here from the user, the authorization server, et cetera. And I'm trying to remember, it's like maybe 10 or 12 steps just to get through here. And this fundamentally places things in a certain location, right? You have to have an authorization server that says, here's the list of who's allowed to do what, right? By comparison, if we use capabilities, we can make this picture much, much smaller. And this is actually being generous to OAuth, right? It could actually be just 2 of these arrows and nothing else. And in an ideal world, auth should be just boring, right? So this is using capabilities, but it looks just like a regular, sort of like a Google login style. Yep, I want to give access to these, bits of data or this, compute resource, and are you sure you want to do that? Yep, and then you can jump right into the application. So I've said this word UCAN a few times. What exactly is it? UCAN is a user-controlled authorization network. If you're familiar with DIDs and public keys say who you are, and UCANs say what you can do. This is the distinction between authorization and authentication. They look like this. The default encoding is just a JWT. So it moves around as a base 64 string that decodes to just some JSON. It is a different auth model than what most people are familiar with. ACLs have been around since at least the 70s, and it's just a list that says who's allowed to do what, as opposed to capabilities, which act a little bit more like a ticket. So we'll look at that in a little bit more detail. So here's some user, and they want to access some service. And they send a request that gets stopped by another process, that's essentially the bouncer, right, or some guard, who checks their list. And then maybe, if that user is on the list, will be allowed in. And this is, on one hand, nice, because it's broken up into these separate segments. But both it puts these two, the ones that are actually interacting, not in control. It puts this process in control, which means that you need to have this list in one place. And so you're stuck now with auth locality. You always have to go, and you're always contending with the speed of light to get this to move around. Further, if you can gain control of this deputy, sometimes it's called, you can do whatever you want, right? You have a system admin go bad and do whatever they like. And that's because they're the fundamental ones that are essentially the super admin for the system, not the service, not the user. Sometimes capabilities, by contrast, are kind of like tickets to go see a movie. When you go to see a show, you just know where it is, you're given a ticket, and they don't know who you are, you just hand it to them on your way in, right? So it's just this admit one. These are in control. You can carry the ticket with you as you're walking around to do your various things. If you can't make the show tonight, that's fine. You can hand it off to somebody else and say, you know what, go see the movie instead. Where the metaphor breaks down a little bit is you can make copies of these if you need to, and you can delegate sub-rights inside of it to someone else, which would, in the movie scenario, I guess, be, if you had, say, a movie festival pass, you could delegate, you can go on Tuesday, but not the whole thing. If you come from a blockchain background, these are a little bit like state channels, but for auth. And they can do some things for composition that ACLs don't. So rights amplification is the composition of your authority across multiple systems. The metaphor that's always used for this is if you have a can of soup, you can't do much with it, and if you have a can opener, you can't do much with it, but if you bring them together, you can have a delicious soup. So if you have auth to read some private data and to do a computation on completely different systems, you can compose those now without having to pre-negotiate both systems. You can just say, hey, here's a certificate that says go read from over there, take this thing and run it, and that's it. To get right down to brass tacks, this is how an actual certificate looks. It has a header, just like a regular JWT. It has this payload, and then a signature. And the signature has to match the issuer, which is contained in the payload, so that you can prove that this is who it came from. It has a description of what you're interacting with, or what you're granting permission over, and what you can do with it. And that's openly extensible. There's nothing in the system that says these are the things you can do. You can define completely your own, as long as the other service understands what that means. And this is just, a noun and a verb. That's all. And they're fully extensible, right? You can add sort of whatever other data you need as well. So in this case, we're saying you can only send emails to people at a Fission Code's email address. This is also, whoops, that's right. This is also all the information you need for invocation. So you don't actually need a separate system now to say, and please run this, right? It's, hey, do this thing, please run this WASM over this data. And it can be both the auth and the invocation call. So you can do distributed RPC as well in the same model. You probably don't want to invent your own whole set of resources and abilities. So there's a standard library for a bunch of the really common ones like mail servers, file systems, et cetera, and sort of your CRUD actions and so on. And you can take those and make them even more powerful by saying, okay, I have a read capability out of the standard library, but I'm a photo application and I want to narrow that down further to publishing into an album. You can just define that, and anybody else that you're collaborating with just needs to understand what album publish means, and that it is backed by this read action, and everything works. The way delegation works in the system is you have a chain of who originated the resource all the way down to who's consuming it, as long as the resources and actions get narrower as you go down, right? So if I have the ability to write into an entire file system, maybe I can give somebody else access to write just into the documents folder. So By creating a resource, I have full access over it. I'm the admin. I can then point to, hey, this is from me to somebody else with some subset of my rights, and then they can do the same thing. Hey, here's to somebody else and a subset of those rights, and so on. And because we can follow this chain backwards from this last invoked one, they contain all of their parents, or at least references to all of their parents, there's content addressed. We can verify this anywhere. It doesn't have to be at a particular place. I can just walk around with it. This works offline. This even works in the browser. So with things like WebAssembly and offline compute, you don't necessarily need to go to an external system. We can keep stuff completely off the network in a lot of cases and not have to deal with that 200 millisecond round trip time. So all of the browsers now have Web Crypto API, which means you can have non-extractable keys. Public-private key pair, where the private key isn't viewable to anyone. It's completely managed by the system, never leaves the system, doesn't move around. And we can link between them now in a perfectly secure cryptographic way that still preserves user agency, data locality, and reduces the amount of stuff that we have to put on the network. If I'm going to run a query over a database, we have content addressing. I can pull down the subset of the database I care about, run queries over it, make some updates, and then atomically push the diff, for example. So plugging things together, plugging together services, plugging together applications. Perlis said every program has at least two purposes, the one that it was designed for and the one that it wasn't. And we want to enable all the things where people didn't expect to plug things together. So here's a user who's signing in with MetaMask and an Ethereum account. And they have a bunch of these, these emoji are representing different resources and actions that they can do. And she wants to collaborate with this other person and says, you know what, you can manage everything for me directly in Chrome. And he says, I actually also need to use this on my iPhone, but sometimes I leave it out, so I'm only going to do some subset of things on that. So delegates between devices. So this isn't per person now, this is per software agent. And can delegate that on further to somebody else working in Brave. But it doesn't have to go in this direct chain, right? You can delegate as many times as you like. So here on Polygon, right, a completely different set of capabilities as is across the top. And a WebAssembly function in the cloud. And finally, somebody working in Firefox can take these two, farther down the chain and bring them together and now have access to both. These aren't limited to a single application, right? Maybe there's Twitter at the top, and a spreadsheet application on the bottom left, and some science app on the bottom right. The certificate doesn't care. And we can plug these systems together now without having to worry about, what is Twitter's token format? Or, Twitter hasn't adopted UCAN yet, but in this glorious future, we don't have to worry about what their specific API looks like, what their specific token format is. We can just attach all these things together like Lego with zero coordination ahead of time. People usually ask about this time like, well, okay, that's great. You have all this stuff moving around the system. How do I revoke things? And the good news is we have content addressing. So as long as you're earlier in the chain, you can sign a revocation and gossip that through the network to say, hey, you shouldn't trust this specific one and anything downstream from there. So if this guy on the Chrome browser revokes this Brave browser user, but not the one in the middle, the downstream consumer of that also can't use it. So let's look at a non-trivial example. This is a relatively complex UCAN, right? Lots of random-looking letters and numbers. And I won't go through like every layer of it, but just to give you a flavor. Here is that same token format that we looked at a little bit ago. And it has two proofs in it. And these are just other base64 encoded UCANs. This is actually, I'm inlining it here because these are actually CID pointers to them, but this is actually what's happening under the hood. And then we can take one of those, so this purple one, and unwrap it and look inside and say, okay, great. On this previous one, I have the ability to append into a photos directory and into a notes directory. And one of my proofs gave me the ability to append into photos. So I'm always narrowing down or at the same level as my proofs. People started building a bunch of tooling around this stuff as well to help explore all of these proofs and the proof chain and what is this UCAN actually able to do, and is the signature valid, and all of this stuff. It's a little application at ucan.xyz, and basically you can just paste one in and it'll decompose it for you and say here's all the moving parts basically. And then to explore all of the proofs in the delegation chain, you can click through along the bottom, this one has 3 proofs, I want to see proof 1 or proof 3, and you can drill down into the chain. So, it's still extremely, extremely early days for Web3. We're just figuring this stuff out, right? I would say that we're about here, right? We're not even at the classic chasm, we're at the smaller chasm. But it's growing fast. And if we're going to compete with Amazon and Google and Azure, we need to find ways of plugging our stuff together. We don't even register in scale, right, against them yet. We want to find ways to leverage everybody in this room, all those smart brains in here, right, and everybody's projects and efforts to not need to reinvent the wheel every time and have a winner-takes-all mentality, right? We have content addressing, we can move things around, we can push compute to particular places. At the end of the day, in Web 2, service composition is too hard for devs. DApp UX, and I would argue that a concept of DApp doesn't even exist. You have applications that users use, right? DApp UX is too hard for people. And no one today is in control of either their data or their compute. And we want to put that directly in users' hands or the service provider's hands directly without having to always go through one of these giant systems. We're building on top of standard, well-understood technologies to be a Trojan horse and get it in basically everywhere. One of the teams building a tool for thought on top of UCAN said that they really love this, that you can encode it as a JWT because it works with all of their existing tools, right? It plugs right into their Rust server as a bearer token in the header, and it decodes it for them. Yes, they then have to plug it into a UCAN library to actually understand what's happening inside of it, but the actual ingestion pipeline just works straight out of the box. They're in a sort of a Web 2.5, but there's nothing saying that you couldn't do this in a pure Web 2 space, and we want to connect Web 2 and Web 3. I'd recommend in general for everyone here, also echoing a bunch of the things that David mentioned earlier, we need to play nice with others, plug into existing systems, bridge into existing standards, and make it easier, more secure, and more open than existing systems, than OAuth, X509, SAML, MetaMask, Wallet Connect, all of these things. Further resources. We have a bunch of sub-projects. If you do an implementation, we will commission a logo for you. We do a lot of work on specs and improvement proposals. We have implementations in TypeScript, Rust, Go, Haskell, and there's private ones that are not, unfortunately, in the repo, but are being used by people in Elixir and, I believe, Python. There's an IPLD implementation from the good folks at Daghouse, which is powering big chunks of their system internally, to the point that their services in their service mesh don't know that they're running as part of a trusted execution environment or something. They just communicate with UCAN and read certificates and say, okay, great. And if later they decide that they need to collaborate with a mail provider or some sort of heavier compute, they can just do that. Their system doesn't need to understand anything special. We've also extended this to things like establishing mutual TLS channels. So if you want to collaborate with a bunch of other people that have access to the same kind of data, they can prove to each other, hey, look, I have this certificate. I'm not going to delegate it to anybody, but I have this certificate right now. I can sign a challenge with it. Let me into the, give me a key so I can communicate on this channel. We do instant messaging, all of that stuff. Coming up next, we're getting to a v1.0. So we've been at this for about 2.5 years now. On the last community call, we run monthly calls. A few people said, hey, it'd be really good to get this to a 1.0 so we know this is like the long-term supported version. We're plugging into sign-in with Ethereum. WhoCan is a proposed replacement for IPNS that's based on top of UCAN, so a DHT for naming. Invocation, so actually agreeing and aligning on a UCAN invocation spec that gives both the authority to run something as well as to say, hey, please run this specific action for me, which is largely being driven by the DAG house use case, though we also have uses for this inside of Fission and IPVM and a bunch of others. We're doing state channels with these, so you can do payment directly in a UCAN, and cosigners, so you can do multi-factor authentication, things like that. I've already actually talked about the invocation, so UCAN as RPC. The vision there is that this could essentially replace a gRPC-like interface and have it come along with the auth as well. Because this is going to be on video, and people often ask for resources, here's a set of links. Thank you. And do we have time for questions, or? Yeah? Okay. Yes.
Oh.
Oh, sure.
So, made a note here. So when you were talking about revocation,
yeah.
It seemed to me like it was revocation can be done after the fact, but can you do revocation before the fact? In the sense that I don't want this particular entity to access any of this before that. Also things like limits on the number of invocations or not allowing delegation, basically negating stuff before the fact. How do you do that?
Yeah, so limiting number of invocations, or you're not allowed to delegate further past this depth, things like that. All of that requires some central place that you're going to check that list. We've tried with various, getting clever with hash preimages, all of this stuff. At the end of the day, there's always some way to get around it. So that has to be handled at a place. And so you can actually plug this into systems like CapTP that say, okay, this is the resource that you're going to access is essentially a proxy that will then forward messages on. And so you can do all of your offline delegation and then pass it off to this central service, and then it can keep moving, basically. So that does force you into location and locality again. So it's not the general case. You can do it. And especially enterprise use cases are often interested in that.
I have a question as well. It's
yes.
somewhat in the same direction, but
yeah.
It's pretty common to have a situation where you may have a substantial amount of data that if all of it were present at once would be able to yield quite a bit of information about you. So you may delegate only portions of it, but given the system allows recombination of data later, how do you prevent this from happening?
Right.
Like if you specifically shard things out so that this doesn't happen, other people can just be like, oh wait, there's all these pieces, I'll just put them back together, right? How do you avoid this?
Yeah, totally. So the core, like UCAN itself won't unless you use a system like this where you're pushing things through some coordinator, right? That says like, yep, sure, yeah, you can get this, you can't, and tracking, actually IDs. There's two layers when we talk about private data. There's encryption, so you can do encryption at rest, especially in content at rest data. And I would strongly, strongly recommend that because data can now move around the system. And not just while it's in transit, right? Like when it's actually being stored in multiple locations, you don't necessarily trust everyone that's storing that, right? And then retrieval is the other layer, right? So we have access control at the network layer and at the data storage layer, both. If you, it's sometimes easier to think about this in terms of the keys. If I give you a key to one directory and a key to another directory, obviously you can get into both of them, right? So part of the idea here is, depending on how open your system is, if you're allowing any entity into the system, then there's no way around this, right? You're kind of stuck. If you have some blessed group of DIDs that are allowed to actually access things, you can push them through a CAP-TP system. It's sort of the short version of this. So, yeah. Great.
Yeah, I got a question here. How do you manage in open permissionless systems? Right here.
Yeah. Okay.
Off-chain systems that the verifier is actually not malicious.
That the verifier isn't malicious.
Yeah.
The verifier is the one that's doing the
backchain trace of the permissioning.
So they're the ones that are actually executing things. So it's in their best interest to not, like, they can only hurt themselves, really, right? The verifier isn't external to the system. You're handing it directly to the service to say, hey, check this chain, which is signed cryptographically, and only execute it then. If there's a bug in your code, then yeah, it could do something wrong, potentially.
So the entire system is fully object-oriented. Is that in the sense that the verification is part of every service implementation?
Yes.
Access, okay, gotcha.
Yeah.
One more question about, I think you called it the verb. I'm not sure. It was the way that you describe sort of these actions. You mentioned kind of in passing that people have to agree on this. How do you cause that agreement to happen?
So there's a standard library for most things, right? It's openly extensible. So in any standard, the spec describes the minimum number of things that we can all agree on that every implementation will understand. And if you invent some completely random other thing, you're narrowing who you can interact with, and it has to only be with them. So, yeah.
Okay, and with
Great.
that, we are out of time. Thank you so much, Brooklyn.
What should the pod wear? I have HDMI as well. But you can do like HDMI, not HDMI. Hello, can you hear me? Can you see me? That's nice. My name is Dmitry. I'm from Fluence Labs. I'm CTO and co-founder of Fluence Labs. And I want just to share some raw thoughts about computer data networks, discovery and composability, and how Fluence can help. What's our approach on this topic? So I decided to go straight from the fundamentals. I will speak about data, computer data, network, what does it mean to have a computer data network and why do we need many, what does it mean discoverability, composability, what does it mean computer data networks, discovery and composability, and finally when we have some understanding of the problem, I will tell what we at Fluence do to help with this problem. So first of all, data and compute. Data is things known or assumed as facts, making the basis of reasoning or calculation. And to compute, from my opinion, it means to shuffle data in a certain way for a purpose. So data is usually needed in a different form that it appears. It appears in some raw form, but it's needed in another. And what does mean another form? It means aggregated, reshaped, analyzed, filtered, augmented, indexed, searched, and so on. So we need data in many shapes and forms. And compute actually accompanies data all the way, and the same holds for data. So if we want to capture the fact, it actually means that we can yield this fact without providing something before it. It means that we have some way represented as an arrow here to get some data as letter A. If we transform data, it means that we provide data, we have arrow, some compute to have another data. If we have an intermediary state that is held between different invocations of compute, then we have this kind of arrow, like state monad, that we have some internal state and input and provide the new kind of the state and output. And this state change, it may help with augmenting data, it may mean storing data and providing nothing as the result, and so on. And finally, to finalize the life cycle of the data, we need to consume it, for example, to show it, and we have some kind of sinks for the data. And it means that you provide the data as an argument, and you have nothing inside the system out of it, but you have some effect, for example, something shown on the display. So there's no way to compute without data. Compute without data makes no sense, absolutely no sense. You cannot see anything. If compute without data makes sense, it means that there is data involved actually. It was consumed or exported or something happened. And data without compute is the lost fact. It happened, but it even isn't stored, so it's just lost. So some more arrows and letters. We have some predefined compute, and providing the data and getting CID is also a compute job. And it's not always trivial to compute CID, and it's not always easy to understand that this file represents this CID and not something else. And sometimes we offload this compute, even this compute from the client to the server, for example, if we stream data, or if the data is too big and we just upload it, and then we get back CID. We have this arrow inversed, and that's not quite compute. If we get from CID to data, it means much more than compute, because we need to discover it. And a lot more things involved here. And we can think about the user-defined compute, which is an arrow without data yet, but ready to get it. And luckily, we can represent it as data as well, like WebAssembly binary or Docker, or like any code finally is data. So compute over data, by definition, from my point of view, implies that you can get an arrow C and place it where the data is, so that finally you compute over data. And place it where the data is means either to move compute closer to the data or to get data closer to compute. And both cases make sense, and I'm not sure that we can limit all the use cases just to one, like batch processing, or to another, like runtime, real-time processing. Both cases make sense, and fundamentally, it makes sense because it's just more efficient. The closer the compute to data, probably the more efficient the computation is. And it brings more privacy, more security, and overall it's fine. Then a few words about the network. It's a concept which is orthogonal to compute and data. And I wish we could just skip it. If we could not think about the network, things would be much, much, much easier. But in the real world, physical world, there is such big latency and bandwidth distinction of physical resources that we are forced to treat these resources as somewhat independent peers. So we just have to, it's physics. But if these resources have something important in common, if they share some attribute, then we can organize a network out of them. So this network is identified by this attribute basically. For example, if we know that some peers are storing a data set, or we want to put this role on these peers, like say, these peers, please do store it. We want to identify it as a kind of a network so that they can help each other, or maybe they can help us to work with this data. Or if we have some special peers with specific compute capabilities, GPU access peer is very different to laptop, for example. And maybe we want to organize them in networks as well. Or particular things served for a particular user. For example, if I made some kind of a deal with some service provider, then these peers, despite the fact that there are better peers for like physical resources, but these peers are ready to serve me because I have financial relationships with them, for example. So all of this matters and means that we have a lot of networks. We have place to have a lot of networks, which kind of could be very big as protocols, but they also could be very small. For example, all the providers of a particular file for a given CID on the IPFS network, effectively, they also form a kind of a network by this attribute. And basically, network means shared connectivity and or agreements over data within a set of peers. So either you can find the root over the network, and that means that it is a network. For example, if you can get a peer-by-peer ID by Ktemlia, it's mainly about shared connectivity. Or we have some agreement over data, like consensus. All the different kinds of consensuses, including eventual, weak consensus, like strong consensus, any type. It's about agreement over data that all the peers will probably share or be capable to yield some particular data that like conforms to some invariants. Now let's speak about compute over data networks, also with arrows and ladders. If we think about IPFS as a network as a whole, then every IPFS deployment constitutes a compute over data network. And compute here at least is getting CID or getting from CID to files. And the notation could be something like we can yield a function from CID to maybe data. If it exists, if we can find it, maybe data. We can think about every IPFS node as a single peer cache network or any subset of these nodes as a cache network, so that we provide a peer ID and have this function that works with a very different like latency because we look up locally and use IPFS as a hot hash instead of using the network for content discovery. It's very different. For compute, we should have many compute over data networks for different geography. For example, if we wanted them locally, or for types of compute, or for different ways to compose this compute. But fundamentally, it means that somehow we can have an access to the peers that can take our compute in some form of abstract arrow, like WebAssembly, for example, or Docker, or whatever, And after that, we will have an ability to execute these computations on data. So the notation becomes longer and longer. And also we can think that a single device, even one device, or like a small set of user devices that belongs to one user, for example, they also constitute a single device computer data network that, for example, provides the way to capture facts from, I don't know, measurements or click streams or something like that. So we can think about all these kinds of devices and workloads as different kinds of computer data networks. Then comes discovery. So discovery means that we need to yield some capabilities out of thin air. So previously we had this, from nothing we get some capability, and that's discovery. And we have a lot of different domains that we want to discover for and in. For example, for different types of data sources, we want to discover data sources, be it devices, access to the chain, access to sensors, to external events, to randomness. It's different data sources, but we need to find the way to get this data. Or for a type of data store, cold storage, like Filecoin, hot storage, blockchain as a storage, whatever. Or a particular data set, we need to find this particular data set. Or a kind of compute capacity, we need GPU, we need whatever, we need ZK kind of compute so that we need certain proofs. Does this compute fit for a certain data that we want to provide? Is it possible to connect data source to compute capacity? Do we need to prepare the data before we do compute? And for efficiency of everything above, we need to employ very different discovery algorithms. So there must be some solution on top of that to think about all these problems in some layer that just simplifies them, or at least lets us speak about it, like to have the common language to speak about all these problems while they seem different. And in Web 2 we have solution. So when we just do Web 2, we have a lot of easy ways. The most easy ways is to point on the local capabilities, like local host, file system, local CPU, or something that you have in the web browser. Just call function in JavaScript or write a variable. That's the access to data and to compute. Very simple. Or for the remote capabilities, usually just have a REST endpoint, something XYZ, like some host in Fura, I don't know. That gets to DNS for discovery, and we have this discovery layer hidden in a fundamentally centralized way, but if we get to the endpoint that fulfills our needs, we're just happy. So absolutely good. Web 2 is very optimized for that. And we may discover computer data networks the same way with the gateways. And many people are happy doing just in Fura or something like that. So let's switch to composability. What to compose and why. What we want is to utilize the same network or sub-network, it could be a small network, or the same compute capabilities or the same data wherever they are as building blocks for something more complex to deliver the value to the end user. One example is data processing pipelines. So you have some device, something that produces the facts that we want to capture and analyze. It could be really a device like the phone, but it could be the chain, the access to chain. It could be the source of time, of randomness, other triggers. Then we have the edge, like relaying node in libp2p, for example, or the closest cache, or we could like do some filtering, pre-processing, and it means that we want to do it very close to the device just for optimization, because we might get an insight very fast, or we can filter out unnecessary data very fast, or we can do a small aggregate and prevent the further processing until we collected some data. So it's efficient. After that, we could have some real-time processing close to the edge. Probably we want to have the same region. We want to have good latency to get some real-time insights, or to store some data in the read models, to have some databases for like application level. And finally, we store it into probably Filecoin to the cloud. We accumulate a lot of data. We batch process it because we have a lot of data available, and this is a very different domain. So the question is, if you want this, how to express this pipeline? What is the way to speak this pipeline, to approach this pipeline? How to code it? Especially given that we have a lot of discovery processes here and different protocols, because probably edge nodes is a sub-network that is capable for doing one thing, while cloud is a very different set of peers and different hardware, different capabilities, different connectivity, different latency. So, and where should this data pipeline be expressed? Given that, for example, we have just these 4 levels. Who owns this pipeline from one level to another? Who writes this code? Who deploys it? And where to deploy it? Is there any place to deploy it? Who, on the way, we have the user data, probably. We get some insights, we make some decisions, we should transfer some permissions. So a lot of questions about security that were like ignored or exploited in Web2 world, but we want to do better. So for computer data networks, discovery and composability, if we take all the words together. So what we want is to utilize many networks with different kinds of resources and attributes. We want to point to these resources and have the single flow of processing. We want to take resources by geography latency, by different ways to establish security, something ZK, some consensus, some trust, different kind of access to data. It could be real-time, hold, cold chain, whatever. We have different compute capabilities, and we want to point on them. We have a very limited amount of peers actually connected to the end user, to the device, and that's the question, is it connected or not? Can we only pull data, or can we also push notifications and so on? And we want to have a single pipeline. And in this case, we will have this computer data as a big product composed of different protocols. So, coordinator to organize, to orchestrate this workflow seems very inefficient. Because if we think about just these 4 layers, there could be much more, there could be less, but if we think about just 4 layers, then there is no good dedicated place or location, and even geographical location or protocol-wise location. What network should it be like located in, or should it be a Web2 like endpoint? Just no very efficient place. In Web2, it's not the case, because you can have everything in one place, and you can you can have one endpoint that actually leads to the workflow being executed inside like the cloud. But in Web3, probably not. And also, if you have a coordinator, it's going to be too powerful in terms of ability to censor the facts, or to change them, or to move them to some other storage that user haven't authorized to work with this data, and so on. All of this could be managed inside a single network. So if we say that compute over data is actually about creating just one network that is a one-stop shop that does everything, probably it would be enough to have some protocol inside this network to discover the right place to have the call and so on. But in the real life, even for Web 2, one network is not enough. And even in Web 2, we have different solutions for the edge and different regions and different stores and so on. So probably what we want to have is finally a flow of service composition that is coordinator-free, permissionless, like ready to be composed and integrated with different protocols. And we want to have this workflow to look somewhat like this. So we have certain steps, and we can describe the workflow, be it some kind of controller for a user interface, or really data processing, or anything like that. We can abstract it out to something that consists of very simple steps. For example, I want to get data, then I want to discover the edge peers which are ready to serve me. Like, ideally, they should be prepared. Then I run compute on the edge. I wait for the proper results, given the consensus or security capabilities of these edge peers and proofs. After that, I discover some kind of fog, some intermediary computations for the real time. I move the control flow here, run compute on fog, wait for proper results and proof, and after that, I discover storage. Like, why should I discover? Because it could depend on the data that I got from the fog compute. For example, I could determine the right shard which points on the subnetwork, on small network, only during this computation. I cannot, probably, I cannot have everything in place from the very beginning. But I can discover every next step, and after this, like, discover, run, wait, discover, run, wait, discover, run, wait, and finally done. But if these peers are not prepared to serve me, if they're not warmed up, then I want to have the pipeline like this. I try to discover edge. If I cannot, I'm trying to do latency-based discovery to find the closest peers, deploy the code on them, so that to prepare the edge nodes. The same for the fog. I want to find the capable peers. If they are not ready, if they are not in cache, deploy the content on them. So on every step, I do some computations. I have the decision about the next step, and I push my requirements to have the next step prepared for me. So until everything is done. And when it's done, it doesn't mean that it's just stored. I might want to have the proofs that everything was done, that everything is okay. Or maybe I want to distribute some incentives or to have some acknowledges. So ideally, the pipeline should look like this, and it should not depend on any particular network. So that's about the Fluence approach. Given all of this in mind, we created a set of tools that makes it possible, like today. So first of all, we have an Aqua. Aqua is the way to express these workflows, which are like decomposed into this discovery compute steps with maybe some provisioning, like deploy something or not, or failover or not, and so on. And you can compose distributed workflows which are suitable for open networks from these basic steps. It's push-based, so next peers are resolved on the fly, and you can take the actual real-time connectivity into account so that you can optimize the way. You don't say want, you say I'm going here because it's meaningful for me. And a push-based approach means that still having an open network, you involve the minimal amount of peers possible. And the minimal amount of peers means that it depends heavily on the discovery mechanics. If you have log n, then you have log n peers. If you have several logarithmic discovery processes, like in Cademlia, then you have k log n or something like that. But if you can reduce the scope of lookup, so for example, using not the whole Cademlia or the whole network, pretending that all the peers are the same, but instead if you can, using some attribute, select a subset of the big network and organize some kind of Cademlia on top of this, then it's much more performant. And if you have a hot cache, it's even better. So, but fundamentally, it depends on how exactly you write the code, and you have full control. It works on top of libp2p, but it doesn't require you to recompile, rebuild, redeploy the network or the networks. So if some protocol is ready to serve Aqua, then it's just ready, and you can use it for composition without any additional communication with the team, I don't know, protocol forking and so on. And you can have different workflows. So it's open for integration with all the other protocols. And as the result of execution, as the side effect, it provides an audit log that only what you expected to happen have happened. And you can use this log, and we're going to use this log for the incentives layer. With Aqua, you can express these smaller networks on top of compute over data network protocols. So subnetwork is a network formed around a certain resource or attribute. For example, data for a user or peers of protocol N close to region G. It's an attribute or a set of attributes, or peers capable to access some data like blockchain B, which run Fluence, and at the same time which run, I don't know, Filecoin, for example, so that you can access the new blocks. And with Aqua, you can do subnetwork formation using Aqua just libraries to interconnect, sync, bring code on peers, deploy, provision, and so on, because all these network concepts of having connectivity or having agreement over data, they could be also decomposed to single workflows. And if you can have a set of workflows to run on the network without the end user interaction with these workflows, but instead with the subnetwork, then effectively you have the subnetwork. And you can have subnetwork discovery as an Aqua library as well. And the composition of subnetworks, which means pushing data and control flow to the next and next and next subnetworks, meaning peers of these subnetworks, because nothing magical. It's just a new line character. You get from one line of the code to another, and it could mean moving compute and data to the next peer. And finally, Aqua is part of Fluence, and you can think about Fluence as the workflow stack for compute over data network discovery and composability. Yeah, COD, ND, and C. So Fluence accompanies protocols to help them organize push-based and purpose-driven workflows. So we are open for different protocols. as a sidecar or as libp2p protocol. With Aqua, the language, you can describe the workflow, orchestrate, provision, and so on. And we have Marine. Marine is a WebAssembly runtime to run compute, or probably highly likely to lift another API or protocol running on the same peer to Aqua. So just to enable the composition, you can write a very small WebAssembly to use the capabilities that you already developed in another protocol. Or if you don't want to do it, if you want to do all Fluence with all the portability and so on, you can do pure WASM. And Fluence as network is a libp2p based network for Aqua and Marine to enable discovery and composition of all the parts. There is a huge amount of missing details in my talk, so I was just sharing our thoughts and approach. And if you want to learn more, take a look on fluence.dev, or let's chat after this and after the break or during the break. I see that everything is prepared. So thank you for your attention. And then
we have about 3 minutes for questions if anyone has any, and then we'll go to break.
Hi, thank you for the talk. I have 3 questions, but maybe, I don't know, can start. Have you thought about load balancing on peers? So you said your pipeline is discovery and then push computations, right?
I haven't touched this aspect, but let's think about load balancing as a data-driven discovery algorithm. So what does it mean? Load balancing means that you have a network, a set of peers, and these peers can do some job. And they are, maybe that's one of the approaches, they are at least aware about each other, and maybe they're aware about each other's current load. So this is the shared data, and then the discovery algorithm that takes this data into account is just a part of the workflow. So we've been developing these things as well. We have some data about the workload provided by default as the part of the protocol, so you can do this as well.
Okay, thank you. Yeah, because I mean you cannot push every computation to the same peer if the same peer is doing all the computations, right?
Yeah.
Okay, so the second question, which I thought, so you talked about doing discovery over Kademli, correct? Or some Kademli with some property on top, right?
Yeah, I said the word Kademli, and I said that for some cases it would be nice to have Kademli built out of the workflows, to have small Kademlias, because using big Kademli sometimes it's an overkill.
Exactly.
So actually you can decompose Kademli into workflows, and you have many Kademlias on the same set of peers serving different purposes for different service location. But it's not the only way to locate services.
Exactly.
It's just one of the ways.
My question is more like, so a DHT is good for an exact match kind of search, right? And here it seems to me that you want to do any match search. You want to find any peer that has this property, correct?
Depends on the use case. Sometimes I do, sometimes don't, but I'm not limited with the Kademli. We are in progress of developing attribute-driven Kademli. But that means that you have attributes. If you have something more complex, like a set of filters to find the proper peers, probably you need some data index to help you to decompose this set of properties into a set of discovery rules. This part is being in R&D. We can discuss it. It's very funny. We have some Bloom filters and so on, but not sure that it's the only way to solve this problem. So, yeah,
this would be interesting in discussing this with you.
Thank you. Hello, thanks for the talk. I've got a question about a use case where you don't know how many nodes you want to send work to before you started computing. So maybe you run the workflow and get big data and you're like, okay, I want to send that to 100 nodes and shard it out. Or maybe you get small data and you think, actually, I only need 2 nodes for that. Does Aqua support that sort of thing where you don't understand the shape of the execution up front and you work it out as you go along?
Well, you need to understand the shape because otherwise it's super unsecure to serve this workflow because we care about the security of the peers who participate in this workflow. But Aqua is based fundamentally on PyCalculus, and in PyCalculus you have this, like, I forgot the word, the fixed point analogy, recursion, kind of recursion. So basically, in Aqua you can do the for loop, and you can do for loop for parallel branches, which means that you can get the data, for example, the list of subscribers, and then you can do in parallel based on data many threads. And we are trying to solve the problem of amplification attack. In this case, we have some solutions, but it's an interesting topic. And basically, yes, Aqua allows to do it, but you need to have the code that expresses the workflow before you send it to the network. You need to sign it, otherwise there is no way to deal with amplification attack during the runtime.
That's cool, thank you.
Thank you.
Hello. Do you have idea of market or payments built in your reasoning?
Of what? Sorry?
Market.
Payments. Yes. We are in the process of finalizing the deal marketplace, which is akin to what we have in Filecoin. And for the entity that the payments will be distributed to, we have a subnetwork. So if you have a resource, you have subnetwork for this resource to have fault tolerance and something like that, and to have a capability for peer rotation. And you have a deal with this subnetwork to serve some job with you. And then I said that we have audit logs as a side effect of executing the workflow. And this audit log contains kind of the proofs of some peers serving jobs for a particular subnetwork. And eventually, with a golden ticket-like mechanics, we send this proof to a Rust-enabled blockchain to find the subnetworks and to distribute the rewards. This is the, like, in short, our approach to economy. We can talk about it more during the break.
Terrific. And with that, we are going to break. So thank you so much. And
thank you.
Be back here in about 15 minutes for our next talk. Thanks.
Morning. Joined the morning in Lisbon in this beautiful venue over here. Walked over here the other day and we thought this talk was going to be in the actual food market, so I was a little confused. But glad that we're not doing it there so we can get a little bit more focus. So my name is Zach Hayesh. I'm going to be talking about the Filecoin virtual machine. I'm a developer advocate with the FVM team. And kind of excited to bring this to you and talk about the possibilities about how we can collaborate between the FVM team and all the different teams working on compute over data. So a little aside I like to tell people at a lot of these conferences and talks, about imposter syndrome. So this piece of paper that you see here was me talking with the engineers on my team and trying to understand how addressing the F4 addressing class works in Filecoin. So, you go to all these events, you go see all these teams working on all these cool different research, and it can get a little bit overwhelming, right? It can feel like you don't really know what's going on, you're stuck in your silo, you know what's going on in your team, but that's the case for, I think, everyone here. So don't let it get to you. We're all learning, we're all in this together. So just a little note I want to make there. Thank you. Appreciate it. Yeah, so I'll give a quick introduction to the FVM. We'll talk about a little bit of just a brief overview of the architecture, the roadmap. I'll give a quick overview on some ideas on how FVM can be used with compute over data. And we'll do a demo using Remix just to make it alive for you. So, as the name kind of assumes, the FVM brings programmability to the Filecoin blockchain, right? So you may be familiar with blockchains like Ethereum, Polygon, Avalanche. They all have this concept of smart contracts where you can deploy code to the blockchain, and that code gets the same immutable properties that blockchain has. So FVM is taking that and bringing it to the Filecoin blockchain. So Filecoin, the blockchain, is still built at its base layer to be a blockchain for connecting users to storage deals, right? To storage providers. Filecoin, the FVM, sits kind of at this layer 1, and we call it computation over state, right? So everyone here is here for computation over data, which would sit on a layer even on top of that, right? The data that we're doing computation with in the FVM is not the data stored within the storage providers, but the data stored as state on the blockchain, right? So you'll have access to the deals that monitor the storage providers. You'll have access to any other actors or smart contracts that people deploy to the blockchain, but you won't have direct access to the data in the storage providers. That's where all the beautiful CoD projects come in. And yeah, this is just kind of a slide of a general idea of all the general use cases that we see being possible for the FVM. A lot of questions we get is, why would I deploy a actor or smart contract on Filecoin and not just deploy it to Ethereum or Avalanche or one of these other existing layer 1s that exist? And the answer I usually give is that none of these have the native primitive that is storage deals, right? Filecoin is the biggest blockchain in terms of storing the world's data, and none of these other blockchains have that ability, right? So you can make all kinds of cool contracts with data storage as a primitive. Right now, for instance, you can't just have a storage deal perpetually renew, right? Someone has to renew that storage deal. And if it's a data set that a large amount of people depend on, you have to hope that this person will just keep renewing the data. Well, now you can make things like data DAOs or perpetual storage contracts, or a group of people can fund the contract and keep that data stored and not rely on a single entity. And in general, data DAOs can enable all kinds of cool things, like maybe you put bounties up for important data sets that the world needs, right? Like maybe some scientific data that you would like some DeSci workers to put on chain. And so when the team was making the FVM, they were kind of inspired by Unix and hypervisors and being able to virtualize different runtimes on top of the system, right? So you'll see that they took this, and one of the first runtimes available is the FEVM, right? The Filecoin Ethereum Virtual Machine, right? So essentially taking the Filecoin Virtual Machine and emulating the Ethereum Virtual Machine on top of that. And we'll get to why in a second. Right, but at its core, the FEM is based on WebAssembly, right? So any language that compiles to WebAssembly, but one of the most popular ones is Rust. Yeah, it's built to support multiple runtimes. Right now, the EVM, maybe in the future, as we see other runtimes gain adoption in Web3, we can support things like Solana's runtime or Move or whatever else is the thing that becomes big. All data within the FEM is IPLD native. We have support for foreign addressing, right? So all these different blockchains and all these different runtimes, if we're going to support them, they each have their own addressing scheme, right? That's different from Filecoin's addressing scheme. And so natively, we already support foreign runtimes, abstract accounts, currently being worked on right now, but the team is getting very close to being able to deploy something there. And of course, some kind of built-in resource metering, essentially gas to make sure no one spams the network, and they pay for the computation they're asking for. So the roadmap. Back in July of 2022, many people don't know, but the FEM was already live. These are the built-in actors that were created, so they run WASM modules, but they're already kind of hard-coded into the code. You can interact with them, do some fun things, but there was no yet external deployable contracts, right? Like users couldn't just write some code and deploy it onto the blockchain. And as of right now, Wallaby testnet is online with the FEVM available, so you can write code in Solidity or anything that compiles the EVM bytecode and deploy it to the Filecoin chain. So why EVM? Why is EVM the first language that we allow deployable onto the chain? And that's for the simple case that there's already a whole bunch of tooling and support built out for the EVM, right? So a lot of Web3 developers, already know Solidity. There's tons of tutorials online. You got tools like Remix, which we'll use in a bit, Hardhat, Truffle, Brownie, testing frameworks, auditors, the whole works, right? And of course, we want to support native deployments. So after EVM, we'll move on to WASM actors on FEM, so allow people to compile any language to WASM and deploy actors. But for now, we want to take advantage of all the tooling that the community has already built in the EVM world to kind of bootstrap this whole process. And yeah, literally several days before this event happened, we had the first transaction happen on MetaMask, which is a very cool event for the team. Really kind of brought everything to life that, hey, this is going to work with the EVM and all the tooling that we got. And these are just some ideas, just a couple of small ideas on how FEM can kind of support COD. I'd love to have more discussions with people after this talk, and talk about how we can support your team specifically. But again, I think one of the important things is, access to storage deals, right? That native primitive to Filecoin. You can have perpetual data again, storage for important data sets that you may want to do continuous computes or make available to the public, and incentivized addition of other important data to the data sets to improve the results of any computation done. Of course, there's tokenizing incentives for the node operators, right? So, you might have this compute over data network as a L2 over a L1 FVM contract. And as they complete jobs, you can reward them in some kind of token, whether it be fill or a native token to the network. Of course, you can use it to orchestrate the jobs, have users post jobs on chain so it's immutably recorded, and orchestrate between different CoD networks maybe, orchestrate between retrievability networks like Saturn, all kinds of possibilities there. And even settle batch transactions on chain. If you really want to add an extra layer of verifiability, perhaps you could design a CoD network based on something like Lurk and have verifiability built into the network from the get-go, and then every time you do some combination, I like that Lurk shirt. That's dope. You got to hook me up with one of those. Yeah, you can have verifiability out the gate and post those validity proofs onto the chain and have it double check everything for you and your users. And right now, the FVM Foundry Early Builders Program is already open. We already have a whole lot of teams building on top of the FVM. And if you're interested, I highly recommend that you go to this website, fvm.filecoin/foundry, sign up and see how we can collaborate from that perspective. My colleague Sarah, who's not here at the moment, is kind of heading this and doing an excellent job. So yeah, please go to that website. And all right, so I'm going to go ahead and start with the Remix demo real quick, just to show you a contract deployment and a simple write to that contract. So one of the most important things you're going to need here is a MetaMask wallet with some TFIL, right? So I already have MetaMask installed. You can go to MetaMask, I believe metamask.io to install this. And I've already pre-filled it with TFIL, but I'll show you the process on how to do that. Oh, and of course, if you want to add the Wallaby network to MetaMask, it needs to know what network you're pointing to. Go to chainlist.org, click on testnets, type in Wallaby, and you'll see that Filecoin Wallaby is there with the chain ID, all the information. You just have to click connect wallet, add to MetaMask. I already have it added, so it's not going to pop up, but MetaMask will pop up, you confirm, and the network will be added to MetaMask. And then one more step is, remember how we talked about foreign addressing schemes, right? Well, in Filecoin, the F address class that we use to kind of represent all other runtimes is the F4 address class. And with MetaMask, we have the Ethereum address class, the 0x, blah, 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 addresses that if you've worked with EVM, you'll be used to. These, Filecoin doesn't understand natively, so they created a whole new address class that translates Ethereum addresses and really any other runtime to Filecoin addresses, right? And this cool explorer here, Glyph Explorer, explorer.glyph.io, actually has a tool that will just connect to your MetaMask in the browser and give you the F4 address, right? So here's our Ethereum address, and here's our F4 address. We'll take that, we'll copy it. And we'll go to wallaby.network, and you can scroll down and you'll find the faucet, right? This is where you'll post the F4 address and get to do a really fun CAPTCHA. They always have very interesting questions. This one's actually a pretty simple one. All right, and then hit send, and that'll send me even more TFIL to my wallet as if I wasn't rich enough with TFIL. All right, so now that you have a wallet filled with TFIL, you can go to remix.ethereum.org and see if we can get that back in there. No, that's fine. You can go to remix.ethereum.org, and if you're not familiar with Remix, this is kind of the gateway to a lot of EVM smart contract developers, right? It's not where a lot of professional teams develop their smart contracts, but I think it's a quick, easy introduction. If you're serious and you're really wanting to develop, a lot of people use internal tools or local tools like Hardhat and Brownie and Foundry, which are local IDEs. But this is a really cool tool to get used to experiment and to have demos like this. All right, so we're actually going to deploy a simple storage contract, a built-in one with Remix, storage.sol, and very simple contract. It has a variable number, it has a function store that variable, and a function to read that variable. Very basic, hello world level contract. You want to go to the Solidity compiler here, make sure it compiles. You can turn on auto-compile if you want. It will literally compile after like every click you do, so I usually keep that off. And very important here, you want to make sure that you're connected to injected provider MetaMask, right? It defaults to Remix VM London, which is just a internal fork on your browser, right? So it's not actually going to deploy anywhere. This will connect it to MetaMask, which is connected to Wallaby. So MetaMask will mediate all of our transactions. All right, make sure it's connected to storage here, and you are ready to deploy. So we'll click deploy. MetaMask will come up with this screen saying, hey, you're ready to pay gas. We'll hit confirm, and the deployment will go through. Now this keeps happening. I actually had a deployment like pre-ready, but Remix's cache keeps resetting and losing the contract. So it takes about 30 seconds for once you deploy a contract for it to be included on the chain. And Filecoin VM has kind of a deferred execution model. So it'll be another 30 seconds after all the execution is confirmed through that a transaction receipt is sent back. So this actually might take a minute. And if it doesn't come here in the next couple of seconds, we'll move on and we'll come back because there's a couple other things in the presentation I want to cover. So yeah, we'll come back to that. And I mentioned it earlier, but that was Remix. That's kind of in browser, great for just practicing with an MVP or getting your feet wet. But if you want to have more of a typical developer experience, there is this Hard Hat starter kit. I highly recommend that you check it out and download it. There's a little QR code here if you need the website. But it can be found on Filecoin's GitHub. And this will provide a local development environment with some built-in tasks to deploy to Wallaby automatically. And currently a work in progress, so we're getting it cleaned up more and more. I'm going to add TypeScript, a couple of other things. And in the future, hopefully we'll support things like Brownie if you prefer to automate your tasks with Python. All right, let's see if that contract deployed. And yes, all right, so we have it deployed right here. It gives you the address of the deployed contract on Wallaby in terms of ETH. So behind the scenes, all that F4 translation is being done and just orchestrated for you. And if we hit retrieve now, we get 0, right? So EVM defaults all new variables to 0 in the background. So we're actually going to need to store a number if we want to show it. We'll just store 100. Click store. MetaMask will pop up again. We'll hit confirm. And again, this will take another minute, so we can return back to this. But I think y'all get the gist. It's going to take about a minute. It's going to come back. I'm going to hit retrieve, and it's going to show 100, right? And yeah, so that's kind of Remix working with the FEVM on top of the FVM. So another resource I'd like to push people to, if you have any questions and you're not at a conference like this and we're easily accessible, is the forums. These were just recently incubated, and we're putting a bunch of tutorials and how-tos on there. Community is already jumping on. We have several community contributors. So yeah, feel free to check this out. If you have any questions at all, no matter how silly, please post them on there. If you have them, probably a million other people have them, and the team will be monitoring it and, be there to answer some questions. And so yeah, we talked about what the FVM can do. I kind of showed it. showed it off, but what can't it do? It can't actually build the apps on top of it, right? So that's why we're doing presentations at places like this. So, we can enable you to build apps on top of the FVM, right? So I'm looking forward to all the cool apps that people build after this. I showed the roadmap. Right now we're on testnet, but later in the year we'll be having a hackathon where you can actually build apps and, compete for prizes, and then hopefully mainnet will be early next year. And this is the lovely FVM team. If you see any of us around at the conference going forward, please ask us questions again. I feel like we're all open and friendly people. And yeah, that's my presentation. If you have any questions, now's the time to ask. Thank you.
Is the correct mental model for FEVM that it's actually a separate virtual machine on top of FVM, or is it more like it's translating the instructions so that you could get data that wasn't initially in FEVM, or is it like a completely separate?
It's translating instructions, right? So you can actually access like the built-in actors that are already there, the WASM actors. There's not like great support for that at the moment. That's still being worked on. But yeah, it's doing the translation on the back end. Right, so one of the advantages when the native FEM, like you can deploy actors to native FEM, is that you'll get better performance, right? So there's no translation step.
Cool, thank you.
Yep. Any other questions? I believe we had one up here. Yep.
Thank you, yeah, great talk. Do you have a link to any documentation or something where we can try the demo that you showed ourselves?
Yeah. So the documentation is still a work in progress as well.
Yeah,
the
sure.
forums are kind of being the proto docs right now.
Sure.
We're working with the docs team to get that up and running and kind of basing it on like a lot of the questions that we're seeing from the forums. Mm-hmm. But for right now, no.
Okay.
If you go to the Hard Hat starter kit, it does walk you like step by step in the README on how to use it.
Okay.
And yeah, you'll find tutorials and stuff on the forums.
Okay, so we should check the forums and we can run stuff on the testnet now, right?
Yeah, correct.
Awesome, thank you.
Cool. Any other questions? Yep, right over here. One second. Yeah, I'll wait for him to give you the mic.
So for the hackathons, they're completely open. Do you have tracks or requests for startups with more idea on what you can build, or it's completely
Yeah. So anyone can deploy an actor at any time. Now that Wallaby is up, you can mess around with Remix or Hard Hat and deploy an actor. But if you have an idea and you want to like get some support, that Foundry program that I showed earlier, that's where you want to go, right? We already have several projects that have a couple of ideas working on there, like those perpetual storage and data DAOs and some of those use cases, and they're kind of working out of that program. So.
Okay, these two are the most go-to at the moment as use cases, right?
Yeah, those are the ones I like.
Okay.
There was that whole like list up there, but I think those are the easiest to grok like right up front.
Got it.
Hey, thanks for the presentation. Can you elaborate a little bit on the interface to the existing actors or storage models, but also like would you support BLS curve natively in the
like the
EVM,
precompiles and
right?
stuff?
Will you have different precompiles than normal EVM because you have those curves already?
Now I believe the team is currently working on the precompiles. I don't think they're there quite yet on the EVM, but the plan is to have as close to possible as the native EVM. Also, I didn't mention, but right now, there's no logs or events. That's one of the other big features that's missing. And that's like being worked on ASAP. So, hopefully in the next week or two, those will be live. But yeah, they're working to get it as native as possible.
Do you know what are the performance limits? And if there are there any plans to shard execution layer?
Yeah. So there's actually, Mache and our team just answered that question on like the block size and everything and the tip set size. You can find that hopefully on the forum. He should have posted on the forum now. I had talked to him last night. But yeah, I know that the consensus lab team in Protocol Labs is working on interplanetary consensus, so basically a form of sharding, like creating subnets and attaching, and that'll be fully compatible with FEM, so we're working with them to make sure FEM is running on those. But you know, that's kind of in the distance and separate from my team.
Any thoughts on Oracle technologies that could bridge smart contract with compute and data, so we can have maybe a Solidity contract launching a job in Bacalao or something and getting something back? And do you see any advantages in being in the Filecoin ecosystem, or do you think that the solution will be something generic from the, like Chainlink or something?
Yeah, that's a great question. I actually worked at Chainlink before here, so I worked a lot with oracles. I mean, I feel like if, you know, a team like Bacalao, you know, wants to do it, they would make their own oracles. Like the network itself is basically already an oracle, like a CoD network. You're sending information off chain to this other network. It's doing some work. You know, it can post data on chain. I mean, of course, the FVM is open to anyone, so any system can deploy there if they want to. But yeah, I think oracles are going to be an important part of that ecosystem, right? Like you're going to want to connect to some outside data that isn't available on the blockchain. Did that answer your question?
Is there something in the makings of within the Filecoin ecosystem, or should we be looking outside in the general Oracle technologies that exist already for EVM?
I believe there's some projects working in the Foundry program on things like bridges and other kind of general Oracle tech. I'm not super caught up on Foundry. That's, again, my colleague Sarah who's kind of heading that, but I believe so. Okay. But, you know, I'm sure that, like, you know, like everything, there's people that I don't even know looking to deploy their technology to the network.
Hey, I'm Charles from First One team. So basically, the Chainlink cross-chain technology is our team is working on that, where we have a first product to enable you using Chainlink external technology, adapter technology, to bridging the Filecoin data on top of a smart contract to Polygon network. So as you said, we are the Foundry project. So we continue working on that in FVM, integrated with Solidity. The workflow is that we building an external adapter, continuously broadcasting every DL with the DLC ID and the information inside it. You can consume the data based on the smart contract deployed with the Chainlink or Oracle operator, and you can get the information. For now, we already enable you to using the price feed based on Filecoin vs US dollar, so you can unlock the contract, perform some ZK proofing and payment with DeFi pricing to get swapped the token to Filecoin token, pay the storage on Filecoin network. So integrate with the FVM, there'll be one step over, which means that we don't really need a swap anymore. We can do the DX directly on Filecoin network, get a direct payment. Yeah, thank you.
Yeah, awesome. Appreciate that. Yeah, I'm sure we're running on time now. So thanks everyone for the questions. And yeah, catch me around. See ya.
Thank you very much. All right. Let's see if that's a quick swap. Oh, there it is. Good. Thank you. Okay. Can we switch over the slides? Oh, there we are. All right, moving right along. So I'm here back again to talk about Bacalao.
a platform to bring to compute to data. As I mentioned earlier, Bacalhau, we hope, is just one of many platforms, many different specifications and things like that. But we've made some terrific progress, and I'd love to show what we have today. So that's us, that's the fish. By the way, everyone knows why it's called Bacalhau? Does anyone know why it's called Bacalhau? Anyone? So it's like we were in Portugal last year when we were thinking it up. Compute over data, CoD, Bacalhau, that's the joke. And the question is, we had at that time was, can we build a decentralized system that was built for decentralized compute, right? Start with decentralized compute first and work from there. So in February, when we started, we set ourselves a goal for April to have a Computer over Data Summit and to set some of the goals you see here. Very small, very gradual. Interestingly, I was one of the first PMs on Kubernetes, and I led it for several years, and this is much bigger than we had as our first one. Kubernetes gated at 50 nodes at the start, interestingly. A little data point for you. So this was actually more substantial than that. But we said, with 8 weeks, we feel like this is something we can do as a proof of concept. So we started, first line of code written. I think I wrote it. I don't know. It was like Kai, me, or Luke. Somebody wrote it. Somebody checked it in. It was, I think, CI. Who knows? Anyhow, you can go check the repo. It's there. And the first Compute over Data Summit was just 8 weeks later. And we did really well. I was shocked, actually. Luke and Kai get on stage. They demoed it. They demoed our interfaces and things like that. I'll give us yellows for 5.9s. I think we didn't have quite enough monitoring things at the time. And deterministic, certainly it was there of a proof of concept, but there was a lot to desire. But the rest of it did work. Scheduling and CIDs and public data and so on. So then we said, okay, let's present this to everyone. We got really good feedback. You can see there, that's our first teeny little group getting together, being excited. And the number one question was like, okay, you're practically done, right? When is it coming? So we set ourselves a big, hairy, audacious goal. And that goal is what you see here, right? We wanted to get to 1,000 nodes, provably 1,000 nodes. We don't actually need 1,000 nodes running. That being able to run, not just schedule 10,000 jobs, be able to process basically unlimited amount of data across many nodes, job success rate, malicious nodes, or handling malicious nodes, DAGs, and so on and so forth. You can see those there. And that's a lot. That's a lot to take on for October. But we are not, if nothing, not ambitious. So in June 1, we launched alpha to production. No gates, no anything. You could go out there, download a client, and have at it. In August, we added Filecoin and estuary support. And in September, right at the beginning of September, we were able to add native WASM and GPUs. So we went back and looked at this, and we said, okay, we're actually at where we wanted to be timeline-wise. We actually were about a month early. And, some reds here, no question. Very, very large file processing we weren't able to do. We didn't do DAGs or malicious nodes at the time, and no reputation system to speak of. But we did succeed in a bunch of things. You can see those there. But along the way, we had listened to a bunch of people from the ecosystem who were already giving us feedback, who were always saying, hey, this would be great. If you could do this, can you do it? And you can see this list on the right here. So everything you see on the right there was not in the original spec, yet it is what we delivered. GPUs, HTTP downloads, open telemetry, you name it. Huge performance wins, huge examinations of locks and mutexes and things like that. So we were really pleased with that, and we were moving forward. So, which brings us to today, where we are proud to announce our beta. Now, obviously, it is beta. There will still be API movement. Oh, thank you. So, there will still be movement in the API and things like that, but we really are taking on SLA and things like that. We want to have uptime. We have canaries. We have all sorts of things that we want to nail. And I'll talk about our path to getting to 1.0 and things like that at the end. And again, it goes back to our original vision. Can we deliver simple, low-cost, distributed first tools and unlock new ecosystems and collaboration? And if we do that, you'll get simplified execution, you'll get huge performance wins over even potentially a lot of existing systems today, and you'll launch a new collaborative scientific community. And one of the things when I say simple is really meeting people where we are. And so I went through this thought experiment. I gave this slide back in April, and I said, look, this is what people are using today. This is Microsoft's research. They published it. They use 158 different tools, 68 different tools. Oh, 59, sorry. Different tools. It's just an enormous amount. And if you map to what we can support today, it's actually not bad. I don't know, call it 50-50. And some of these we'll never support. Like, we're not going to support PowerPoint. Sorry. Well, who knows? Maybe you could script PowerPoint. I have no idea. We do support Windows, by the way, so maybe. But, and some are yellow. Like, yeah, you can throw it in a container. Is that really doing it? But the point is that it's not that bad, right? You can throw a Jupyter notebook in. You can throw Python, so on and so forth. Not terrible. But I think this is really a mission. Like, how little can we have data scientists do and take advantage of all these things? So you may be asking, what can I do with it today? And so let's show right here on stage. So I'm going to start with a very simple one, right? One thing that's kind of weird about Filecoin, no matter how awesome and like widespread, universal it is, it's actually kind of hard to upload your data. Not with Bacalhau. This is it. Seriously. Can you abuse this to your heart's content? Well, obviously. So let's go. I don't know if you've seen, there is some, can you see this here? Yeah, good. So I'm a cheese fan, so I'm going to search for some cheese. Wensleydale. Cheese. I'm going to be very responsible here and use only a Creative Commons one because I want to be a good citizen to the world. Oop. Okay. And I'm going to grab this image of Wensleydale cheese here, which is on the Creative Commons thing. I'm going to find this. I'm going to go over here. Oops. I'm going to enter it as a URL. And now I'm going to execute this command. Oops, sorry. Now, what you see here, it says Bacalhau Docker run. I give it an input URL. I give it a container that we offer called the uploader, and I return. That's it. I've taken an image that was out there in the world. It is now running. It is finding it, downloading it, copying it over to Bacalhau. Presto, we're done. And now I take this. I say, go get it for me. I was a little bit nervous. It's not that we don't support it, just oftentimes the handshake to actually getting the thing. Oh, wow, fantastic. I'm going to go grab this. It downloaded it into this handy folder here. Combined results, outputs, and there we are, Wensleydale cheese, presto. That was uploaded, put on Estuary, put on Filecoin, downloaded through Bacalhau, and by the way, not just there, right? I can go straight up to any other gateway and get it. Presto, magic. And it's cheese, which I'm always a fan of. So that's not abuse. That's just nothing. So I don't know if you've seen, for example, they have these great data sets out there in the world. This, in fact, is NOAA's geostationary orbit, right? There's a lot of images in that. In fact, if you open up the buckets, you could see like hundreds, thousands of images. I mean, it'd be a shame if someone didn't grab every single URL and throw it in a, simple loop and execute the hell out of that. So now, every UUID you see here is being uploaded to Filecoin as we speak. So that's pretty easy, wouldn't you say? That's it, €1,000. So not so bad. So there you go. Abuse away. And by the way, I should point out there, you have a QR code in the upper right corner. Every one of those QR codes are different, and they all link to our public documentation where you can see stuff. So, all right, now I have a bunch of data on Filecoin. What can I do with it? Well, I could run some Python. There you go. Upper right, you can run it right there in line. Middle, you can run a complex thing where you might need to import things. Unfortunately, we don't support, as you know, you can, we'll get to how you do it in a minute. You can't do requirements and things like that in this format, but you can, anything that's native to Python you could do. Or if you do need to do something complicated, you can see down there in the lower left, you can actually put your entire script on, you know, Filecoin using the same URL that I showed earlier, and it'll run just fine. Okay, how about R? R is pretty popular data science. We got R. There you go. And you're like, all right, fine. Hello world. Let's get to the good stuff. All right. So now we're going to start to get more complicated. Pandas, again, huge data processing thing, super easy or super powerful. In this case, I mentioned about like using multiple files simultaneously. How would you do that? Well, there you go. So you can see in that tree, I have both a CSV reader and transactions that I'm going to want to process. I'm going to add both of those into a IPFS, get CIDs back. And then down below, you can see I'm going to mount those CIDs into a folder. You can see there I can name the folder, working directory files. I run my pandas container, and then I run the script that I was doing, and it's able to mount in all the files that I had named earlier into that single folder and just execute it like it was on my local machine, right? There you go. This one's insane, but it's so good, I love it. Let's say you have a Parquet file. Who knows DuckDB? Anyone? All right, not a lot of people. So it's this wonderful thing that basically will allow you to mount in columnar databases, or columnar files at all, and give you full SQL functionality against it. So in this case, you're going to mount in the CID of a Parquet file that I want, and start DuckDB, and execute arbitrary SQL against it. Then it shuts it down, tears it down, and destroys it. But now I get full SQL against any Parquet file in the world without installing anything. That's pretty sweet. Who knows what YOLO is? YOLO is the #1 object detection thing for images. You can see here. We're just going to mount in YOLO and run that. Presto, YOLO. And you do that over thousands of images if you want. And one thing I want to show about this architecture here is the YOLO container is actually quite small because we are mounting in the weights from IPFS. Meaning you don't have to download all these various things in order to do it, especially if your containers are quite large. That makes it extremely portable. And because we schedule to where the data already is, spin up time for this should be quite quick as well. And if they're not available and you want more CPUs, you're able to do that. How about go figure out the next protein? You can do AlphaFold. Not too bad. All right. You're saying lame. You're demanding. Stable diffusion. Let's get to it, baby. All right, so if you are silly, like me, you like cheese, and you really want to be silly about this. So what we're going to do is here, we do have a stable diffusion container. We have GPUs on the network. Let's abuse this. I like cheeses, so I downloaded 1,000 cheeses. You can see them here. I wanted to have a verb, just to like say that cheese is going to do something. I don't know, who knows what, right? Stable diffusion, you'll figure it out. I merged them together into a bunch of sentences. Cheese, cheddar, cloth-bound survey, now Oklahoma City would go blah, 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 blah. Who knows? Stable diffusion will figure it out. And I executed 1,000 of them. So there you go. Running on the back of the network. We're going to pop over, and here you go. Once per second, it will go out to the network and grab stable diffusion doing something silly with that sentence. There you go. I mean, I have done a lot of demos and led up to things in my life. This probably was some of the wildest demos. I was like, what else can I do? Oh, here we go. Some of them are crazy. Like, how do they, like, look at that. That looks like a real picture. Man, stable diffusion is amazing. And some of them are just, what is she doing? She's running with cheese? I have no idea. All right. All right, back to the demo. So, like I said, you can go get that. We have that published. I will say, by the way, you run on CPUs, be expected to wait. That's fine. There aren't that many GPUs in the network. We would love you all to join and participate in GPUs, but there you go. Seriously. And, here you go. Lots more stuff that we did. Some real nightmare fuel out there, by the way. Still, well, geez, man, you guys are demanding. It's WASM time. So I took that, actually it wasn't me, it was my colleague, took that Stable Diffusion demo here. We generated a bunch of superhero dogs, and we ran those. Oops, sorry. Here's the code. Again, it's all hosted out there. Very simple. It takes the existing image that's already out on Stable Diffusion, or on IPFS, and it runs in WASM a transformer to convert that into just, I don't know, take your random image conversion tool. Here, we're going to run that over here to the side. I will zip forward here. There are my superhero dogs generated by Stable Diffusion, and now we're going to apply a filter against them, and you can see those there, right? Again, in WASM, executed on the network. I didn't have to think about anything. I just ran my code. And let me just break this down for you for 1 second, right? You write your app, whatever it might be. You use, in this case, cargo to target your WASM runtime, and that's it. You're done. We upload the job to Bacalhau, find an appropriate node, mount it in IPFS, mount the data, in from IPFS, run the job, and write the results for you. Again, could not be simpler. Just stay focused on what you do great, what every data scientist does great, and go from there. We promise. And even further, you don't even have to install it. Every one of these examples has a notebook on Colab. You can just go click it, run it right there in the browser. Kind of. So our motto is, if you can contain it and you can compile it to WASM, you can run it. Mostly because we don't have any networking for now. Networking is a huge security flaw or security surface area, and we want to be very, very sensitive about that. And you might say these seem like science projects. These seem like Dave having a good time with demo. Too much fun with demo, probably, but there you go. I want real world, and we are very happy to announce many real world partners that we're launching. A few are listed here. So first, we're proud to announce we will be partnering with the Caltech High Energy Physics Lab to do work with their Large Hadron Collider CERN processing. We will also be partnering with LabDAO to accelerate scientific progress, enabling people to use our compute or use the compute framework to deploy and run. We will be partnering with the city of Las Vegas and Blocks to launch CCTV for internal processing and other things like that. That data is going to be available and online. This was a really interesting one because they have requirements on locality and where that can be deployed, and you can deploy the Bacalhau network to your own private network if appropriate. Again, our feeling is that this is even easier than a lot of the big data platforms today. They're just far more valuable and easier to engage with than having to set up Hadoop, Spark, so on. I don't want to take anything away from those platforms, but we solve a different purpose. We're doing a lot simpler things in a sharded, decentralized first way. When you get to the end of it, then sure, engage with these other things that are more appropriate for things like streams. We're also proud to be partnering with the Boeing project. For those that don't know, one of the earliest broad-scale end-user contributions, SETI at home, climate prediction, Rosetta Bio, things like that. We're going to be partnering with them as well. And finally, you'll hear about WeatherXM later today. We're very excited to be partnering with them. They're collecting weather data from all over the world, and we're going to help them process and run their models on it. So those are all launching today or very soon. Certainly the announcements today, but very soon we'll be talking about them and what they're doing publicly. I talked about earlier the compute over data and what we're trying to achieve via compute over data. You can see that here. Our hope is that Bacalhau sits, right at the center of it. And if we're not, we really want to get there. So we are very serious about being a very open, very extensible platform, not just for us. We want to also enable other platforms that want access to compute over file client compute over data, helping them achieve that. So what's next? I'm going to walk through a little bit of our roadmap over the next year or so. When we think about it, we really think about breaking it down into two major categories. First, from the end user side, you have people who are actually wanting to run jobs on it. And from the compute provider side, those are people who want to enrich their storage provider deployments or potentially earn incentive. Obviously, we don't have incentives yet. We're working on that. But there's like making the storage they're already hosting on Filecoin and IPFS richer, since we plug in directly. All you have to do is mount it in, and we can run it. In M1 in December, we're going to be powered by Phil Plus. We're going to make significant improvements on performance, reliability. We're also going to launch our dashboard, which we're really excited about. So you'll be able to look across the entire network, see jobs, see your jobs, and things like that. In March, we will finalize our support for WASM. What you see here is, I would call it beta quality, which is fine. We are at beta. We're going to improve reliability, particularly in transport, making sure your jobs are running to completion, that the network handles that. We also are very serious about improving the developer experience. We want to make that loop of executing jobs very, very straightforward. So you can, on your local laptop, simulate what it's like to run a full back-end network, and then when you move it to the network, you can be very certain that you're getting exactly what you ran locally. We're also planning on launching our API client to 1.0. Means API stability, building on it will be much more predictable, and if nothing else, we're going to have versioning. We do have API versioning right now, but we're going to be better about enforcing it and having backwards compatibility per whatever we decide as a community. Also, we're going to have our grant program on our back AL season beginning. In June, we're again going to work to improve our developer experiences, particularly around some of the most difficult concepts for decentralized systems, or distributed execution today, MapReduce, sharding, things like that. We already do support very rich sharding today, but not over single files, and which can be a problem. If you have a very large file, how do we split it up? How do we make it easy? Also, finalizing support for DAGs, full DAGs, though we already do have some work on that initially. I think we could do a lot more. Federated reads, so if you have a large file that crosses many machines, how do you read from them all simultaneously? How do you join them and execute them? And rich local client. And finally, consensus and verification of deterministic jobs in September, website for data, no-code type experiences, those kind of things. On the compute provider side, we're going to have Phil Plus. Our plan right now is to look at, if you run the compute job, you will get first rights to bid on the Phil Plus deal. So if you run it on a Phil Plus, you'll be able to get Phil Plus on the other side. Obviously, that's a huge incentive to anyone wanting to participate in that program. In March, looking at the unified control plane, so if you have many nodes, being able to look at them, graph them, understand what's going on, understand who's running what on your machines. You can already do that right now, but giving people a much cleaner way to interact with that. Multiple executor support, we talked about that, and our server API reaches 1.0. In June of 2023, additional deal engines. Like I said, we already support Estuary. We want to add many more. We're also going to support for much more malicious network attacks, Byzantine fault tolerance up to 1/3. And then finally, our end of the year goal is that anyone can be a compute provider. I was, incredibly inspired by AlphaFold and SETI at Home and things like that. I want to have everyone, on this very powerful machine that most of the day does nothing, be able to participate in the back AO network and potentially, advance humanity. And with that, that's it. Oop. No more cheese. Any questions? Yeah, question back there?
For the server M3, how are you approaching the Byzantine fault tolerance? And is that going to be an FVM integration or?
We are speccing it out as we speak.
Awesome.
We are talking very closely with the FVM team. Obviously, they provide you a layer of consensus immediately, and so it's very optimistic that we're hopeful that we're able to do it. I think if I was to place my bets, I think that integration with them would be quite likely. But we don't want to have them, need to take a dependency on us. If they're like have other priorities, then you know, I want to make sure that they're able to execute according to their schedule. But over time, I'd be very surprised if we weren't closely integrated.
Sick. Thank you.
Any other questions? Yep.
Hi, great talk. Also love cheese. Perfect. So my question is, do Bacalhau nodes communicate? So what I mean is, so I submit a job. A job has 2 computations, let's say. So can 2 Bacalhau nodes coordinate those computations? Is that something that you're looking forward or not?
So there's a subtle thing there, and I'm going to break it apart, if I might. The first is DAGs, a DAG, directed acyclic graph, right? Like, how do you start at one place and get to another place along many steps that may, you know, fan in, fan out, have conditionals, all that kind of stuff. We plan on supporting that. We are actually already working on that as we speak, so that you can submit to the network your DAG, and we will figure out how to execute it, whether or not it's on a single node, whether or not it's over a series of nodes with intermediate steps, things like that. We are working on that. However, the networking thing, we do not support right now because the attack surface is too high today. Every node has no networking. You know, it's very disappointing, but it is true. No networking, meaning after you start your job, you saw there that I could mount in from a URL, anything, but that is before the job begins. Once the job begins, that's it. So, no, like for example, downloading from PyPy and you know your requirements. You got to build that into the container or have it in a you know already mounted on IPFS. No worker parameters, you know master nodes for a 3-tier TensorFlow deployment or something like that, right? Unfortunately, it's just too big an opportunity for like attack, and it also hurts the ability to do determinism. That said, we have a lot of really good ideas how to get around that in very isolated ways. We just haven't gotten there yet. As you saw on the roadmap, our back of the envelope guess is September of 2023, which is a long time. I think we can come up with intermediate steps that might get you there, but it's the reality for like truly like treating this like a general network. That's probably when it is.
Okay, thank you.
Yeah.
I'm really interested in the reputation structure you're thinking about. I'm wondering if you can talk a little bit about it.
Still very much in the spec phase. We have a lot of thoughts. I think that we're exploring just about every model that is out there, whether or not it's having referees that oversee things until we bootstrap a reputation system, historical reputation. Once things, you know, you could also imagine, you know, generalized consensus where you deploy this. It's actually quite trivial to deploy to like 10 jobs concurrently, and then at the end evaluate like if all the things equate to each other. You could do that too, or like some number of them equate to each other. But I will say, I will be honest, it is very early thinking there. We're always looking to plug someone else in. We would love not to invent it ourselves.
Awesome, thank you.
Any other questions? I think I have time for one more.
Sorry, a lot of questions. Big fan. Do you guys support harnessing like multi-CPU or GPU hardware stuff already, or where does that fit into the roadmap?
We do. It is fully supported. So it's already it's basically, just assume anything Docker can do, we can do.
Okay.
So absolutely multi-thread, multi-GPU, things like that. We don't have any multi-GPU machines on the network, so you got to add your own, but or like encourage people to add their own, but yes.
Awesome, thank you.
One more.
What about TPUs? Do you have a plan for that?
No plan. I have no idea what
I mean,
Google's,
when eventually storage providers will, I don't know, sometime in the future.
To be clear, again, we are gated on Docker for now. So if you can give me a Docker container that runs TPUs and then mount a machine that supports TPUs, there's absolutely no reason you couldn't do it. There was one right here. Then I promise that's the last one. Is Juan here? Okay.
I do a lot of work with ecological data, like in a forest. How do you imagine this could work for edge computing and edge storage and those kind of environments?
Edge. Well, as I said in the first talk, this is designed specifically for that, right? So, like I said, if you can contain it, you can run it. So what I would say is, depending on how low power your edge is, this is an ideal network for you. What you would do is, at the edge, you would collect your data, you would write it to some file store, you'd upload it to IPFS, which eventually would propagate to the rest of the network based on whatever your requirements, or not at all. The back of your node would run on that same edge. This is a very lightweight deployment, just sit there and run. And you would request to the network and select, I want it to run against things that have this data or in this particular machine profile or my private signaling, right, label. I want it only to run in whatever, Yosemite on whatever these devices. Again, we're looking through a lot of the node selection stuff right now. There's a lot of flexibility and we'd love to get, your specific requirements. But the net is you would take that job, either, raw compiled code, WASM, or your container. It would push it down to that edge, it would run it locally, and then it would give you only the derivative. And so in many ways, this is hugely valuable for that, because those things on 256 kilobit connections that connect once a day, you don't want to be interacting with them in some long-standing way that requires this huge long uptime. You want it to trickle back the results and trickle back just what you need. So if you had said hey, 98% of the day, there's no data, and then 2% is, normally today you would have to push all that back to the server in order to figure out there was 98% of it was worthless. If you could run a simple filter job on the edge where it is right now, and then push back only to 2%, that'd be a huge win. Okay.
Sounds good.
That is my time, so thank you so much.
understand my offense. Is that good?
Yeah, if you just sweet. Just let me know when you want to plug in.
Almost there. One second. All right, great. Ready to go. Cool. That's good. Can you hear me? Great. All right, cool. Hey everyone, great to see you. Just a quick question. How long is this, the time slot? 20 minutes? What's that? No. What's the actual time slot?
12:10 to 12:45.
Great, awesome. Hey everyone, great to see you. What I'm going to talk about today is compute over data in 2023. So I want to focus on the impact that we can have next year. I'm going to talk about, kind of give a quick introduction to kind of at a larger macro scale, give a sense of a range of projects and kind of the moment that we're in now and what we're likely to see in Q1 and Q2. I want to talk about why there's very likely to be many different compute networks, and then how that breaks down into many different interconnecting projects. Then from there, I want to talk about some early applications that I suggest to you as good things to kind of get started with. And then I want to kind of articulate why we want to focus on having like strong early impact and how to build on that. And then I want to do some Q&A. So many of you have probably heard me say this already, but Web3 is not yet web scale by any means. When you think about the web and most of the applications that we use day to day, we're thinking about massive scale systems with trillions of transactions and so on. With massive scale of data and compute and so on. So Web3 is very far away from this kind of setting. At the same time, the benefits of Web3 computation, which is public verifiability and decentralized decision-making around systems, or building public utilities that anybody can leverage without having to trust human contracts in specific jurisdictions and so on, all of those benefits haven't yet come to computation. And because of this problem, Web3 is also kind of stuck in Web 2.5, where there's a lot of applications in Web3 that end up having to revert back to Web 2, because you can't actually have backends in kind of this Web3 setting. And I'll dig a little bit into why that's actually really hard in a bit. So when the Falcon project, this is kind of the broader plan of the project, where in step one, we're amassing a massive, large-scale decentralized storage network. We've mostly accomplished that. In step two, we're onboarding massive scale data from a ton of applications and systems and so on. And in step three, we want to bring computation to the data. So primarily today is going to be kind of about step three. But just to give you a flavor of the scale here, the network has amassed close to 17 exabytes globally with a ton of GPUs ready for computation, which is pretty awesome. So there's a massive scale network with GPUs there ready for your compute networks to deploy jobs to. And there's a ton of data that is being added where a lot of the users of this data want computation to be added into this. And because a lot of this data is public or kind of public commons type data, there's likely to be many more users of that data than the original parties that may have wanted this data backed up. So it's an environment ripe for compute over data systems. There's a lot of kind of on-ramps that are bringing different kinds of data. And this is driven by an economic component of Filecoin called Filecoin Plus that's kind of bringing a ton of data into the network. So this means that Filecoin is a great target for computer over data networks. Now, a bunch of the data sets that are being added, like I mentioned, have this kind of public data commons orientation, but in particular, the needs there around the traditional style data science pipelines. So this is not, you don't need kind of real-time computation, say, for something like a social network where you kind of send out a tweet or upload a video and you need like super fast, super responsive communication. You can actually lean on asynchronous, large-scale data pipelines and the traditional kind of data science type jobs, which is a perfect fit for where we are in computer over data. One other component that's going to arrive in kind of that is launching now and will get better throughout next year is retrieval. We want to get to kind of sub-second retrieval of all of the data on Filecoin. Now, you probably have heard a lot about FEM, and you will hear a lot more about it until it launches. This is going to enable a lot of these computer over data networks to be deployed into Filecoin. And I'm going to dive into this in a moment. So again, like the hardware is there, ready for computer over data. The data is there and growing with a lot of different kinds of users. And now what we need is to build the computational networks to be able to leverage that data and create that value for users. Now, if we do this right, then we can properly make Web3 web scale, and we can imbue the day-to-day applications that we use with public verifiability and the utility of Web3. So I'll make briefly the case about many networks. So there's a lot of different types of cryptographic primitives when it comes to verifiability and privacy. And when you're in the decentralized setting, you cannot trust the computer. You cannot trust the computer to actually do the job. You cannot trust the computer to not leak the data. And so verifiability and privacy become way harder than in the centralized cloud. Now, in reality, you can't actually trust the centralized cloud either, and that's part of the point. Except that the centralized cloud has been, so far, riding on this kind of brand game and contracts and so on, and that has mostly worked for a large set of applications. But it kind of breaks down when you enter different settings where computation is kind of important kind of on a national scale or where you want to build robust systems that can resist massive scale attacks and so on. So all of these, there's a lot of different approaches to achieve verifiability in this public setting or achieve privacy in this public setting, but all of those approaches have different trade-offs, have different characteristics in terms of performance, and sometimes conflict. You might lean on an approach towards verifiability, and that pushes you away from privacy. It makes certain kinds of privacy harder. Or you might push towards privacy, and that just makes it way harder to make it verifiable. So unfortunately, we have this very hard set of trade-offs for decentralized computation that makes it difficult to land on this. Now, how do we navigate this? Well, what's likely to happen is that this is going to yield many different projects that tackle these different spots in the design space and build different networks. Different technologies will appeal to different use cases. Those different use cases will mean different customers. Those different customers will require different branding. That different branding will mean that different groups and different projects will appeal to that set. So we're likely going to end up with many different networks that are doing computation in this decentralized setting. Now they're going to need to interop. They're going to need to be able to kind of work over data in the same kind of environment and so on. And if that's, if this kind of model is not convincing enough, then just look at the current cloud setting. Like already in these large-scale systems and large-scale brands, you end up with many different sub-products that do different kinds of computation and different kinds of processing and so on. So whether these kind of later down the road get sort of unified in kind of porcelain-style products at the top. It's a separate question. Either way, right now, for the next 2 to 3 years, we're very likely going to end up with many networks. And so the Filecoin network, because it has the large-scale data capacity and it has a bunch of the hardware already, is a really great target to be kind of like a home L1 for a lot of these decentralized compute networks. And even if it isn't kind of like the root of that network, even if it might be home somewhere else, say Ethereum or some other network, can still leverage all of the data on Filecoin and all the computation primitives of Filecoin. Cool. So in a sense, you can think of Kubernetes as the kind of like poster child of like scheduled computation in the decentralized cloud setting. Now there's many different approaches to this that have been tried over many decades, but this is kind of like roughly how things look. You have some cluster of machines, you add a program like a kubelet or a borglet or whatever. You coordinate these by talking to this kind of like master scheduler, and then users submit jobs to this scheduler. The scheduler then sends the job over to the worker node. The worker node processes the job, then submits the results back to the scheduler, and then things go back to the user. Now imagine kind of like replacing that scheduler. Instead of it being a specific machine, you can put that into a blockchain directly. You can run the scheduler in a blockchain, and you can maintain that in a smart contract. That's kind of one of the settings that you can explore. And if you need really high throughput scheduling because you expect millions or billions of jobs, don't worry, blockchains are scaling. There was a whole other summit last week right here talking about how you can now get blockchains to be able to scale, to be able to handle that kind of thing. But the point is that you can run a scheduler in that setting, and you don't have to treat that as an additional kind of single point of failure, and so on. Now, the Bacalao project is already doing a ton of this. I don't think there's yet a scheduler on chain and so on, but that's kind of likely to come in the future. But either way, whether you use a scheduler on chain or in a different node and so on, you have this really nice setting where you can kind of think of all of the computation and all of the data as addressed by CIDs, content addressed, which is a really key primitive, which, by the way, offers tons of benefits besides all the decentralization of the networks, right? Like being able to address your computation with hash linking, or being able to commit to the data and memoize computation, and all of that. You get all of that for free when you use hash linking in the way you express the compute jobs, in the way you express the data, in the way you do intermediate computations and so on. So kind of aside from all of the Web3 benefits, just that alone, being able to have a hash-linked oriented compute network is super, super, super valuable. And so that's where we can create a lot of utility. So now think of like being able to implement the things on the left, like these kind of Kubernetes, Lambda, Cloudflare workers type things, with some of the kind of primitives, and bring some of the primitives on the right, like things like verifiable computation, things like fully homomorphic encryption, and so on. This is where all of this stuff is headed in the long term. Now, it's not going to kind of land there in the short term because these things are pretty expensive. Fully homomorphic encryption is still very expensive, though you'll see that starting to arrive over time. Now, in order to kind of do this, there's a ton of work that we have to do in kind of the underlying plumbing that all of these decentralized networks, decentralized compute networks, are going to have to do. So things around kind of how do you architect the thing, how do you blend it with different programming languages, how do you kind of write libraries for all of those programming languages, how do you, like what VMs do you use, how do you encapsulate, what kind of program formats do you use, how do you compile all the things? How do you schedule the things? What are the scheduler? What are the features of the schedulers take? How do you monitor your system? How do you kind of extract information about the system in terms of what's going well, what's wrong? Like where is your pipeline stuck? How do you do I/O of the data? Like how do you have to specify the formats ahead of time? What kind of like ETL do you have to do to the data ahead of time before you can run your own code? And then kind of what does the UX look like for the people running the worker node? What does the UX look like for the developers that are trying to use this, or the end users, and so on? So there's an enormous amount of work that is involved with running any kind of decentralized compute network that everyone's going to have to do. So what are we doing? We're saying, great, a bunch of this stuff is common stuff that everyone can leverage, and so let's solve it together. And then that'll become a really great basis for being able to derive specific decentralized compute networks that tune for a specific use case. So think of that as being like a really good platform that everyone can just kind of use an open source project to then derive some more specific computational network, which then you tweak and tune. What you change the scheduler, you change the verification, you change the deployment pathway, you change the use cases, whatever might be specific to your case. But we can all collaborate on making the common parts really good. This is kind of like similar to kind of the IPFS and Filecoin kind of trade-off, where you can have a kind of fully open source like project that doesn't say anything about how you pay for the thing or where do you run it or where the context is, but has all of the tooling for how do you address data, how do you move data, how do you address the computation, all that kind of stuff. Cool. And now, so probably a lot of you will either be building applications on top of decentralized compute networks, or and want to leverage that utility, or potentially will be building decentralized compute networks yourself, and you will be building one of these networks and launching it and so on. So for that, I want to plug some resources for builders. There's a whole series of hackathons that can help give you kind of good opportunities for you to go and build this stuff. There's like micro grants that can help you get started. There's requests for startups that can kind of like spark new ideas for new business models that you might leverage. So all of this stuff is there. And then once you kind of start finding something significant and you start scaling it, there's things like accelerators and VC funding and network capital funding in our ecosystem that can be helpful to you. So strongly encourage kind of looking for these things. If you want more info about this, there's we gave a summit last week on Monday, the PL Summit, that kind of describes this stuff in detail. Great, so there's gonna be a bunch of networks and a bunch of users on top of them. Now let's talk about some of the projects that are ongoing right now. This is kind of the R&D pipeline with a lot of stuff going on and translating from research all the way into development and production and use. I mentioned before the Falcon project and the storage providers and so on. Think of kind of the life cycle of data moving in the network, where there's some clients that are kind of onboarding data into storage providers, and then they're retrieving it. That data gets indexed by a set of indexers to be able to look it up really quickly. But computation permeates the whole network. So in particular, you might have massive scale computation in the storage providers. So this is where you have data center level quality deployments with tons of GPUs and so on, and potentially dedicated hardware. Like we might start to see specific computational networks demand specific types of hardware that accelerate zero knowledge or accelerate fully homomorphic encryption, and you can deploy those in those kind of storage providers very close to the data, right? So you don't want to move the data. The data is enormous. You don't want to kind of move petabytes. That's very expensive. You want to move the computation and the hardware, which is way cheaper to move, to where the data is. So that's kind of like why we tend to say that Filecoin has gravity, or like data has gravity, where over time the data sort of accumulates into storage providers, and you want to move computation and the hardware to the data. Now, you might also want to run some computation in larger scale networks that are close to the edge. So think of like the Cloudflare worker setting, where you might have a very large network of kind of computers in ISPs or computers in homes and so on, where you have a ton of processing power, because by the way, like these phones, like a pretty powerful, and when they're plugged in at night, you could actually use them, or your laptop or your desktop machine and so on. You could use all of those nodes also for computation. You just need to kind of orchestrate them, and you have to figure out solve the UX problem to enable the users to use them. You have to think about like policy settings, where like what kind of computation can run where, what kind of resources are available. There's a bunch of hard problems about how to schedule this right, which by the way are again common to everybody. So let's sort of like solve them together. And that's where kind of Bacalhau and Station come in. So there's two projects here that are going to be extremely, extremely useful for everybody. So first off, Bacalhau is solving a ton of the problems for how do you create these kinds of networks, and how do you organize them, how do you build tooling to be able to ingest various kinds of data and so on, and how do you model the computation, how do you run it, and all that kind of stuff. Station is a project to be able to kind of build this kind of thing you install once, and you can run many jobs for many kinds of networks. So the kind of like UX of Station is that you download one program, you run it in your computer or in your server, or eventually later your phone and your browser, things like that. And then that kind of profiles your device. You set some policy about like what can or should be able to run there, or what kind of resource utilization you expect. And then Station kind of figures out like what is the best thing to run based on your profile, and can run many kinds of jobs for many kinds of networks. It could be running jobs for a CDN, it could be running jobs for a compute over data network, and so on. So think of like Station and Bacalhau being like really good fits. And then there are things like the Falcon virtual machine and the IPVM, the FVM and IPVM, that are going to be really useful as components in building these much more specific decentralized compute networks. So yeah, you've probably seen a lot about FVM. You heard about IPVM earlier this morning. Heard about Bacalhau. I don't know if you've heard about Lurk and Zama, but these are kind of the zero knowledge computation, or in Zama's case, fully homomorphic encryption. Cool, so think of like all of these projects sort of interconnecting to be able to give you this like really nice substrate where you can create specific kind of specialized decentralized compute networks, or where you can kind of, as a user, use these networks to kind of leverage the utility of the broad network. And you can think of different deployments, right? So your application might want to run large-scale computation in a data center setting because you're processing tons of computation, or you need kind of a ton of GPUs or something like that. You can lean on that set of users. Or you might want a very wide distribution of users around the world because you're doing something more interesting that involves networking. So you might need to use nodes in the spread out around the world and so on, and that's kind of like where the kind of virtual provider type setting helps. Or you might actually want to push some of the computation all the way to the user's machine. There are some kind of edge or kind of full local-oriented computation things where that becomes relevant. Cool. So let's talk about some early applications. So right away, there's a ton of different use cases in Web3 that require computation. Building good bridges to a bunch of the other networks will help a lot with that. So being able to kind of do a bunch of the compute-oriented jobs that all of these networks require, like that would be really great. It would be also awesome to shift a bunch of these systems from Web 2.5 fully into Web 3 because, again, a bunch of these things are kind of bottleneck for not being able to run because of verifiability or privacy reasons. I think video is going to be massive in 2023 and 2024. But, maybe it'll start kind of growing in 2023 and then it'll become massive in 24, 25. But this is where kind of things like transcoding, and this is a slide from LifePeer, which is a video pipeline processing network. And that's where think of all kinds of applications related to video that could be running. Remember that video is one of the largest use cases of computing and networking in the world. It's a huge fraction of the bandwidth used every year. It's a huge fraction of the storage. And so think of tons of processing involving video. And that's likely only going to increase. And it's going to get messier with AI, right? Because now AI can generate tons of video, so that's going to get fun. Yeah, all kinds of like media processing pipelines. I'll mention kind of decentralized science because this is a use case very near and dear to us. And it's kind of where IPFS came from and so on. DeSci is a movement to improve science using Web3 tech and tools. Think of everything related to open access papers and open access data, being able to store all the data together, being able to run computations on that data together, being able to have reproducible science where you can kind of understand exactly what the computation was that was done over the data to get the results. All of that is kind of accessible. You have containerized programs, you have like VMs and so on that you can run and reproduce all of the results and figures and so on. So being able to kind of imagine a lot of this tooling being used to improve science. So this is a great area for kind of like early applications. You can think of building kind of like a GitHub for science type of tooling. Like, I don't think we should be building a specific platform that is a GitHub for science. I think that's unlikely. For a lot of reasons, I don't think that's the right fit for science, but think of all of the primitives and components that might be involved in a GitHub for science. Think of all the analogs to versioning and addressing and pipelines like CI and all that kind of stuff. And in terms of reproducibility, this particular problem is pretty large. It sounds kind of, for everybody coming from computer science, it sounds kind of simple, like, oh, virtualization is kind of old news, 1970s, 1980s. Why is it so hard? In reality, it's pretty hard because people write programs in a bunch of programming languages that rely on kind of like the latest versions of things, rely on a lot of specific things about their computer at that particular moment in time. And so when you kind of take those programs and take that data, and you then kind of address them somewhere, and you try to run them again, something doesn't work. Something went wrong, like the program changed, the program like happened to have some inclusion into, for some reason, into something that was like linked by some location address that changed, and so everything is a mess. So this is where content addressing can help a ton. If you can content address all of the programs and all of the code involved in that thing, and you can kind of completely sandbox the thing to not make any kind of network accesses beyond anything that you content address, then you can end up with completely reproducible objects associated with science, where you have a paper, you want to run some computation to produce figures, or you want to run some computation to produce some cleanup of the data or whatever. You can do that by content addressing the whole thing. And so through this, then think of enhancing this kind of stuff with then kind of like all the notebook-style computation and large-scale jobs, large-scale pipelines, and so you can do massive-scale data science. I think that this is, I would strongly suggest like one of the main applications that this whole community in compute over data focuses on is this massive-scale data science because it tunes perfectly to the job type. So you want to be able to like compute over public data, public commons. In some cases, you want private data, but the privacy of the data is kind of different than, say, like live social network data or something like that. It leans on asynchronous data pipelines, which is what compute over data networks are going to do really well initially. It lends itself well to kind of these public identifiers like CIDs and so on. So kind of really focusing on this set of tools and set of use cases will help a ton. So I want to draw attention to this. And then the other one that I think is like really good low-hanging fruit, when you look at large-scale engineering efforts to build things like programming languages and browsers and so on, you end up with these massive-scale testing infrastructure that test the performance of these systems to enable thousands of people to contribute code to these large-scale open source projects. And this is another example where scheduling jobs would be perfect. So imagine being able to run massive scale CI across these compute over data networks where you can, some new version of Bacalhau comes out, some new version of IPFS comes out, some new version of whatever program you want, and you can run it in CI at a massive scale, way larger than whatever kind of the current CI systems give you. And what's better, you can test it in home settings. So you don't just test it in the cloud where you have like these very weird type of environments, very different from kind of home settings, but you can actually go and test it in people's home computers in real network conditions, test it in phones, test it in those kinds of environments. And so you can imagine being able to build kind of like a proper R&D test network that can properly get us like massive scale performance wins across all these systems. This is one of those cases of like you build a very high leverage product that enables you to then build much better other things, right? So if we build this kind of massive scale testing infrastructure first, then that will enable us to build all of the other use cases much easier. Because that'll just feed back on itself and improve all of the tooling and all of the components, because it'll right away tell you like what's working well, what's not working well, and so on. Highly recommend exploring, if you're interested in these use cases, highly recommend exploring the testing infrastructure of Chromium, Firefox, Rust, and Go. Those I think are some of the best ones that I've seen, and they're massive scale, especially Chromium. I haven't yet been able to find this page on the bottom right again, but it was in there somewhere. And as an example, they ran thousands of different benchmarks. For every single commit, they ran thousands of different benchmarks to show you whether or not like your particular change decreased or increased performance across tons of different platforms. And like that level of CI is what you need to make sure that like as a developer, you're improving the product and you're not accidentally breaking it or making it worse. So if we build that kind of system, which, think about Bacalhau, like this is perfect setting where, you recruit a network of hundreds of thousands or millions of computers across data centers, homes, a bunch of other places, and then you submit a new version of Bacalhau and so on. You then like test itself. You use Bacalhau to test Bacalhau. You deploy a new version to a bunch of these systems. You run some workloads. You test it, and then you kind of return the results. You produce all the profiling and so on. And lo and behold, like you have effectively built not only a thing that improves your product, but effectively is the same tooling that you need for this other use case around data science, right? Because a lot of this kind of profiling and reporting and so on is very similar to the massive scale data science. So these are like the two main use cases that I would kind of focus the whole community on. There's a bunch of other stuff like again like video and media and so on that will also be really valuable, but I think they won't be as valuable as these two. There's one around like CI, and let me see if I had it here. One of the other thing I'll mention is developer tooling. So think of all of the code on GitHub and containers and VMs and so on. Like all of that, all of those objects benefit tremendously from content addressing and need a lot of processing as well. So like we're talking about CI here for large scale testing. A sub-problem of that is just doing basic CI over a thing. So you can build a decentralized CI network today with something like this as well. Cool. So here I want to kind of just speak a little bit about focusing on delivering impact. So for these kinds of use cases, focus on the core users. What do they need? What do they need right now? What do they need in the next 1 or 2 quarters? And build those features. There's a ton of interest on these programs and systems and so on. And that interest, that demand comes with very specific requirements in terms of performance, requirements in terms of features, in terms of threat model, in terms of incentives, and so on. So let's tune what we're doing to solve those problems early, as opposed to kind of like maybe like shinier use cases that are maybe further down the road. Let's kind of focus on the demand that is here now. Deliver impact in those groups, for those groups kind of quarter over quarter, and so build our networks to, over time, kind of grow with those communities and keep bringing more and more communities into our network. Cool. I'm gonna, since time is short, I'll open for Q&A now, and I'll maybe take questions for 5 minutes, and that's it. Raise your hands if you have questions, and maybe there's a mic that can come around. Yep.
So hi, thank you for the talk. This is very interesting. My question is mostly focused on the challenges that on the research challenges that this compute over data exists. So I'm a PhD student. I'm working on computations in general in decentralized networks. And achieving this is, from my perspective, is very, very hard. There's a ton of different little challenges that you need to address to do this. And my question to you is, how do you see, or for you, what are the challenges in this environment that you see that need to be resolved, like first?
Yeah, I agree. So a lot of this stuff is really hard, and that doesn't mean that you can't do it. It just means it takes a while. All of what I'm talking about today is stuff that a lot of us have been thinking about since 2014, 2015, and we built a bunch of the tooling underlying that was needed. So we built IPFS, we built things like Filecoin, we built things like libpp, and now, in the last year, we've finally been able to get to the computation part. Now we're building that, and now we're sort of like ready for the scale. And just kind of like, big things have small beginnings. Look at the scale of the Filecoin network is in a year and a half, we went from, in 2 years, we went from 0 exabytes to 17 exabytes. An exabyte is a lot. It's a lot. So if you can put together an exabyte, like we can solve compute over data. Like this is coordinating thousands of people around the planet and a huge supply chain build out to enable this. It's a way harder problem than doing the software of scheduling and so on, right? So also very hard, but has been solved by many groups over the last 10, 15 years. It's a new setting. Decentralization definitely brings its own sets of challenges and so on, but it's like very, very solvable. This is not like you don't have to we're not trying to pitch scheduling compute over data in like the 70s when it was like first getting started. So solvable. In terms of I guess your question was kind of like what challenges do I see right now? It's this stuff. It's like kind of go through each one of these things and like make sure that you have good versions of these, and you use kind of like the latest and greatest stuff. So WASM is a pretty awesome setting. You can do a lot of the computation there. Not all of it. Some stuff you need like access to the local host OS, or you need access to the network. Maybe you can use WASI. Maybe WASI is not good enough yet. Maybe you have to like go and contribute to WASM in order to like get the interfaces to work right, to like so that you can use it. And then there's just a ton of like work that we have to do to kind of knock out all of these things. And then once you're done with this common part, then you have to do your specific network setting, right? You have to go and like if you're doing zero knowledge or fully homomorphic encryption, then you have to like do that. But by the way, I would say the optimistic settings are going to be way easier. So like just start there. Just start with optimistic computation, where you kind of the worker node kind of commits to the job, runs a computation, commits to the result, and then later you can sample that and rerun it and check it. And you can use staking systems based on that to get really good guarantees. Now it solves verifiability, but not quite privacy. Privacy is way harder. There you have to figure out like, yeah, we won't get into it, but the merging of like compute over data with incentives with crypto econ day and so on, like think of that being like a very strong theme next year as we kind of figure out how to run these things.
Yep. Hello again. So I'm very excited to see Bacalhau partnering with Boink and getting a lot of the Boink projects in, hopefully, to some more distributed systems. I'm curious about your perspectives on why we need blockchains when it comes to distributed computing, because a lot of the questions we get from researchers and people who do distributed computing on something like Boink is, okay, but why blockchain? Why not database? Or any of your perspectives here?
What is database?
Just referencing the old, why do you need a blockchain? Why can't you just use a database?
Yeah, I'm just like I'm asking like a fundamental computer science question. What is a database and what is a blockchain?
You tell me.
So a database is just a set of data with the ability to query it over time and mutate it over time with some strong guarantees. You want to build a log of the operations that you're doing, and so that you can kind of over time accumulate the set of operations that you're doing over the data, and you can then query the thing. Now it happened to yield a specific set of software components that we associate with the word database that doesn't give us public verifiability or doesn't give us public computation. It just kind of, it's a trusted private setting. Blockchains are a system of software that enables you to aggregate a bunch of data together and create a log of operations that are mutating that data that give you public verifiability and are tuned for the public setting. They're both the same kind of thing. They just come from different families of software development. And the point is, like, these are merging. These fairly soon you will see blockchains that are going to scale to trillions of transactions per second. And so and which will support SQL and will support like all kinds of these. Like the blockchain world kind of had to kind of backtrack a little bit from the trusted setting to arrive at this public setting. And now we're bringing all of the knowledge from distributed systems and databases and so on and programming languages to speed up blockchains. So the broader answer is like these private settings give you a ton of problems on the road. They just sort of like lure you into this false sense of security that you fall into, and that's what leads into like bad reproducibility for science. Things don't run later on. You can't have a commons. You can't compute together over the same data. Like if you're going to write a paper as a scientist, if you're going to write a paper, where are you going to address it? You're going to address it at like Elsevier. You're going to put your data into like some repository that's going to start paywalling people or like preventing access. Like, hey, that's bullshit. like be a better scientist. Like get your data out in a public setting. Put the data such that it's accessible by everybody in an open access way, and pick systems that are going to give you like super low cost, high scalability computation that's oriented with broader public access, right? So that's the broader answer.
Thank you.
Hi, you mentioned DeSci. I mean, you just mentioned it there. What do you think is like the quickest win, like the lowest hanging fruit that Web3 can offer DeSci that scientists will adopt and say, like, this is a great use case? Because I guess we have IP NFTs, but they haven't really been proven in court. And this, like, the data side of it seems like sort of the lowest hanging fruit. What do you think?
Yeah, so look, there's a lot of different projects in DeSci. Like, 1 second. So I'm not going to give a whole other talk, but like there's a talk that I gave recently that kind of goes over DeSci and so on. There's a ton of problems with academia and how science works today in academia. And I think like first and foremost, what DeSci can really help with, aside from all the computation stuff, is just funding. You have better funding structures that are much more kind of community-oriented and regenerative. And it might sound like, to a lot of people, it might sound crazy. But let me find this graph. It's like, yeah, so this is like the whole R&D spending of, say on the left side is like most nations in 2020, most nations that do large-scale R&D, and on the right is like the US's budget specifically in like 2020 dollars. So the graph on the right is not growing with the economy of the US. That is a serious problem. Like this is why things suck today. If we had kept growing the R&D budget in the US relative to the growth of the economy of the US, I need to get another graph that shows like GDP of the US mapped against this. In a sense, you can think of like the amount of money that we're spending in science as decreasing every year because we're not keeping up with the GDP growth. And so like that's a disaster. And then on the left side, the US is one of the largest spenders in R&D in the planet. So that's like even double disaster. Like not only is the US like decreasing its spending, it's one of the largest funders of science and R&D. So we have to like solve this funding problem, and turns out like blockchains give you the coordination primitives, and $70 billion a year is large, but it's not that large. If you have crypto networks that are hitting 1 trillion or 10 trillion in terms of value, you can start being able to afford funding of science and R&D at the scale of nation states. So that's kind of like the larger, kind of crazy long-term vision. So think of that as being relevant like 10 years from now or 15 years from now. But kind of like even before that, you already have a bunch of kind of smaller scale experimentation that can happen. Separate from that, there's this whole other stuff around just kind of like the reproducibility of the artifacts and so on. So you mentioned IP NFTs. Like I do think that those are like extremely good experiments to be able to change the way in which IP gets generated and gets funded, moves back in. You need to change the incentive structure of how we get kind of results in the market, and we bring back funding into funding R&D. And so things like this are really good experiments to try and do that. And then HyperSearch is another, I'll plug that. Then there's a whole other part around like just organizing people and organizing the work. So think of GitHub as being super, super valuable to all of science, but it's not even tuned for science. You can't even do the type of processing in GitHub that you would like to do at large scale kind of scientific type of computations. So being able to do that, that's a really good part for DeSci, where like you can start doing those kinds of operations. And then you can think of like, as you do all of this work, you can sort of like think of like structuring the credit attribution graph of all of the people working on this and so on, and that like that gives you, again, feeds back into funding and long-term rewards and so on. So yeah, like there's a lot to say here. Maybe the computation piece can help with how we do the science and how we make the science reproducible. Like just get to the point where like when you read a paper, you can get access to the paper, like you don't have to be paywalled. And when you see a figure or you see the data, you can click a link and get the data, and you can click another link and run the program in your computer or a compute network or whatever and reproduce it. Like it's that simple. Today, unfortunately, though the number of papers is growing exponentially, most of those like you can't check, and that's not what science is about. Science is about like really getting to being able, like taking no one's word for it and really being able to test all the things. And so getting to reproducible science alone would be a massive breakthrough for DeSci to do. Cool. I think that's a great, so one last question and then we'll close.
Cool. So clearly you guys have I've talked to people, you guys have put a lot of work into cybersecurity. I mean, so that's like code hardening and Dockerizing to protect the service providers, to protect the client. You have all of the verification things and the other stuff on the WASM triangle, which that's cool. Nice. Have you thought about the safety of others, as in, this looks like a giant botnet?
Yeah.
Have you thought about controls against that don't really just hand the key to people for censorship?
Yeah, it's a great point. So the internet is a huge botnet. So yeah, the one part here is you can use a lot of the sandboxing that we've already built into cloud systems and browsers. So the cloud and browsers both have had to build a bunch of this sandboxing in VMs to be able to like sandbox and program from like being able to access other co-located programs and so on, and sandboxing in terms of the networking to be able to rate limit, use, detect abuse, and shut it down. So the good news there is that it's not new ground. We just have to apply a lot of the techniques and solutions that have worked already. But that's a lot of work. So that isn't, I don't think that's a lot of that is done yet beyond kind of the basic sandboxing that you get out of things like WASM and things like V8 and like the VMs. But all of this kind of networking, sandboxing, and so on, like we should be learning from the browser, because the browser has a lot of really good defaults, and you can even use things like Electron. And B, we're going to have to blend cloud and browser type sandboxing, and that's a bunch of work. So cool. All right, thanks everyone. Great to see you.
1. All right, hello everyone. My name is Sergey. I'm a co-founder at Camus. So we're in the business of structured data and bringing structured data to Web3. And let me tell you what, I guess structured data is well understood, right? Not everything is an image, but what Web3 data means to us is the following. Starting from late 70s, the first SQL database was developed. Later, it took a very winding path through data warehouses. We then got MapReduce, transformed into data lake architectures, then pretty complex federated data architectures. But one thing didn't really change is that all of the structured data was really confined to the boundaries of one single organization, right? All of these enterprise data solutions are confining you to work only on the data that is coming from within your business. So what Web3 data means to us is breaking this boundary down. So basically migrating over to the space of decentralized data supply chains where data can freely travel between boundaries of multiple organizations, where you have micro-publishers like on the level of a single IoT device or a person supplying their personal data to the network. We have multilateral data contracts and data transformations, basically multiple parties engaging in really complex behaviors of exchanging data for mutual benefit. When we have decentralized analytics, being able to run your standard analytical workflows, but on the data that sits in completely different data sources. And ultimately leading to what we think is the holy grail is the collaboration on data, being able to collaboratively build these complex data supply chains. So this is gonna be a fairly technical, but very like sort of building up from fundamentals. I wanna show you what we think is the proper way to do structured data in Web3. And treat this talk as just as an invitation for further conversation about how we can standardize on all this stuff. So I'm going to start with logical data models, basically what we actually put in these databases, what form of data we want to be there. So I'm going to start really early, basically for like a lot of you probably took introduction to databases course in universities. So this is where I'm going to start because I think we get off track pretty much immediately from that point. Because in those courses, we mostly talk about non-temporal data models. So like this table of account balances, right? You have account 1 with a balance 200, account 2 with a balance 300. These are non-temporal models because they don't have a time component to them. They only store state and evolve through CRUD queries. So this is kind of a historical how it came to be because databases mostly evolved in the context of OLTP, right? You have your application with a bunch of clients in it, interacting with the application as an engine of your business rules, and these rules are being translated into state transitions and stored in a database. Kind of an unfortunate feature of this entire model is continuous history loss because you cannot tell what your data looked like before the last transaction. So the DB is non-temporal. Then comes analytics inevitably. Everyone encounters this, like you ship your app and suddenly you face questions. How can I tell how this app is actually performing? Like what's the retention of a user? What's the like weekly active users I have? To understand that, we need to be able to ask questions from our data, like what changed, when, and why. And analytics is a historical problem. It's a temporal problem. It needs history. So we have to reintroduce time somehow into our data models. And this tiny yellow box there is probably derailed data engineering for decades, just figuring out what needs to be inside of that weird little box. Because we're suddenly in a space where we lost temporality, but we need to reintroduce it. And we came up with a whole bunch of different methods to do this, and they were very impactful on both sides, on LTP and analytics sides. But I'm going to focus on two most prevalent ones right now. As first one is change data capture. So CDC is a very simple idea. Basically imagine putting a trigger on your database, and every time something changes, you immediately log it into some stream. So you have this type of CDC stream table where it says that account 1 at event time T1, there was first insert into this database. The data row was created. Then through series updates at T2, at T3, its state evolved, and now it's finally got to 200 balance. So it answers the questions of when and what. It doesn't, however, answer the question why, which is a very important question. Because CDC data is anemic, right? When you look here, you have inserts, updates. There's no such thing as insert and update in your account processing systems. There might be credit and debit, but there's no such thing as update. Like, what does that even mean? So it doesn't speak the language of your business. It puts you in a position of reconstructing why and what, which is often impossible because information loss already occurred. But very many people and many companies try and get stuck in these problems for decades. A very much superior model is event sourcing. So this is a software engineering term, but the key idea here is let's treat state as just a projection of event history. So if we have event log, this event log can speak the language of your business, having debits, credits, transfer, purchases, and then you can materialize the state on demand, and the state can be computed in variety of different ways. Like it can be a projection of account balances, but it can also be the amount of SKUs that were purchased in total, etc. So event sourcing plus CQRS model gives us this very nice path where we suddenly don't lose temporality anymore. Application stores their data in event store. You have projections that still compile it into the state for very efficient querying, but analytics can just source the data directly from an event store without any need of reconstructing anything because everything stays temporal throughout. So you might be wondering, why am I telling you this? Isn't this just like a blockchain type of model, right? And there's 2 points. I see too many Web3 projects still use CDC model as their starting point. And I believe this is just a time bomb because right now we're building applications on Web3, but inevitably we're gonna run into analytics. Like projects like Dune Analytics, they're already doing a lot of, giving you the tools to do analytics on blockchain data, but a lot of this data is still in the CDC format. You cannot figure out what happened or why something happened from the CDC. And a lot of smart contracts don't emit logs properly, so we still depend on some data about state changes of individual variables that often is not very useful or really hard to figure out why from this data. So I think even L1 developers can actually learn a lot of new things from event sourcing model, making events like a primary data on L1s. The second reason I'm telling you this is just to show that OLTP already loves event logs, right? OLTP is converging on these append-only ledgers that are super nice for us because they both can bring dynamic data, but also content addressable data. So on the right, I have here an image how this event log could be materialized in IPFS, ignoring the actual physical layouts. So we can just have a bunch of CIDs that just evolve one from another. So data is both content addressable and evolves over time. It's history preserving, which is great for accountability, verifiability, etc. So this is the logical model, how we now map this model to actual files or what's going on, like what are we even putting into our storage. So again, a lot of evolution over decades here, starting with monolithic databases that just handled all of the aspects for you, right? They bring some proprietary data formats. They maintain indexes as part of those formats or separately. They bring the querying, query scheduling, query execution models. So all in one solution, but it can only scale vertically. So once we reach the limits of the vertical scaling, we went to the database clusters, and suddenly you have petabytes of data in one database cluster in completely proprietary formats. And once you face the decision of you want to migrate to a different technology, you're stuck because your data is in this highly proprietary format and highly proprietary solution. So this led us to data lakes, which sometimes are described as deconstructed databases. So the key idea here is that let's separate the data and store the data basically in individual files. It can be CSV or JSON, what have you, and then just have a layer of compute on top of it. So some scheduler that can schedule data processing tasks on top of the data. So this allows you to run multiple such engines, like Some might be specialized on processing GIS data, some might be specialized on just pure analytical processing. So it gives you an ability to easily switch from one engine to another while your data stays mostly static. It's basically a data-centric design. The question here now, we kind of lost the indexing part, right? How do we make this actually perform well? So this is where big data formats come into play, like Parquet, we've seen in a demo today. They bring compactness to the data, and they also bring fast querying, because in formats like Apache Parquet, they're columnar, and they also have built-in indexes that allows you very easily to search through data. They're also very friendly to compute, because you can actually like memory map it into RAM, or even memory map it into GPU directly and immediately start running your computations without any transcoding going on. So technologies like Apache Arrow that specialize on this make compute really, really fast. A key property of them is also that is very relevant to us is that they're immutable, which is very interesting, I think. Because now we suddenly have these data lakes evolving by adding more Parquet files, right? This is another indication that all labs have event logs. And enterprise data is actually much closer to Web3 than you might think, because data lakes are already becoming these event ledgers. There are some solutions that are trying to bring CRUD to data lakes, but I think it's really a step back towards CDC model. So I think they're addressing immediate needs of their customers, but it's not really a very well thought out long-term solution. But really, I see that Web3 data can really be a continuation of this deconstructed database model. We don't really need a hard break here. We can already meet enterprises where they're at right now and start layering the properties of Web3 data that we want to see to enable these decentralized exchanges on top of the data that already exists in their data lakes, right? If you have big organizations storing their data in S3, they might be comfortable with it, and we should support it to allow them really easily expose their data without forcing them to copy all of their data into IPFS suddenly and maintain these two distinct copies of data. So there's a really big missing piece, like Web3 dataset shouldn't be just a bunch of Parquet files in IPFS. We need an ability to represent some higher level constructs like schema evolution, because if you have a data set that is long living, there's very likely that requirements will change, the data set is going to evolve. We also need compactions, like there's a lot of maintenance to these Parquet files that needs to happen. Partitioning needs to be accounted for as well. So we really need a metadata standard, and this is going to be essential for us achieving interoperability in Web3 space to get into the place where data lakes are already like where you can have multiple engines running on the same data. We need the same ability for Web3 data as well. So I think agreeing on a metadata standard should be our #1 priority. And enterprises, unfortunately, doesn't have a good answer there. There is no like really a good metadata standard as far as we can see. Before I get to the solution to this problem, I also want to touch on processing models. So once we have this giant Web3 database, what processing model should it have? And I'm not talking really about like what query language it uses. It's really like a minor detail, but rather how it executes these queries, right? And for a lot of you, it still might be confusing what I'm talking about here, because 99% of data processing right now is batch processing. So you might be only familiar with this model, right? When you use Excel, you're doing batch processing. When you're using most of the databases, like through SQL, SparkQL, any kind of query language, you're still doing batch processing. Same with Pandas and R frameworks like Hive, Impala, Presto. Everything is batch, surrounds us. The key property of batch is that it treats data as a bounded list of records. So when you execute a query, it goes to that list of data and it runs your query from start to finish, and only after that gives you the result. So to illustrate why batch is not enough, I want to give you an example. Like I mentioned, we have a data set of hospital admission records, and we want to calculate daily number of COVID-19 cases. You might imagine running this SQL for this purpose, right? We have a really simple select with group by date, and we're counting the number of cases per every single date. And let's since it's a batch, we're gonna just agree to execute this query every midnight. So to show you how batch performs in this scenario, I'm gonna use something called bitemporal diagrams. No need to panic here, it's really simple. So on x-axis, we have event time. So this is when event actually happened in real world time. So for example, one case of COVID was registered on midday on Thursday, right? System time is the time when this event actually made it into our database, into our system. So this diagonal that you're seeing here, it basically represents the ideal case. Whenever something in real world happens, we immediately know about it in our system. So in this idealized case, if we run this SQL on Thursday midnight, we count the number of events, we get 2. On Friday, we get 1, but also 2 because with batch, we constantly reprocess our old data. So this looks good so far. There's definitely like this inefficiency going on because we're recomputing the results over and over, but whatever, like it looks okay. It's workable. However, when you encounter the reality of data, you suddenly get a lot of interesting problems. Like your data can be late, it can be out of order, it can be lost and then backfilled several days after. It can be run and then corrected. And people often refer to these as like edge cases, but they're not really an edge case. Like this happens to data all the time. So in BC province of Canada, where I'm from, this is how COVID-19 dataset actually looks like. On Saturday and Sunday, we don't get any data entry because I guess that person who enters these records in the database just like sits at home on the weekends, so you don't get data on the weekend. There can be a later night shifts at the hospitals where data gets entered only on the next day, right? So data is delayed. If we start running batch processing on this type of data, on Thursday you immediately get an error. You get 1 instead of 2. On Friday you get 0. There's completely like wrong results for several days going on weekends. So there's 2 problems here. Like we're getting wrong results on dynamic data, but even bigger problem here is that we're actually rewriting history. Every time you ask batch, give me this computation over Saturday and Sunday, it potentially can give you completely different results, and it's not made explicit that it's doing that. So can this be fixed somehow, right? Well, maybe we can delay processing by 1 day, except on weekends. There we probably need 3 days. Oh, and there's probably statutory holidays. We don't have the statutory holiday in our data set yet. We don't know how it affects us. So this is a lot of cognitive load, and if you start accounting for all of these edge cases, you're definitely going to make a mistake in your SQL. And this is just for one data set. Like it's a really simple query touching one data set. Imagine if you need to join 2 data sets that are constantly out of sync of one another. It just becomes like such a more complex problem. So the reality of batch, how we see it, it relies on data completeness, which is not the case most of the time. It basically wants you to stop and wait for all the temporal problems of data to disappear before you start processing, and pushes all this complexity onto you. Like you need to figure out whether your data is complete or not. And this makes all this processing very manual. If you as a maintainer of this data pipeline walk away, basically the data stops flowing immediately. And this is what we saw with a lot of COVID-19 data projects, is as soon as funding dry up, or like the interest in the problem slightly goes down and suddenly you don't have thousands of volunteers working on this problem anymore, pretty much every COVID-19 data project died, which is really unfortunate. So when you're using batch, especially on dynamic data, you get non-reproducible result and correctness issues that undermine trust in data, trustworthiness of data. And it's also non-composable, right? You can imagine this arbitrary 24-hour interval working out within one company, but when you start trying to develop a proper data supply chain that goes through multiple actors, suddenly they have to coordinate on these intervals somehow. Like it's just unimaginable for you to actually build out something reasonable from this type of primitive. It's also inefficient, yeah, as I told, on recurrent tasks. So here enter the stream processing. This is a different model, and it treats all the data as an unbounded stream of events. So processing can actually run continuously and potentially forever. There is no such thing as done state. Results are emitted throughout the processing loop. It's very new, so like the third generation stream processing engines right now are represented only by Apache Spark, Flink, and differential data flow, which is also part of Materialize engine. So they're still actively evolving. This is how the stream processing framework would handle this complex case. It would basically emit one result per day. It would not reprocess the data, it just continuously follows. And this magic green line would somehow figure out that, okay, on Saturday and Sunday, we probably don't have full picture of the data yet. Therefore, we have to wait until like late Monday to actually emit some kind of result. And this magic green line is the cornerstone of stream processing. It's called the watermark. And it basically tells us so watermark at system time S and event time E tells us that with high probability, the system absorbed all the events prior to event time TE. So here, for example, on Saturday, with high probability, we observed all of the events from Saturday only later in the afternoon on Monday. So watermarks are really cool because they can be have multiple forms. They can be predictive, so based on observed delays of the system, right? It's a probabilistic model that your system can adapt to the latency of the events arriving. It can be manual, like we can just set a fixed offset and say that, yeah, 24-hour delay is good enough. But most realistic, I think, it can be set by a maintainer. So a person doing the data entry in a hospital can provide you this off-band data saying, I finished the data entry for these dates. You can now continue with your processing, and with high probability, your results can be consistent and correct. So I think stream processing is a super honest model that highlights that data processing is always a balancing act between correctness and latency, which I think is a really important concept to understand. Because what I see is there's a lot of sentiment going around saying that, well, batch is for static data and streaming is only for dynamic data. But I think it's a fallacy, because I see stream processing as a superset of batch. It's just a much more powerful and complete model that is useful for many types of data. And as we see, our data is becoming more dynamic. Like it started with financial data, stock market tickers. Now we have blockchains also as really highly dynamic data sources. We're moving into IoT proliferation and more of a smart cities use cases, where we're going to have millions of data sources, dynamic data sources that need to be processed. And even if, let's say, you do have static data set, right? It can be a data set of some, let's say, populations of Byzantine Empire cities. This data set still can be revised, right? There will be a scientist that is going to revise this data point. And now then it becomes a question of how many decisions have been made on top of this data set, how many other derivative data sets were created that take this as a ground truth. And really the difference between batch and streaming is who reacts to these revisions, whether it should be a human in case of a batch, and do we really trust humans to do all this, or it's just a machine that emits a correction. So to illustrate, in our case, if we realize that some big chunk of data was missing on Friday and we later backfilled it, stream processing is going to automatically emit an explicit correction. So it's not going to lie to you and say like, oh, on Friday it was actually 4, I was right all along. It's going to explicitly tell you, remember Friday, I said it was 1, but it actually should have been 4 because I later got the events that confirmed that. So yeah, once again, I think it's a really honest processing model. And the model that addresses temporal problems instead of ignoring them, and gives you the control of the latency versus correctness trade-off. It's also really autonomous. You can basically write this query and leave it running potentially forever, and it's still going to produce valuable data for you. And it's infinitely composable, right? You can easily imagine this stream processing pipeline consisting of multiple stages, operated by multiple people, different organizations. They don't have to really care about agreeing on some synchronized processing intervals or some scheduling, right? It can just take care of all these complex problems for us. So if you're, just a really interesting comparison, if you've been writing smart contracts for blockchain, you've essentially been doing some stream processing already. I think in blockchain case, it's a much simpler case because blockchains are consistent and linearizable, and most of the real world data just isn't. The temporal problems immediately show up themselves once you start doing off-chain data or even just cross-chain transactions between blockchains that might be out of sync with one another. So to solve this problem, we created Open Data Fabric. And ODF is just an open protocol spec for decentralized exchange and processing of data. So you can find it on GitHub. It's just a document that we want to collectively evolve as a community that specifies all these things that I talked about, like data model, logical and physical, metadata format for how to represent structured data and how it can evolve. Processing frameworks of how do we process data while maintaining verifiability, accountability, provenance, and also identity and ownership component of it. So I'm just, in the interest of time, gonna give you some highlights of ODF. So first highlight is that there is two kinds of data in the system. Explicitly, we separate between source and derivative data. So source data, you can think of it something generated by system or as a result of observation. Like let's say you have a temperature sensor. This type of data cannot be reconstructed if it's lost. If you lose your temperature data, there's nothing you can rewind and look at the data in the past. That means it has to be durably preserved. Derivative data, on the other part, which I think is actually majority of data in our society, it's created from other data as a source by some sort of aggregation or summaries, some sort of function. So this data can be easily reconstructed if it's lost, assuming that the function that was executed is actually deterministic and that we can still reach that source data that it was pulling from. So this is how logically Open Data Fabric looks like. So on the left-hand side, we have our data publishers publishing the source data. We basically put these ledger-like requirements on top of their data set. And what this gives us is it establishes a trust anchor. All the data that you get from this type of publishers can be reproduced. It can be proven that it actually came from this publisher, and you can use these ledgers to hold the publisher accountable for all the pieces of data that you started using from them. Next, all these blue data sets are the derivative data. So basically think of them as these streaming SQL queries that continuously run on some infrastructure, producing new data. And this is basically a giant ETL data pipeline that can span multiple organizations. Like each of these derivative data sets can be operated and maintained by a different person, different organization. You can see that our system effectively removes people from the hot path of data. So all these scientists, analysts, they're configuring the system through these queries, but they never actually shovel data from point A into point B. They never actually touch data manually. Everything goes through the queries. Everything is codified. This creates two nice effects. First of all, this whole thing can be really highly dynamic and responsive. So any piece of data incorporated into a publisher here, it can immediately, thanks to string processing, propagate through the entire network and be incorporated into this much more higher level derivative data set that some decision maker are gonna look at from their dashboard, or some automation like a smart contract can be using to fire some triggers or do some high level decision making. And second property is that you get provenance. So any piece of data that you consume as this decision maker, any data cell can be attributed to the ultimate data publisher who provided this data, and you can see which transformations were applied to form it into its shape that it exists right now. So all of this is achieved thanks to the temporal metadata. So metadata is a crucial point of our system because it's basically a passport of the data. It records where data is coming from, how it was transformed, all of the aspects of how data looks like right now. And metadata is also temporal. It's a ledger because, as I said, these data sets can be long-living. We need some ability to evolve them over time. So do query changes. If your derivative data set needs to be modified somehow, do the schema changes. So yeah, this picture shows how these metadata relate to one another. So in a root data set, you can have data edit events, schema changes, etc. And in derivative data set, you can react to the schema change, which is also going to be captured in metadata, or you can change a query to accommodate for some, let's say, new columns that have appeared in the data set. We explicitly target any storage, like literally any storage can be used to store these data sets, because like I said, if an enterprise company is already comfortable in using S3 and want to continue using S3 because they're like have their Apache Spark and a bunch of analytics already working on it, we provide a format that you can use to materialize these data sets in S3. Similarly, there's a content addressable layout where these dynamic data streams can be materialized in IPFS, which basically looks like this, like these green rhombuses are metadata blocks, and these blocks can refer to files containing the data, Parquet files, and also checkpoints that allow us to resume the computations of the stream processing from any point in time. We're also agnostic of processing engines. So there's a plugin system, and we can support basically any data processing framework. We want to be very open to the types of framework that can be used in our solution. We currently limit ourselves only to stream processing engines, and this is not a technical limitation. It's basically to prevent our users to shoot themselves in the leg with batch processing, mostly. So right now we're supporting Apache Flink and Apache Spark streaming subset of the Apache Spark. So an engine doesn't have to be modified in any significant way to run as a subset of ODF. All of these properties like verifiability, reproducibility are layered on top of it by this coordinator process. So there's a very simple interface that you have to implement, usually through an adapter on top of the framework. And yeah, you can plug it into the environment. So while ODF is a protocol, Camus is our product, which is our planet scale data pipeline solution. The key product right now is Camus CLI. We basically started building this from ground up and wanted to test our reproducibility, verifiability, and stream processing model within a simple tool that you can immediately use. So it brings you the simplicity of Git, but for data management. So you can already download it today, install it on your laptop, and build out a pretty complex enterprise-grade data pipeline. This data pipeline can be peer-to-peer, so you can like arrange a pipeline with your colleagues or teammates. And you get out of the box 100% verifiability, reproducibility, and automated provenance. So it's pretty cool, and it has a lot of like integrations like with Jupyter notebooks that allow you like really easily just explore these pipelines and navigate the data. So our goals for Camus is basically make publishing as simple as possible and enable collaboration on data on a scale that we currently see in open source software. Like this component of verifiable trust, we believe that is the key piece that is missing for us to collaborate on data, but also shifting from batch to these stream processing workflows, it allows people to just work with data much easier with a much more concise code. So basically, you can collaborate on data pipelines code very similarly to how you collaborate on any open source library, which is pretty cool. Our goal is to bring fidelity of stock market tickers to all significant data flows, right? Why is the market data is the only real-time data source that we mostly get on our phones, right? What about unemployment data, decarbonization, like all these really important data flows of our society? Why do they still like shake up the stock market whenever some statistic comes up? Like unemployment data continuously throws the market off, especially during the COVID times, because we simply don't get dynamic access to this data. That's the only reason. And we are decoupling ownership from storage and processing infrastructure. So finally, a party that processes the data can be completely separate from the party that is a stakeholder that is interested to run this data transformation or owns the data set that they're publishing. So I think a real measure of a good design is how many things you didn't think of and later discovered and was amazed by like, oh, this actually works in this use case too. So I wanted to highlight some cool synergies. Like first of all, this whole idea of convergence of data that I've been hinting on, right? We looked at the state data, how it evolved through CDC towards event sourcing. We looked at the event data, how it was evolving completely separately from these engines that were doing mostly like time series processing, but now combined into this stream processing framework, third generation stream processing that can handle both of these use cases. A lot of synergies there was also in like intermediate stages OLAP, like bitemporal data that was just too complex to grok when applied to batch processing. But with stream processing, it just makes so much sense. So I think like distributed ledgers are there as well. So I think we're really converging on something like I would personally call one true data. It's really starting to look very similar from all of the perspectives. We believe that this model can function very easily for on and off chain data in the same exact way. So blockchains are ledgers, right? And they already satisfy all the properties that we require ODF dataset to satisfy. So we can treat them as dynamic data streams. So using ODF with on-chain data, you basically can get zero copy processing. So some projects like Dune Analytics, for example, before they let you run some processing, they need to take blockchain, decode it, then put it in a huge database, index it, and only then they let you run queries. So this is not a very decentralized model because how many nodes on the network can handle these multi-petabyte data sets? It's going to be very few. So if you treat blockchain as a dynamic data source like dynamic stream, you can actually define your stream query and just say, I'm only interested in data from this smart contract, only in the change of this variable, and then you deploy this query immediately to the blockchain node, and it's going to stream this information to you. So this actually gives you like really low cost, near real-time data pipelines, but also with a trust anchor coming directly from a blockchain ledger. There's no copying of data into some database that you don't really know the provenance of, or it's not really verifiable. You can trace the provenance exactly to the individual blocks of a blockchain. So this allows you to very seamlessly enrich blockchain data with off-chain data sources because they're part of the same model. So another thing I have alluded to is that derivative data is basically a form of caching, right? If you can reconstruct the entire thing, you don't have to store reliably all the derivative data. So storing derivative data becomes just a trade-off of storage versus latency. And this is how we can achieve the massive scale of collaboration at really minimal infrastructure cost. We also can get codified governance because our metadata chain can be extended. Like I said, it supports schema changes, but it can also support these notifications about significant retractions and corrections. So our background in DSci, we're coming from that angle. And I think it's really important for you as a scientist, if you started consuming some data set, build out a lot of research, publish your research on top of this data, and then suddenly you get a significant retraction from the source that you will be notified, and it's going to prompt you like, hey, like the data set that you've been using for your project actually had some really significant changes, and you might want to revisit your project. So this really puts all of the complexity can be codified in this type of temporal metadata, which I think is really powerful. Like same goes for all the license management and stewardship information, semantic graph, etc. It's also really helpful for systematization, right? Right now, we're just failing to systematize data, like all the data volumes that David talked about in his talk. Right now, if you go to any major university's data sharing portal, they're just drowning in the amount of data sets. And I think it's mostly because of our data science workflows. They're encouraging excessive copying and versioning of data. Whenever you consume someone else's data set, you're encouraged to make a copy, upload it into this research hub just to enable reproducibility through versioning. And this creates a lot of noise because suddenly you get a bunch of copies spread everywhere. You get copies of the same data set. Like it's just madness. So I think with ODF, we can really shift the focus towards let's structure all of our workflows around the set of core dynamic data sets coming from governments, coming from research, and then entangle them into these higher level data pipelines. So you get both long-living data sets that are a lot more easier to systematize than a bunch of copies, and you also get very transparent pipelines, right? It's a lot more easier to contextualize data once you see that it's already a part of some pipeline, and like this data set produced by MRI machine in this hospital is being incorporated into this global data set of MRIs, etc. And finally, an interesting observation is the relationship between ODF and Oracle networks, right? With ODF, what we're doing, we're basically moving the trust anchor from API call level, like in Oracle networks, to the data publisher. So we're allowing you to achieve reproducible querying of the data and hold all the parties accountable. So not only the publisher, but also the collaborators, people who might have processed this data through multiple stages, and also hold accountable the infrastructure providers themselves. So I think this really puts a big question mark on the future of Oracle networks, if we can achieve this type of model, because I think the verification of these streams is a lot cheaper and more efficient model than establishing this trust anchor through the consensus per every individual API call, like on most major Oracle networks. So this is the conclusion, right? Web3 data doesn't have to be a clean break. I think we can easily meet the organizations where they are right now and basically structure Web3 data as a continuation of many decades long trends. I would recommend to avoid CDC unless you know what you're doing. It's really a stopgap in most of the projects. It's not really a long-term solution. And consider batch harmful by default. It's useful in a lot of contexts, but really stream processing can serve a lot of these queries in a much more safe way. I really believe that stream processing is basically an ongoing silent revolution in data processing that is going to make a lot of our workflows less manual and more automated. So ODF, this is an invitation for standardization, just for us to organize and start defining how structured data should actually look like in Web3, because I don't think we can afford further fragmenting the space, right? We want data to be interoperable between multiple compute solutions. So really, after all the talks today, like what I see ODF becoming is really this layer 2 network, compute over data network, based on top of FVM or perhaps based on top of higher level primitives of Bacalhau. We have a lot of work to do still, like SQL over blockchain was one of them. Other types of proofs of the verifiability proofs. Right now we're basing everything on reproducibility and determinism, but obviously it's not suitable for some use cases. So yeah, thank you very much, and I hope to hear your feedback. Questions, please? There first.
One of the slides you mentioned that 99% of the jobs are basically batch, and you mentioned towards the end that you think the future is streaming. How do you anticipate large companies or corporations that are mainly running batch jobs onboard themselves into this new streaming future?
It's going to be a slow and painful process because tooling is simply not there right now. Like I said, there's only 3 major stream processing engines, but I think really the pressure is on, like, a lot of data becoming more and more dynamic. And if your batch data processing pipelines continuously lies to you and actually produces non-consistent, incorrect data, the pressure is on the companies to do something about it. Also, Web3 is going to put a lot of pressure as well because, yeah, like I said, this simply is not a composable model, right? We need something that can be composed and layered on top of one another. There, please.
Have you looked into the Apache Iceberg project as a metadata solution for running compute over like Parquet files and data lakes?
Yeah, I've looked at the Apache Iceberg. It didn't immediately struck me as a fit because I don't think their metadata is temporal. I think it's more like a CDC, like basically CDC on top of the metadata, which is not something like what we want to achieve. We don't want diffs in our metadata. We want it to be basically also an event log that tells you how the stream is evolving, not saying like, oh, suddenly like the schema is completely different. How do you do that? We also want to enforce some really higher level rules on top of the metadata that, for example, does not allow you to create any kind of backwards incompatible changes to a stream, like dropping a column, for example, or like changing a data type of a column that would completely break your downstream consumers. So we're approaching the metadata design from the perspective, here's this long-living data set, and a bunch of people might have created data pipelines on top of this data set, and we want to minimize the impact of every change that you make as a publisher to these downstream pipelines to keep them going. Because if we start with any type of change, blowing up these pipelines and saying like, okay, this stream is over, here's the new stream, we're basically back to the batch model, non-composable model. So really, like with our approach to metadata, we want to encourage this long-living factor. And yeah, I am happy to be corrected wrong, and if the Apache Iceberg is a really right solution to that, I would love to hear about it, yeah.
Thank you.
Here.
Hi, thanks for the talk, that was great. You made a big caveat at the start about only thinking about structured data. Does sort of two-part question, does any of this kind of preclude semi-structured and unstructured data? And if yes, like what are the main challenges there?
Yeah, I was going to start my talk by defining structured data, but I was just, yeah, it's too much content for one talk. How I'm thinking about this, right, with all the cheese images in Web3, right, obviously image is closer to unstructured data than to structured one, right? Same goes for X-rays, MRI data, like there's a lot of, I would classify them as observations captured like over time or instantaneously, and these type of formats are mostly immutable. So you can think of them like how I represent them is kind of like a cell in this structured data set, right? And in our solution, we would simply link, like if you have a data set of images, you probably have some sort of metadata of what this image represents, where it was taken, some kind of geo coordinates associated with the image. So there's definitely a flow from unstructured to more structured, and we would like to use our solution to create these overarching data sets that describe the unstructured data stored probably directly in IPFS, and then just link to it, right? So a storage of images might evolve by just throwing more images into IPFS, but we still need some sort of overarching data set that tells you what these images are and how to find them, right? Like, why don't we have a data set that tells you about every MRI scan that was ever taken in the world? And this type of data set would be collaborative because there are so many data publishers producing this data. We need to bring all this data into one place to be able to discover it. And it would be highly dynamic because these type of data flows, yes, like one image once taken, it's static, but the data set of images being taken all over the world, it's constantly evolving. So this is kind of roughly how I draw the line between the two, is that metadata allows us to get a higher level concept of what is going on, and then you can drill down towards images or other unstructured data. Anyone else? No. There's one.
You mentioned Apache Iceberg. Are there any other projects in public, if you could wave a magic wand that ODF would partner with, or I don't know, any thoughts about like how to go forward with lots of other people since this is such a common problem?
Yeah, so really want to be inclusive of all the data processing engines. The more we can get, the better. From the other perspective, I would really love to partner with something like Bacalhau, basically a compute infrastructure. Also, from the earlier talks with Fission, right, like we need a common authentication authorization framework, which I think their solution would be perfect for this. So there's a lot of synergies going on, and we are explicitly want to minimize the amount of things that we reinvent, basically bring them to zero.
Again, that's fantastic. Sorry to follow up, but I've seen similar things, and again, I think everything here is great, but like open lineage or like you mentioned, Iceberg. They're just everyone's kind of taken a run at this before, and I wonder if there's someone to partner with. That's all.
Yeah, like lineage, I think, is not a good stopping point. Like, it's not enough to know that dataset A was produced from dataset B. We also want to know the transformation that was applied. We also, like, ideally, we are pushing towards fine-grained provenance. So being able to query, like, oh, here's this data cell. I find this value kind of suspicious. Can you tell me where this value is actually coming from? So these are the types that, like, it's probably a handful of projects that can actually drill down into the scale, but we really want to pursue that. So, and it's mostly enterprise solution that, yeah, they can give you provenance, but it's only in your, like, very constrained use case, which is not usable in Web3.
Okay. Yeah. Walid gets last question.
Thank you. Yeah, I just want to clarify one thing. You mentioned that batch is not accurate compared to stream processing, and I think the example that you mentioned is the utilization of watermarks, which is basically the distinction between the event time and the ingestion time or the arrival time.
Yeah.
But that approach is not unique to streaming. It's also possible, or that's the logic also can be applied on batch processing, where you define the point of where you are more confident about the data that you're receiving. And technically with batch, it's actually more achievable and easier to achieve more accurate data because you're capable of doing more deduplication by partitioning the data and achieving higher locality. So maybe I misunderstood something about how streaming is more accurate than batch.
I didn't really get the last part, how you can achieve these things through partitioning. My main point is that with batch, it's on you to decide when to run your computation and how far into the data you want to look at, right? So in this case, if we run data processing on Sunday, do we want to include Saturday and Sunday in this processing, or we have to know that, oh, there's actually was no data input happening on these days, therefore we need to delay and only reprocess data from Friday. So this right now is completely on you in a batch processing world. There's no mechanism that will tell you that maybe you should hold on for a little bit because your data is not complete yet. So this is why you get a lot of inconsistencies in data and correctness issues because you're kind of running ahead of your data, which is super important when you start joining streams together. Like, let's say you have a data set of your investment portfolio and you have a data set of the, like, stock market prices, right? And you want to figure out what's the value of your portfolio now. You might be refreshing your data set of the portfolio once a month. So for the duration of the entire month, if you approach it naively, you will get incorrect results because your original data set was lagging. So stream processing gives you this ability through watermarks to define how to know that your data set is lagging compared to another and delay the processing. Does that make sense?
Yeah, I mean, yeah, makes sense for the example that was given. Thank you.
Thanks.
Can we do it later? We're just already past 3 o'clock.
Happy to
So
catch
thank
up
you very
later.
much.
Thank you.
And Lavi and Jonathan.
There we go. Okay, incentives. First, who here before today had heard about Gridcoin? A couple people, okay. What about Boink, which before today was mentioned like 3 or 4 times today? What about SETI at home? Majority of people, okay. And I assume you all crunched, you worked on SETI at home, you did those work units, you were involved with the project in some way or another? Yeah, okay, so it was funded into Commons. There was a speaker, Kathy Mulligan. She mentioned that she thinks the space that we're working in right now is not working on a cryptocurrency level. We're not talking about currencies enough. We're doing tokenomics. And I think she is definitely onto something. The technology we're working on is basically economic networks. We're building our own nations with their own economic substrate. And it's built on open infrastructure. So we are the ones who can decide what we incentivize with the currencies we create, where we inject value, and how we inject value. So when we're working with CoD, I think it's important to realize that everyone has a computer, and we can just inject currency into the system in which we all operate by giving it to people who contributed to distributed computing. So I've got 7 brief lessons here that I've learned over the years. I'm from Gridcoin. It's a coin that launched in 2013. We've incentivized BOINC since then. BOINC stands for the Berkeley Open Infrastructure for Network Computing. It's been running since 2002, 2003-ish, and as we all know, Steady at Home is 1999-ish. So we have been doing this for quite a while, and basically what Gridcoin does is mint a currency and distribute it to people who contribute to these BOINC projects. And BOINC still runs. There's 30-some-odd projects running things from COVID vaccines to asteroid identification and mathematics, a bunch of whole different projects around the world. So when we think about incentivization, we have to think about the fact that when we incentivize something, we're going to get more of what we pay for and less of everything else. It's not just what we pay for. We're sacrificing something else. If I paid you to go get me a bottle of water right now, you would get out of your chair, so I'm incentivizing you both to get the bottle of water and to leave an empty chair. So when we incentivize people for distributed computing, how is that affecting the rest of the economic network? If we're only distributing currency that we're minting to distributed computing, what aren't we distributing currency to? What else could we be distributing currency to? Could we be using currency emissions to incentivize impactful science? Could we be using it to secure a blockchain? Anything like that. So it's important to keep in mind that CoD is only one aspect of these economic networks we're building. A second lesson over these years, incentivization does not need to be monetary. So the way that Gridcoin distributes its currency is we choose a subset of these BOINC projects. So there's like 30 to 40 BOINC projects. We choose about 20 of them to distribute our currency to. The way we choose them is through a network-wide vote, and we're a very, very large network. We have 5,000 staking nodes. We have probably 20,000 distributed contributors, computing contributors, and BOINC itself has 200,000 hosts or more, so there's a lot of potential there. So we ask all these people to have a conversation about what is good science, essentially. So it's a very weird conversation to have, but in this network, we have scientists themselves, we have just regular people, we have people who are Web3 enthusiasts, and all array of background. So we end up creating a system where we're determining impactful science, or what we would call impactful science, without giving anyone money. They're not being paid to run an IE, which has been talked about a lot this week and is a very cool idea. But they're still getting to the same outcome. We don't need to pay them to do that. We ask them to determine what is valuable to them, and by doing that, they choose things that will add value to the network rather than detract value from the network. So they're not going to choose something that's trying to hack email passwords. They're going to choose something that's trying to cure cancer. That's the hope, at least, and it's worked so far. So, again, incentives don't need to be directly monetary. All right, number 3, like I said, BOINC has 200,000 hosts. Gridcoin itself has 20,000 people contributing to the network. And all these other distributed computing projects, once they get going, people are going to want to contribute computation cycles to impactful research or any type of computation project, particularly if they're getting paid. So computer data has the potential to be kind of one of the next onboarding ramps to crypto, Web3, whatever you want to call it, even to science. Everyone here, from what I could tell, has done Steady at Home, and Steady at Home probably played a major role in what you're doing now. So we need to think about maybe UX and UI and how we can build these systems to help these new people come in to a large open community of distributed computing, choose what they want to research or what they want to contribute to, and then just seamlessly integrate into this new economic reality where we have dozens of open economic networks working in parallel to determine what we as a society think is valuable at any given moment in time. Again, CoD has the potential to bring 1 million people into the network fairly seamlessly. Lesson number 4, you get to define the values of your network with the incentives. So if Gridcoin, for example, only distributed currency to projects working on cancer marker research or something like that, that would be what we decide is valuable. That's the value of the network. If we distribute currency to both cancer marker research and math projects, finding large prime numbers, we determine those things are valuable. When you add everything that we're distributing currency to, you get the set of what the network thinks is valuable. It's a value set. You can distribute currency to essentially anything you want if you can figure out how the mechanism would work. There are easy ways to measure it. Distributed computing has challenges, but it's one of the easier ones because you can measure flops, cycles. You can distribute points that way. But you could reward the Olympics if you wanted. We could distribute currency to every gold medal winner in the Olympics from 1980 and on. And that would be part of our value set. It would be a very weird value set because it's cancer marker research, prime numbers, and Olympic sports. But it is anything you want to do. What you incentivize, where you distribute the currency, defines the values of the larger economic network in which you're working. So when we defined these incentive mechanisms for these projects that were just starting to get going, I think it's important that we sit down and write down what our value sets are, what we think is valuable as a network. Lesson number 5, make things dynamic. So we have in a very envelope mathy sort of formula for how much computation power each project Gridcoin incentivizes. It's basically 1 over n plus x. N is the number of projects in the network. So if you have 10 Gridcoin to distribute to distributed computing projects, and you distribute 10 GRC a day, which is currency, each project would get, if you have 10 flops to distribute to a computing project, and you have 10 projects, each project would essentially get 1 flop. That's a very basic way to think about it. And then the plus X is anything else we want to add to it. So we can change that. We can make some projects worth more, worth less, try to get more people to do that work, and get fewer people to do a different project. We can make more people want to become Olympic athletes if we add that to our value set. Or when you bring in non-monetary incentives, you might be able to do something like what COVID-19 did when it first started going around. And we had this smoothing curve where we try to get people to distribute computation cycles to all these different projects, but all of a sudden there is this non-monetary incentive to contribute to projects that are trying to map the spike protein and otherwise analyze COVID-19 so we can develop a vaccine. And everyone, for a very brief time, stopped worrying about money and started working on the COVID-19 projects. They went very well. They discovered they mapped the protein very quickly, and we are where we are now. So there's that X factor that can manipulate where the currency is distributed, and then there's the aspect of it that's non-monetary, where if you can make people think that another aspect of the distribution or of the system is more valuable than another, they'll go do that thing, regardless of whether or not they're getting paid. So that's make things dynamic. And number 6 is a fun one, make things free by default. What the hell does that mean? So when you're distributing these currencies, there are specific projects that seem to be fundamental to advancing society, scientific projects mostly. So if we are developing systems that are still pay to store and still pay to compute, how is that any different than the system we currently live in? They should be able to store these data sets that build everything after it basically for free. We should be able to compute on them for free. And it's not free because nothing is free. It's essentially subsidized by the economic network that we've created. So we're generating currency and we're distributing it to people who contribute to these specific tasks. Now, if you're working on a project that is going to be very profitable, that's a very translatable project or otherwise profitable, you should probably pay for compute, but it should be free by default. Any researcher, anyone who's building a foundational layer to society or the way economies work should probably not have to pay for it. They should just get access. I would love to see how that gets built, but I do think it's very possible. So number 7 here, when you do all these things, when you have an economic network that lets people decide what's valuable, what the value set of that economy is, and you make access to these resources essentially free, supported by the underlying economic layer, the central bank, if you will, that's minting the currency, you can develop an economy that's based on science. So if the science research is the value set, the scientific outcomes are what is injecting value into the system. If you have a ledger of scientific outcomes that are deemed valuable, if you store valuable data, that is what, this makes people want to interact with that data, with that ledger. People will want to use the currency to interact with the data because they have to pay transaction fees at the root of the technology. So you're injecting value right into the ledger by just making people do science. So that is pretty much all I've got for you. It's a very quick talk. I want to go back to one lesson, though, and that's how important this field, computer over data, is in terms of adoption. It's bringing people in from almost every field to do one thing, which is compute, which basically runs the world already and is probably going to become much more important over the next 20 years. You get people who are working on economics, you get people who are working on software development, you get people who are working on every layer of the stack at the same time, in the same room, talking to one another and trying to figure all this stuff out. It's very important to be open to these perspectives. And in Gridcoin alone, for example, we are a very old coin that really did not start with any pre-mine. There was no ICO. There was no money. And we've survived for almost 10 years at this point solely because people want to do this. They are very interested in making this work. They want science to be the base of economy. They don't want debt to be the base of economy. It doesn't make sense. We want to make the world a better place, and if in order to make money, I have to make the world a better place, that's awesome. That would be so great. Imagine every rich person right now, today, who instead of having to extract value from the system in order to become rich, had to produce scientific outcomes that made the standard of living for everyone around them better in order to get rich. They can still be as rich as they want, but the way they got there was to make everyone else's life better, to make more medicine, to make more faster cars or better, more efficient cars, anything like that. That would be a world that I think a lot of people want to live in, and Gridcoin is an example of why I believe that, because it just still exists. There's no reason this thing should exist anymore. It was a very bad set of code. It had very interesting and, let's say, poorly designed economic systems. And we're going to hear from Levy in a second, who has gone from Gridcoin to just contributing to Gridcoin to developing a very interesting model for how to incentivize distributed computing across many different platforms. Our developer is just a guy with a lot of time who's really, really smart. And he has a very serious job outside of Gridcoin. Our community just has families who are they just want to see this work. No one's paying them. It's insane. So, point being, an economy based on science is something that will bring thousands of people in here to build because it's something worth building, not because they're getting paid for it. And it's very inspiring to see all these projects that have been presenting today, and there's been almost no talk of tokens. There's no pay model. We're going to build this thing that's going to fix this problem, and we have this solution. It's very nice to see. So I hope that's the way the space keeps going. And with that, I don't know, anyone got any questions? There's not much to ask about, but all right, Levy's coming up.
Nice job. Ooh, there was a USB adapter here. Hold on a second. Is this going to work also? This was working a minute ago. 1 second. Ah, there we go. Okay, thank you. There we go. Okay. Hi, my name is Levy. As John said, I come from the Gridcoin community. And today I'm going to tell you about incentives in distributed computing. So, John mentioned that Gridcoin's incentive mechanism basically works by taking a pool of rewards, dividing it by the number of projects, and then handing it out proportionally to the people who compute those projects. In practice, what this does is it leads to very, very disparate rewards for crunching different projects. So for example, with the exact same set of hardware, you could get about 5 times as many rewards as you would another project, and that really depends on how many people are crunching that project. The question is, can we find a better way to do this? Can we find an axiomatic approach to defining block rewards or rewards more generally for this network? And really, what we're asking is, can you find an incentive-compatible allocation rule that doesn't pit a cruncher's preferences against what their hardware is best suited for? So basically, if you really, really believe that you really want to work on the cure for cancer, but your hardware is really best suited for some other project like mapping the Milky Way, your economic incentives are not aligned with your financial incentive, or rather, your financial incentives are not aligned with your personal beliefs. And in game theory, algorithmic game theory and mechanism design, you usually want to be able to align those. You want people to be able to express their honest opinions and you want to design truthful mechanisms, right? You want people to say, this is actually what I believe, this is actually what I want to have happen. This is pulled from David Anderson's paper. David Anderson was the founder of BOINC. BOINC has a credit system, and ideally it achieves the following properties. So it should be device neutral. So that means that similar jobs should get about the same rewards regardless of the host and computing resource on which they're processed. It should also be project neutral, and that means that a given device, any machine, should be able to get about the same amount of rewards regardless of which project it crunches. And the third is that it should resist cheating, right? So you shouldn't be able to cheat the reward mechanism. This is being pulled from, this is from a paper by Shi Chen, Christos Papadimitriou, and Tim Roughgarden on an axiomatic approach to block rewards. And basically, this is, of course, right here, this is your expected reward from every block in the Bitcoin network, right? So it's your hash rate divided by the hash rate of the whole network, and that's your expected payoff for every block. And this has a few very nice properties. It satisfies non-negativity, budget balance, symmetry, civil proofness, and collusion proofness. Those aren't really important for right now, but I think they demonstrated that the Bitcoin proportional allocation rule is the only rule that would satisfy those in this problem setting. And so in BOINC and in Gridcoin, we have a really highly heterogeneous computing environment, right? So we have tons of different types of computers. We have everything from mobile phones to Raspberry Pis and SBCs. We have different, obviously desktops and laptops, and we have AMD and NVIDIA GPUs. We have Intel and AMD and ARM CPUs, and we have that combined with many different operating systems, along with different BIOS settings, different motherboards, RAM. It goes on and on, right? So the space of hardware configurations is absolutely massive, and simultaneously, the computing environment, there's also a lot of heterogeneity in the computing tasks, right? So mapping the Milky Way versus trying to find the form of the spike protein on COVID versus doing simulations for the Large Hadron Collider, et cetera. There's just a really, really different, really, really mixed set of computational requirements that these projects have. And so the question is, can we find an analog to this proportional allocation rule in this heterogeneous setting? So this is the generalization, and for now, let's just consider tasks, computational tasks that require a CPU. This does generalize, but I'm trying to keep things simple. So the basic idea is to treat the entire network as one massive supercomputer, right? And so what you ask is, let's say that you take every CPU on the network and you focus it on project A. How many computational units are you going to get done in some amount of time, right? And then say you focus in on project B. How many computational units are you going to get in some amount of time? And then you basically set each of those equal to each other. So basically, this would take the form of, X units of computation type A are equal to Y units of computation type B, right? That's how you relate work units and tasks from different projects to each other. And equivalently, this is also like taking the average of all the computers on the network. It's the sum versus the average. Of course, it's just a scaling factor, so it's pretty much the same thing. So that's great. So now that we have a way to equate work units from different projects, we can construct a universal task, a universal work unit. And since we can compute any type of computation to units of this universal task, we can calculate the output of the whole network in terms of one number, right? In terms of this, in units of this universal task. And then to calculate the cruncher's rewards, we just take their output on whatever projects that they were crunching. And really, it's applications in BOINC, but I'm trying to keep things simple. And we divide it by the output of the whole network, right? So it's whatever you do in terms of this units of universal task divided by the same, whole output of the network in units of this universal task, and that's the proportional allocation rule, right? And so this is basically the same as the Bitcoin proportional allocation rule. And since we're starting with a heterogeneous set of tasks, this is actually a multidimensional generalization, right, of the Bitcoin proportional allocation rule, right? Because you can think of it like instead of having just SHA-256, we're now introducing different types of functions, ETH hash or whatever, just we have a large set of different types of computations, and we're kind of collating them all into one. We're trying to find a way to equate them with each other. So what kind of behavior does this reward mechanism incentivize? So in order to maximize rewards, crunchers should maximize their output in terms of the universal work unit, accounting for their energy consumption. So this has an interesting implication. And so crunchers may be incentivized to maximize their rewards, for example, by overclocking their hardware. Now, this may or may not be the case depending on how much your electricity costs, because if you're only getting a 10 or 20% gain on your by overclocking, but your electricity costs are what we tend to have in most of the world, this is not going to be. It probably won't be worth it. Basically, you'll probably end up losing money, but it might have that incentive. And also, that in particular might yield a lower task completion rate per unit of energy consumed, and it also should shift the burden of the carbon emissions from over the life of this hardware from the production of the hardware actually to the consumption and use of the hardware over its lifetime. And this can actually be leveraged to make better use of already existing hardware rather than the production and purchase of the newest hardware that we have. Also, it's also important to remember that while this is somewhat of an edge case, in general, the reward mechanism basically incentivizes using your hardware as best as possible relative to all of the other hardware on the network. In BOINC, I won't go into the details because it's complicated, but in BOINC, it's very difficult to gather the data necessary to actually compute that equivalence ratio, the way that we equate units of units from one project to another. And so we have to approximate it, right? And so there's two ways of doing this in the paper. One is using linear regression, and another one is constructing a hardware profiling database. The linear regression approach would take a bit too long to explain, although it is very interesting. If you're interested, you can read the paper. But the hardware profiling database, I think, would be of great interest to a lot of people in this audience. So it's really not that hard to construct a hardware profiling database, right? You just need a set of benchmarks that you compute on. You basically do that for every machine on the network. And then what you also want is an approximation. You would also want data on how that same machine performs on the actual tasks from these projects, right? And then it's as simple as just running a machine learning algorithm using like a nonlinear regressor or deep learning or whatever to basically map the hardware benchmarks to outputs on each of these projects one by one. And in that way, you can approximate what the entire network can do. And in fact, you can infer what any new type of hardware can do in the future. And this would be of immense use to many different groups of people, researchers, companies, other compute providers, people on the network who are interested in what if they really care about mapping the Milky Way, what's the best hardware to buy for their next setup. So anti-cheating mechanism, right? So how do we prevent cheating? So this is going to just be a really basic probability and game theory approach. It could be that ZK proofs and other methods might yield better approaches in the future. I don't know enough to say. But this is just a really, really basic analysis. So consider a single machine that's receiving a stream of tasks. And some of these tasks can be replicated and sent to other machines to double check the results, right? Because you generally want to have some kind of consensus on whether these results are accurate. But you also want to reduce the amount of replications of jobs because that's a massive waste, right? So you can just imagine a machine. It's the only one crunching each of these tasks, and then with some probability p, you're going to replicate that, and I'll get to that in the next slide. But basically, the approach is you have a reward pool for every task in the network. For every task that's being sent. And then basically you just divide that reward pool amongst all the crunchers who who did that task honestly, right? So if one person crunched it, then they get all of the rewards. If two people crunched it, each of them get half, and so on and so forth. And so clearly this incentivizes you to be the only person who's crunching this task, right? So you want to be honest and you want to be the only person crunching this. And so how does the anti-cheating mechanism work, right? So suppose that a task is replicated with probability p and has a total reward pool r. So if we can go back in time and check prior tasks that were completed, we can basically calculate the number of tasks necessary to go back and recompute the tasks such that it's not worth cheating, right? So for example, suppose this p is 5%, 0.05, and you basically, the chances of getting caught is going to be geometrically distributed, right? It's just, on every single task that you're being sent, there's a 5% chance of being sent a replicated copy, and that means that in expectation on the 20th task, you're going to get a replicated copy sent to someone else. And if you're cheating throughout all of those and you finally get caught, what basically happens is you can go back and look at the past. So this, if we could just do the 1 over p here, so that's 20. I'm going to ignore that -1. So this is 2 times 20, which is about 40. And basically, you can go back to the last 40 tasks, recompute them on another node because you think that this node is cheating, right? Because you didn't get the proper results that you thought you would. And then basically, if that node was being honest, then the equivalent of the 40 tasks where you get half the credit is the same as 20 tasks where you get all of the credit, and so it wouldn't have been worth to cheat to begin with. And then if we cannot go back and recompute tasks, then you can just use a deposit and you can slash the deposit. This is the equation. The math is in the paper. So finally, we can get to the original goal, right? So. Remember, the original goal was, well, I have all of these personal preferences, all of these personal beliefs about what types of computations I think are important, but my hardware might be better suited for other types of projects. And so, what can we do? So intuitively, if you have some hardware and you really like some project, but my hardware is better on your project, but your hardware is better on the project that I like, we should trade, right? Right, because we could both benefit by doing this, right? So because the amount of tasks we compute from each of those projects increases, our overall profit would increase as well relative to if we crunched what we believed. And so intuitively, you can kind of just virtually trade your hardware. And in the simple case of one cruncher owning one machine that can only crunch one application, this problem reduces to a very well-known problem called the housing market problem with endowments. And this is solved by an algorithm called top trading cycles, which is course selecting and strategy proof. Strategy proof, some of you might know it better by dominant strategy, incentive compatible, plus individual rationality. And individual rationality meaning that it makes sense for you to participate in this game, basically. And course selecting basically means that no coalition of agents has an incentive to deviate and form their own group away from this game, right? So, and that includes coalitions of size 1, which actually means individual rationality, and that also includes a coalition of the size of everyone on the network, which means that it's Pareto efficient. So course selecting also implies individual rationality and Pareto efficiency. Unfortunately, this actual problem is way more complicated than that because, of course, one cruncher can definitely own more than one machine, and of course, that one machine can crunch more than one application at a time. So The generalizations of this problem exist. But the general setting that I just described is an open problem. There's a really, really interesting approach in a paper that was published as a preprint published in the middle of last year that used parameterized linear equations to solve the problem. So basically the way this method, the top trading cycles method, basically the way it works is, you can think about like the two-person trade, but now imagine you have a bunch of people and, maybe we can just trade in a circle, right? And that's kind of how top trading cycles works, and then, it clears the people who traded and it continues the algorithm. In the parameterized linear equations approach, they kind of drop this idea entirely, and so it actually enables a much larger generalization than this kind of older method. So environmental assessment. So basing the reward mechanism on the equivalence ratio incentivizes using hardware on the application on which it's most efficient relative to the rest of the network. However, like I said earlier, depending on the electricity costs, they may not incentivize achieving the highest task output per energy input. So you could, again, think about overclocking. And again, it really depends on how much energy you're consuming. So the anti-cheating mechanism obviously reduces the number of replicated tasks, and that reduces the energy consumption per task completed. The virtual hardware trading reduces the energy consumption per task as well, right? Because when you're trading hardware and you're using more efficient hardware, clearly, you're going to use less energy in computing those tasks. So regarding carbon neutrality, so you can recover waste heat, and we should be doing that. Unfortunately, you're not really going to get better than heat pumps. That's just physics. Basically, the question is, does the social benefit of having a massive decentralized supercomputer outweigh the environmental costs? And I would argue that they do well, we don't have time for that, but if you want to come talk about it later, I would definitely argue that it does, especially if we're recovering the waste heat and we're not having all this massive computational power, concentrated in a few large companies and governments. And also, additionally, you can directly incentivize projects that are environmentally focused, like climate prediction and maybe something in material science for better batteries or solar panels or whatever. And you can avoid curtailment by using excess energy to crunch. So curtailment is when you have somewhat of an overproduction of energy from renewable energy sources, and sometimes you kind of just have to throw it away. Well, actually, you can use it here. You can use it and not waste it. And you can also direct minted currency towards the sustainability project. So you can use the actual network, either individually or you can use the actual network to direct some of the currency towards sustainability. So this is the title of the paper, Incentivizing Energy Efficiency and Carbon Neutrality in Distributed Computing via Cryptocurrency Mechanism Design. I might change that title if you're watching this in the future. I hope you're well. You can just look up my name on Google Scholar and you will probably find this paper. These are the two references, the two papers I cited, and I really want to thank the Gridcoin community because it's really just such an open community full of welcoming people who are always ready to help. In particular, I just wanted to thank two people quickly. So one of them is Jim Owens, who is the lead developer for Gridcoin. I've had many conversations with him over the years, and he's been incredibly, incredibly helpful in thinking about a lot of these problems. And I also wanted to thank user Scribble Maniac on Discord for pointing out a problem in my algorithm, a flaw actually that I addressed in this presentation, and so that was very useful. So yeah, thank you. Any questions? All right, awesome. Got off easy.
Okay, so do we have a break now? Anyone in the back, do we have a break? No? Yes? Okay. All right, so we're going to take a break. I want to plant in your mind a reminder. Tomorrow is our brainstorming session. Again, where is it? Not here. Where is it? Thank you. Hyatt Regency. Not here. Do not come here. Very hard for people to rationalize that. Yeah, anywhere not here. So the rest of the world, right? It's therefore a set. It's a complete set. But the day is supposed to be an unconference, right? So it really is supposed to be around a variety of things that we care about, right? We are a community around compute over data. I don't even know where I should push. I think we have it out there publicly, the list that it currently exists. There is a Google Sheet
I don't know, for lack of a better place, we'll post it to the Computer for Data Working Group channel, the Google Sheet. Go look at it. Please think about what you would like to talk about. Now, that said, there's going to be a slight change of schedule for tomorrow. I will remind everyone at the end of the day. We are not getting here at 8:30. Whoever thought that was a good idea? Terrible. Terrible idea. And not here. Where are we going? Hyatt Region. Thank you. So we will not get there at 8:30. We are going to get there at 9. It will be a relaxed, hour-long, have some breakfast, have some coffee, tea if you're from the UK. Enjoy. We will have whiteboards up. We will have these sessions as they currently are laid out on those boards. And then you come along, vote on them, say, oh, I'd actually like to combine this and this, whatever. It's supposed to be dynamic. Just bring your good ideas tomorrow morning, and then at 10 a.m., we will decide the day. Okay? Questions? Okay. Go have coffee or tea.
That's okay. Yes.
Yeah.
That's okay. Yeah.
Okay. Yeah, I think I'm on here. So thanks everybody for the hookup. And if anybody is interesting, please do come join us. I'm here to talk to you about Charity Engine. I thought by way of context that I'd start by giving you an overview of our platform, what it is, and then talk about a few use cases we've done with clients and partners, and in particular with a focus on telling the story of the evolution of our platform, how each of the use cases led us to develop new and generally useful functionality. So to the first point, by way of an overview of our service, we describe Charity Engine as a crowdsourced cloud service. We harness volunteered computing capacity for commercial use, and we share the revenues with charities. So we donate our revenues to Oxfam Care. We've made donations to Clean Water Fund, to UNICEF, a range of really good causes. And we also donate a percentage of our compute capacity to scientific research. So towards that end, as of a couple of days ago, we'd considerably exceeded a billion CPU hours, core hours, to scientific and medical research. The network is currently comprised of about 1 million CPU cores, 100,000 GPUs. We have about 2 petabytes of storage, which in the Filecoin context is not a lot, but our storage is quite performant in a way that I'll describe later. We provision our resources in standard instance types to make it easier for people to grok what we do, to make it look like a traditional cloud service. Also makes it easier for people to make budget decisions on whether the economics of using our platform are favorable compared to a current cloud service, which they most certainly are. You can run your software in any Docker container, subject to the specs of the instance types that we have available. So that means you can get your Docker Hub, any container from Docker Hub. Container could be on IPFS, or it can just be a container that a customer has developed for themselves. We have an app store, which is to say that we have methods to secure proprietary software and to make that available on the network on a pay-per-hour basis. Our first publishing partner is Wolfram Research, so that means that you can use Wolfram Engine and Mathematica on a pay-for-the-hour basis. So you pay for your runtime, and then you pay a premium for the software. Using the system is made easier by a number of standard interfaces we provide. We have an API for programmatic interface interaction. So for instance, you're building a service of some sort and you need a batch computing backend. You can use our API. We have a CLI, so you can just run stuff from the command line and use familiar tools like new parallel, things like that. So it can be like having 1 million CPUs right there on your desktop. We have a nice web UI if you're so inclined. The web UI also allows you to track and manage your jobs in various ways, regardless of the interface that you use to submit the job. We have a smart contract interface that allows you to provision and use compute resources and storage through a smart contract. We developed that initially in Ethereum, and as was discussed earlier, we're hoping we can bring that to the Filecoin world as well, since the Filecoin virtual machine is Ethereum compatible. that means you can build things like smart oracles and other kinds of computationally intensive ways of basically bridging the gap between blockchain, in this case Filecoin data, and the rest of the world, particularly, as I said, where those there might be some compute that you need to insert in the middle. I mentioned Wolfram language as being an application that you can use on our platform, but we have a nice integration with them where you can access our compute resources directly from within Wolfram language. So if you're inside the Wolfram notebook, it's just a line of code to send your work out to process on the Charity Engine network. And we support BOINC. So we've donated hundreds of millions of core hours to more than 25 BOINC projects as part of our commitment to dedicate a portion of our resources to scientific and medical research. Behind all this now is a marketplace so that we can integrate, in addition to the volunteered resources, GPUs and CPUs in data center environments, storage, software, and data. Some key features just to give you a sense of what it is that the platform does. Critically, it's more than just raw resources out there. There's a quite rich scheduling function such that you just point to your input files and your application container, and provisioning and scheduling are handled automatically. So you focus on your work. You don't have to really think about infrastructure. You just say, here's my stuff, here's my container, and let me know when it's done. The scheduler is fault tolerant. If one of the nodes goes offline partway through, the job will get dispatched and rerun somewhere else. There's a number of validation options for you to get confidence in the results for deterministic computations in any event. Critically, and really the reason why we're here, is that the scheduler allows you to send computations to the data instead of vice versa to compute on the data in place, which I guess is clear to this audience is really essential for distributed data storage. Data, as now a few people have said, has gravity. You really don't want to move it. So towards that end, we've got now a Filecoin integration so that our clients installed on Filecoin nodes can read and write IPFS and Filecoin data and can compute on that data right in place. We also, the scheduler can ensure that computations get sent to appropriate resources. There's a number of parameters you can use for targeting, most notably GPU. Does it have the right kind of GPU? Does it have enough memory? Is there enough storage available? These kinds of things. And finally, the client installed in a data center environment in particular has two modes it can run in. One is a task mode, where as a provider you can be polling the marketplace to see if there's jobs that have compensation that's of interest to you, and pull them down, run them, and then shut down the client. And the other is just let the client run in the background and make use of resources when they aren't being used for other purposes. And the goal here is to give different ways to optimize use of your hardware and your infrastructure. So when there aren't jobs in the marketplace or of your own, you can also, particularly if you're running in service mode, backfill. We have a automated multi-coin mining system, so if you don't have jobs running, you can do currency mining, or you can donate your compute time to scientific and medical research, for which there's abundant need. As a demo, we did a demo at a recent Compute Over Data workshop a few weeks ago. So rather than rerun the demo now, if somebody wants to see computing on Filecoin in action using our CLI, the URL is here. This QR code, if you snap a picture, will send you right to that demo. This will be up again at the end of the talk if anybody missed it. So now some use cases. First is in the realm of mathematics. These are all things, as I mentioned, that we've done in the past couple years with partners and clients. So the first mathematics use case, or a mathematics use case for discussion here is some people who were working on a problem called the sum of three cubes. Was a math challenge posted in 1954 about whether the numbers between 0 and 100 could be represented in this form as, well, the sum of three cubes. As of 2019, which is 65 years later, all the values under 100 had been solved except for 42 and 33. In the spring of that year, Andrew Booker, a mathematician from Bristol University, solved 33 using a supercomputer at his university. And he had some ideas about how to do 42, but it was going to require an order of magnitude more compute capacity than 33, and the supercomputer people just said that they couldn't do that. And that's where we entered the picture. So the challenges for this particular problem were that we, in the end, had to deliver 35 million CPU core hours, which we did in about 3 months. On the infrastructure side, this was the first time that we used our custom scheduler at that kind of scale. It was the first use of the CLI, although in this case, in-house, it was us using the CLI to run the jobs on Andrew's behalf. But it was the first example, and the subsequent examples I'll show, of the eat-your-own-dog-food approach to platform development. So we built these tools because we had a problem, and these were the things that were needed to do this kind of work. And as I mentioned, after a couple months, 3 months, we cracked the problem. You can get a sense from the length of the strings of X, Y, and Z here, the size of the search space, which was considerable. As it happens, we let it running a little while longer. We came up with another solution to the number 3, which for mathematicians, for reasons that are above my pay grade, was of interest, and 3 other numbers under 1,000, which are listed here. We got some quite nice press coverage about that. We got an article in Scientific American, and there's only a few here shown, but a number of the articles picked up on the association with the Hitchhiker's Guide to the Galaxy, which many of you might know about. It was amusing because we really did solve this question with a planetary supercomputer, as Douglas Adams had imagined. Second use case is in the area of genomics. We were working with a consortium of academic researchers who had a large data set of sequence data from 78,000 biological samples. They didn't quite know what was in there, and the challenge was to search computationally these data sets for 10,400 fungal species to make an index so that this data set would be much more useful in the future. As an aside, searching sequence data is fairly compute intensive, as is roughly shown in the illustration. They're, on the one hand, just strings of letters that represent sequences of amino acids, but the challenge is that these searches are almost never precise, and so it's various kinds of fuzzy matching and alignment and so on. So it takes a fair bit of compute to search and to compare genomics data. So in this particular case of searching this set that we had to work with, we had 40 terabytes of data, which we stored with 3 times redundancy. We distributed it, though, across 375,000 devices because we needed a very high ratio of compute to storage, basically 1 CPU for every slightly more than 100 gigabytes of data. And that's, again, because it's compute intensive, and we wanted this to be performant and scalable. At one point, just as an aside, when we were pushing the data from from a data center in Lithuania out to the edge nodes, we found we were 1/10% of all the internet traffic in the country of Lithuania. And we can't really decide if that's like a lot or a little, but we thought it was really cool, and we were excited about it, even if it's a small thing. By way of challenges, this was our first project that was both compute intensive, as the 3 Cubes project was, but also data intensive, as you can see in the left column. This was also the first project that required us to develop scheduling to be able to send computations to nodes hosting particular data. it required us to manage the data redundancy such that if data disappeared from one host, it would, in an automatic way, get reproduced on a new host to make sure we always had 3 copies, so for reliability and performance. We also developed a nice Jupyter notebook where when you did a search against this data, you could subsequently work with it in a Jupyter notebook. And so what the researchers were doing is they'd pull down this index data and then query other third-party data sources to add metadata to what they were pulling out. And at the end of the day, we found well, almost 8 million fungi in that data set. As an aside, most of this work was done at a workshop, so it was set up. So almost all that searching was done in a day. A related project that's come up more recently, which we're very excited about, that uses much of the infrastructure we built from this, is a biosurveillance service we're building for the CDC, the Center for Disease Control. So we get sequence data from environmental samples on a daily basis, and we have to search all the new submissions on a daily basis for a list of pathogens of concern as provided by the CDC. And so there's a nice web portal, there's also a notification service, and the good news was that we had been running this for a while and nothing ever happened, but just a few days ago we found our first detection, which on the one hand is of concern, on the other hand validates that maybe there'll be some utility in what we're doing here. So third use case is biosimulation. And in particular, this is in the context of a spin-out of Grid Republic called FindBio, which is doing drug discovery. Although one could reasonably say it's the other way around, because I got into this whole world for the purpose of doing drug discovery. And we had to build a platform first so that we could do something useful. So in this particular case, our problem is we start with data sets of molecules which produce observed biological effects. And what our goal is to discover the mechanism of action. So you might, for instance, have a list of compounds that are known to be toxic to a malaria parasite, but you don't know how they work, and so you can't make drugs out of them because you can't optimize them if you don't know how they work. So we want to be able to discover the mechanism of action basically with no prior knowledge about the compounds, which we call reverse engineering biology. You go from observation to mechanism. We emphasize the need to do this with no prior knowledge because it turns out that there's actually a vanishingly small amount of biological knowledge in the world. If you look at this chart, you'll see, that about 90% of pharmaceutical research is focused on less than 10% of genes. In the bottom left, the similar ratio applies to proteins. In the bottom right, not surprisingly, this applies through to the commercial world to patents. It's a little bit different there, but maybe 85% of patents focus on less than 15% of human biology. And what's been fascinating to me is that though the number of papers over the last decades has exploded, this pattern has mostly not changed. You have more and more people writing more and more papers about the same thing. So if you want to make discoveries, a lot of them are going to be in that uncharacterized spot. And so what that means is, or our approach to this is, well, biosimulation. You have to be able to work from first principles to find solutions because you can't build off prior knowledge. So in FindBio, we basically do massive simulations of small molecules and all the proteins in a cell or an organism, proteins being the building blocks of cells or organisms. So this requires a multi-step pipeline with basically 4 different scientific applications, each of which have different resource requirements. And we start with large sets of raw data, but each step produces data which become inputs to the downstream sets. Also, we cache data along the way for rerunning steps of the process with, let's say, new model parameters and things like that. So in terms of the platform requirements, when we are working actively, we're running about 1 million jobs a day, about 160,000 core hours a day. And the goal I sometimes describe as near interactive supercomputing, but on a distributed computing network. And I say that because originally, when we started the project on our computer grid, we thought the big advantage of having a computer grid like this was that we'd be able to, in a production way, run really large data sets. And while that's true, it turned out that the real value to having it was in software development, because developing these kinds of software pipelines is very iterative, and the ability for us to take a reasonably diverse data set, and in biology, reasonably diverse means big, and to be able to run overnight huge amounts instead of having to wait 2 weeks meant that we could iterate and improve our software at a rate that greatly exceeded what even a big pharma company would be able to do. So in terms of challenges, this was the first time that somebody who was not a developer of Charity Engine using the CLI, we had to optimize the scheduler to make it more effectively meet daily deadlines. This was the first use of our container service at scale. As I mentioned, it's the first case of multi-application workflows where we had to take outputs from one set of applications, flow them into inputs. We had to cache data for reuse and so on. Because the scientific applications all had different resource profiles, we had to be able to target particular jobs to particular devices within our network that would support those needs. And of course, compute to data. We never wanted to move data around. We always wanted to run jobs where we had cached the data or where the outputs from previous jobs had ended up. So in a whirlwind summary in terms of output, on the left, without getting into it, is a set of experiments. There's a large number of molecules and a large number of proteins, and the blue boxes show what interacts with what. The middle box is what you get when you use the existing state-of-the-art of molecular docking software, in this case, Autodoc Vena. Well, it's not quite state-of-the-art, but it's widely used and quite reasonable performer. And you see it doesn't work at all because it doesn't work in basically when you have a small chemical space and when you have a large set of proteins. And on the right, you see the performance we were getting from our engine. Now, usually I show this in the context of talking about the science of that project. But in this context, what I mean to show is that distributed computing really works, and that computing on a distributed network can help you address problems that are really intractable in other ways. And finally, in this particular case, distributed computing was an invaluable asset in developing a software because it just amplified the capabilities as compared to what we would have been able to get our hands on and afford in a traditional cloud service. So that's sort of the whirlwind tour of Charity Engine. By way of sort of call to action, if there's people out there who have projects in need of compute resources, please do get in touch. My email is right here. If you have compute resources because you're a Filecoin service provider or a data center or something like that, we'd love to add our particular brand of compute as a way to get more out of the resources that you have. If you want to see a demo of the service at work, again, this is the link in the QR code to see what it looks like to install it and to use it. And that, I guess, wraps it up. If there's any questions, I'd be glad to answer them, or I'll be around for the next day and a half or so. Thanks. Thank you.
All right, can y'all hear me? Cool. Okay, everyone. Today I will be talking about building on Backley How for better Web3 data. But first, who am I and what is Spice? So I'm Philip. I'm the co-founder and CTO of Spice AI. Prior to founding Spice, I spent almost a decade working for Microsoft/GitHub, working on some of the large kind of infrastructure projects that they have there, including the ones you see here. So I have some experience building for developers and also some experience building kind of large infrastructure projects. And Spice is an early stage startup, as well as a Protocol Labs portfolio company. We're actually members of the Compute Over Data working group. My co-founder, Luke, actually gave a presentation at, I think it was the 6th community call for the Compute Over Data working group. So if you're interested in what you see here, you can go and deep dive into that and learn more about our platform. And at Spice, our mission is to make building data and AI-driven apps easy. We launched the preview of our data platform, Spice.xyz, in April of this year, which is our data and AI infrastructure platform that I'll talk about in a second. So building an experience, a data-driven experience on blockchain, using blockchain data is difficult. It's very hard, and we see a lot of companies have been emerging in the space that need blockchain data to power their experiences. But it doesn't really make sense for all of these companies that are coming out in the space to build the same infrastructure over and over that basically do the same thing. And one of the reasons why it's difficult is you're forced to kind of build and operate your own blockchain nodes, which have a tendency to be very unreliable. You have to build your own ETL pipelines. You have to manage data lakes, data warehouses, query systems, like a bunch of infrastructure that don't really add value to your core business. And you have to really understand the details of the chains that you're working with. So you have to know how to decode logs, events, transactions, things like that. And that's just for one chain. In order to support multiple chains, you have to basically multiply that out for each chain that you want to support. You could offload running the nodes to an infrastructure provider like Alchemy or Infura, but trust us, we've tried that. It doesn't work when you're trying to index all of the data on the chain. So let's imagine, hypothetical example, you're an NFT marketplace and you want to provide AI-powered recommendations for your customers. So when a user comes to your platform, they connect their wallet, and you want to be able to get a list of all of the NFTs that they've traded and plug that in somewhere and get out a list of personalized recommendations that they would be interested. So how would we go about that? So first, you will need a way to actually get, like when they connect their wallet, you'll need a way to quickly get all of the NFT trades that user's done. And unless you've pre-indexed the transaction data, that's not possible, right? And so you have to have pre-indexed all the transactions. You have to know which transactions are actually NFT trades. And then once you have that, you can finally have the data that you can plug into your model, which is the next hurdle of how do you actually train this model? So the conventional wisdom for AI and ML processing is that the more data that you throw at the model when it's training, the better it can get. So if you want to provide the best, personalized recommendation that you can, you need to give a lot of data for it to train on. And so again, this goes back to the problem of unless you've indexed all of the data on the blockchain, it's going to take a while for you to get that data. We've actually, at Spice, we tried to do this with a small kind of toy project when we first were looking into this, and it just we spent most of our time just trying to get the data. And so our understanding of the difficulty in this problem is kind of what led us to build the Spice.xyz platform. And that's just for working with on-chain data. One trend that we're starting to see is a lot of data that was previously on-chain is moving off-chain and just being pointed to by the on-chain data. I actually had the chance to talk with Matt Ober, who's the co-founder of Pinata, earlier this week, and we were talking about how, it's just so expensive to store. I think it's to store 1 gigabyte of data on the Ethereum blockchain, it's like $200,000 or something crazy. It's just infeasible, and so and it's just going to keep increasing over time. And so we're starting to see this trend of things that were being put on chain is now just being put off chain. And kind of one good example of this is the difference between the ERC 721 NFT token standard and the ERC 1155 token standard. So here's the ERC 721 token standard. You can see here that even just small things like the name and symbol were previously stored in the state that's on-chain, and you could query it from on-chain. But on the ERC 1155 token spec, all you get is a URI that points to somewhere off-chain. And then once you have that thing that off-chain, you basically get a JSON blob that has that metadata. Oftentimes this is stored in IPFS, but sometimes it can be stored in S3 buckets or what have you. And so for really powering an experience that works with blockchain data, you need to have a solution that can deal with both the on-chain data and combine it with the off-chain data as well. And so that's kind of why we're really excited to work with the Bacalhau Howe team and the Compute Over Data Working Group, because we can leverage their experience of being able to provide compute over data stored in IPFS, and we're working to make Spice kind of the easiest way to build an application that leverages both on and off-chain data. And so now I'm going to deep dive a little bit into some of the real-world use cases that we're seeing at Spice of what our customers are doing and what they need. But first, to set a little bit of context, I'll explain a little bit about how we think about where the value in blockchain data comes from. And we've used the analogy before that blockchain data is kind of like crude oil in that it's not very useful by itself. You have to kind of process it or enrich it into these higher order data sets, which we call enriched data sets, which could be things like DEX trades, NFT trades, liquidity pools, et cetera. And then once you have those kind of higher order data sets, then you can apply data science and ML onto those data sets to get to the really interesting things that you can actually build applications on, such as recommendations like we talked about, or fraud detection or anomaly detection. And so the first example of one of our customers is Fimeo, and so they believe that Web3 needs to be a safer and more trusted place for users to engage, and they're working on building things like Web3 credit scores, smart detection, and wallet fraud detection. And they use on-chain data that's provided by Spice to power their ML detection scenarios. And it was funny, we had a call with them recently, and they were talking about how before Spice, they had this infrastructure diagram that was super complex and involved a bunch of indexing and storage systems. And then after Spice, it got massively simplified to just like Spice and then their ML processing pipeline. Another one of our customers is MetaStitch, and they're building a community growth platform for brands in Web3. And so the key idea here is that understanding communities allows brands to know which communities that their customers are engaging with and where opportunities might be to kind of expand out into related communities. And so you can see here on screen a page from their product that's actually powered by Spice data from our NFT owners data set, where they can identify similarities between different communities, which they do here by NFT collections based on the wallet ownership. And so last but not least is Yakoa. They provide NFT authenticity and fraud detection services. So imagine, big brands want to make sure that their IP is not being infringed upon, and marketplaces don't want to list content that is infringing. And so they provide services to help those companies do that. And they leverage Spice data to actually identify all of the NFTs that live on chain. I think there's something like 90 million or something NFTs on Ethereum. And so we index all of them and we make it available for query. And Yakoa actually takes that data from Spice, and then they go out to where the NFT data lives, whether it's in IPFS or in other Web2 storage solutions, and then they run it through their ML processing pipelines. And so I'll show a little demo. Hopefully it works. We'll be running a live demo of taking some data from Spice and running on a Bacalhau Howe. The demo scenario here is going to be showcasing how we would enhance our current offering in Spice to allow processing of off-chain data. Currently, we just have on-chain data. And the scenario is basically taking a list of NFTs that you care about in some way from getting that from Spice, then using Bacalhau to process those images that are stored in IPFS into a collage. This is very similar to the COA scenario, and so they actually helped us prepare this demo as well. But instead of creating collage, they go out and do further processing in their ML pipeline. So yeah, so much of the code for this demo was actually contributed by ACOA, and this, major thanks for them for helping us prepare this portion of the talk. All right, so this is Spice. I'm going to log in really quickly. Because we are a developer platform, we currently offer a login with GitHub. Once we go to GA, we'll have more options there. And currently, if you try to log in, it's going to be behind a wait list. Just let us go onto the Discord and let us know that you came from the talk, and we'll let you in. You can start playing around with it. So I'll go over here into my app. And so what you see here is just kind of a simple SQL interface where you can run some SQL commands and get some data out. This is actually not our main kind of experience that we want to provide to customers. We expect people to just use the API that we provide. We have an SDK here, which you can see here in just like 3 lines of Python code. You can have your data in Pandas or NumPy or wherever you're doing your processing. And this is enabled through our Apache Arrow APIs. And so for this demo, I'm going to take the Bored Ape Yacht Club NFT collection. So this is the address here that I just pulled by going to OpenSea. And I'll just run this query in just a few seconds. I'll be able to get all 10,000 of the Bored Ape NFTs, and I can find the current owners of all of those 10,000s in just a few seconds using Spice. And so let's say that I'm really interested in this one, 5306. And so I want to find all of the NFTs that the current owner of this NFT has in their collection and make a collage from that. So the way I would do that in Spice is I would say, okay, well, I'm only interested in token ID 5306. Run that query. And in just a couple seconds, I'll get back the owner information from that query. Taking a couple of seconds. Okay, let me retry that. Okay, anyway, so once we got that query, we would get back the owner information. Yeah, so we got this back. And so we can take the current owner of the NFT, and then I can basically, with the same data set, our NFT owners data set, I can query, okay, what are all the NFTs that this current owner possesses? And so I'll run that query in Spice. It'll take a few seconds, and then I'll get back. There should be around 17 that I found from earlier. And normally what we would do is once you use this interface to kind of explore the data that you're interested in, we have here a data set reference here of all the different data sets for the chains that we support. And then once you're kind of interested in, you find the query that you're interested in, you would put this into your application using our SDKs and that's how you would integrate Spice into your application. But for the purpose of this demo, I'm just going to download this through the CSV. And so we'll be able to show you that data here directly. And so while it's downloading, I'll come over to the code here and start explaining what we're going to do. So the way that this demo is going to work is, so I just showed using Spice to get the NFTs that are owned by a wallet. But I need to next call the token URI. And so in Ethereum, there is a token URI function on the smart contract. So like if I call that function with the token ID that I'm interested in, I will get back this IPFS link that I need to then pull off. And so if I actually show you what's in this IPFS, so I'll just resolve this. So this is the content ID of that link from the token URI. And if I actually show you what is in here, it's just a JSON file. So I mentioned before that data is moving off chain. So this is kind of one example where the image link is not actually stored on chain. It's a metadata file that points to the image link. So we actually need to do two things. We need to first run a job in Berkeley How that parses that metadata out from all of these different metadata JSON files. And then once we have the actual IPFS links that have the image data, we can run a second job that will go and create our collage for us. So here's the result file that I just downloaded from Spice. And so we can see here the token address here is on the left, first column, and then the token ID is the second one. And so what I'll do here to run the Berkeley How job is I have a little helpless script that will get the metadata URIs by calling the Ethereum smart contract. So, this is going and calling the Ethereum smart contract. We filter out the ones that are not IPFS right now, and we'll just work with the ones that are in IPFS. And then you see here that some of these are files within a folder that's stored in IPFS, so we actually need to go and resolve all of the content IDs of this, so I'll do that now. So I have another one here, and so this will resolve, I'll show you the code for this. So this is actually resolving the content IDs of these into the actual IPFS content ID, and then dumping what I need to pass into Berkeley How into these volume arguments. So I will copy this. And so these are the commands that we actually need to mount this data into Berkeley How so that the job can access it. And then I'll come into Docker run. And then I'll run this first job. This will actually parse out the metadata. And so while that's running, I'll kind of show what this is doing. So in this parse metadata script, all we're doing is just scanning all the files that are in this directory and then extracting out that image URI that I showed here. So we're extracting out this image URI for all of the images, and it's writing it to this file called image_uris.pickle. So I'll go ahead and get this job. Hopefully it completes relatively quickly. Yep. Cool, and so now I have this job completed, so I can take out these image URIs, and then I can move on to the next step. So now I've got all the links to IPFS for all the images that I'm going to create the collage out of. Now I'm actually going to run a Berkeley How job that will assemble these into a collage. I think this would be a lot easier if we had the pipelining thing, which I think is coming soon for Berkeley How. But I'll go ahead and run that now. Generate volume args, and we're going to use image uris.pickle. Cool, and then if we look at this, so we have, similar to what before, we have these commands that will actually allow us to attach this to the Berkeley How job. So I'll run another Berkeley How job here, and then pass in the command that actually will create the collage. It's cool, and so the way that this script is running is very similar to the first one. It's going to loop through all of the images that have been mounted into that directory. It will format them into kind of the same size, and then output this collage called collage.jpg. And if the demo gods are willing, oh, they ran. And so now we have here the collage of all of the NFTs from the data that we got in Spice. So cool. So I hear you saying, okay, like, so what? Like, it's a collage of NFTs. But I think what really becomes compelling about that is if you're needing to run this compute over millions and millions of NFTs, there's 90 million NFTs stored in Ethereum. Like, you can't really do this in a centralized way where it's very difficult to do it in a centralized way where you're pulling the data out of IPFS to run this job on it. And so that's where the Berkeley How, like being able to bring the compute to where the data is very interesting. And you should also think of the demo I showed as kind of an inside look at how we might enable this at Spice. One of our goals at Spice is to kind of integrate the Berkeley How experience directly into the product. And so where you might have something that looks more like this, where all of the stuff that I just showed you is kind of contained within Spice, and all you would need to do is just upload some NFT processing job that needs to combine both on-chain and off-chain data, and then we would handle the scheduling and running of it for you. So yeah, so building experiences on blockchain Web3 data is hard, but at Spice we're doing what we can to make it as easy as possible, and we're excited to do our part to contribute to the Compute Over Data initiative and make it as easy as possible for anyone to build great experiences on Web3 data. So yeah, thank you, and this is where you can find links to our projects and Discord and Twitter.
Inside. It's okay. Test 1, 2. Exit. Not working. Not working either. Okay. No. So I think I'll just improvise. No speaker notes. Okay, so I guess you can hear me, right? My name is Stratos. I'm co-founder of WeatherXM, where I lead the engineering team. And we're here today to talk about how compute on weather meets COD, compute on data, or cow meets code. Sorry, I couldn't help it. This is Dali's impression of this meeting. So at WeatherXM, we're building the world's largest and fastest growing weather network. We have sold more than 5,000 weather stations worldwide, and we only started less than a year ago. And we have more than 9,000 members on our Discord server. So you may think that weather is a solved problem, and you would be wrong, of course, because still we lack accurate weather data for historical weather data, current weather conditions, and forecasts. And let me give you just a small example of the size of this problem. So this is a 3-day ahead forecast for Lisbon last week. And we can see the bold blue line is what happened in reality for temperature in the top chart and precipitation at the bottom. And the other lines are the weather forecasts from 5 different models, 5 different mobile apps, let's say in the weather. So what we see here is that for the first hours of the forecast, they're pretty accurate, okay. But as the forecast goes on, then we can see up to 5 degrees Celsius difference in temperature compared to the reality. And for rain, for precipitation, it's even worse. There are models suggesting that there would be no rain, and others that it would rain up to 3 or 4 millimeters, which is moderate rain. But in fact, it only poured like 1.2 millimeters. So still, one might say this is a small problem for everyday people that just want to know if they should take their umbrella or not. But in fact, it's a huge problem for so many industries like agriculture, supply chain, energy, and so on. And this is why governments across the globe keep spending billions of dollars just to forecast the weather and monitor current weather conditions. And it's still one of the hardest problems for humankind. So we believe new approaches are necessary to solve this problem. Inspired by Filecoin and Helium, we embraced their economic models and took advantage of their existing infrastructure to build a better weather network. So we are utilizing Filecoin to store weather data and lately experimenting with computation. And we hope that this will help us solve our mass-scale data storage problems. And we're also utilizing Helium network for connectivity, network connectivity for one of our weather stations. And all these new technologies enable us to build this new weather economy around weather data with our WXM token in the center. So station owners earn WXM tokens for their weather data contribution to the network. And customers who require weather data and services can purchase them using WXM tokens. For this to work, we had to build our own brand new Web3 native weather stations. They have a number of improvements compared to the traditional weather stations, let's say. They are energy and communication autonomous. They're 10 times more affordable, and they provide cryptographic proof on the weather data. And our customers are already taking advantage of this new hardware to get improved weather forecasts on their mobile apps and our web apps. So we have already shipped 3,000 of these stations, and we're about to ship another 2,000 in the following weeks. And we're ramping up production to meet the high demand, and we estimate to have produced 11,000 by the end of 2022. Just to compare this number, NOAA, the US Met Office, operates currently about 14,000 weather stations across the US, and they've been around for like 50 years. So you can imagine that very soon we're going to produce tons of data. That's why we started experimenting with compute over data technologies. So compute over data in a Web3 distributed way, and Bacalhau project, to be more specific, promises scalable, cost-effective computation, offering also parallel workloads, and we can benefit from that with public, transparent, and verifiable computations. And this makes so much sense for us in so many ways. There are critical components of our network that can benefit, like the token reward system, which is backed by quality of data mechanism and proof of location. For these mechanisms, transparency and verifiability are key. And also for our weather forecasting engine, we can benefit from distributed data aggregations and distributed forecast model training and execution in a very cost-effective way. So it's demo time. Our team, with an extensive experience of more than 48 hours using Bacalhau. Let me just show this as well. So we prepared a very small demo, just to explore what's possible with Bacalhau. Forecast accuracy tracking is very important for us because it's the first step towards an improved weather forecast. Because how can you improve forecast if you don't measure the accuracy of existing forecasts before, right? So just for this example, we have two data sets of data for two locations. One is in Lisbon for October, and one is somewhere in the UK. And we have actual conditions, hourly data sets from two of our weather stations for these locations, and forecast time series from three different weather models. And we've also prepared a Docker container that's running just the basic RMSE calculations, comparing forecasts and actual conditions, and doing also some other correlation stuff. And the goal here for this demo is to find for these two locations which forecast provider or which forecast model is more accurate for temperature, humidity, and wind speed. So we're going to see this in practice, running first for one of the locations and then utilizing parallel workloads to run both locations at the same time. Okay, so let me cheat a bit and copy the command here. So we have already uploaded data on IPFS. I can actually try and show it to you. Right. So let's try Lisbon first. So we have the observation data from our stations, just basic hourly CSV file. And similarly, for the 3 forecasting models, you can see, again, hourly data. Okay, so basically here we're asking Bacalhau to run a Docker container that's already up there on GitHub. I'll give you a public link for it to download if you want. And run this Python file where it produces some calculations on the data, comparing forecasts and historical data. Yay. That was easy. Now we have the result. All right. I should stop this IPFS first. Let's get the job results. By the way, you need to fix that, right, on Bacalhau? It's a good one. Yeah, I have more suggestions for you guys. So let me find it. It's in the outputs folder. Okay, Lisbon. And let's just try temperature. Okay, so this was produced by the Docker container, and what we can see here, let me just zoom, is that again, the bold line, the black line is the actual conditions, and the rest are the forecasts. So we can see that, oh, and by the way, this is all day ahead forecasting. It's not like 3 days in the future. For every day, we got the hourly forecast for the day. So one would assume that, especially for temperature, I mean, how hard would it be to measure temperature? Apparently it is. And they're not doing a good job even with temperature. You see at some days, like here, they're off like 6 degrees Celsius, some of the models. And for days, like, I mean, for most of the days, even if the models are inaccurate, you can see that the temperature pretty much follows, you know, a classic line that you would expect, but a classic curve. But this is a nice example, this area here. So like near the 19th of the month, we had some rain coming. Let me just show you something else. Our meteorologist, Stavros, said I should show you this map. Thank you, Stavros, if you're watching us. So you can see this phenomena just to the west of Portugal, which affected apparently forecasting because the actual weather, the actual temperature didn't even follow the expected curve, but models could not model it correctly. So the situation is pretty similar with the others as well. I mean, we can also visualize this with RMC. So again, here you can see the relative mean square error per day for temperature. And ideally, this should be 0, right? To have the perfect forecast. But again, you see that that's not very good. So let's try running now in parallel. So using sharding now, we are running again for both of locations. And again, think about our needs are like we're going to have thousands of weather stations out there. We wouldn't want to run the computations on their data sequentially. Ideally, we would like to run batch jobs for huge amounts of data because this is just a sample data set. When we start adding GRIB files, the global forecasting files that are gigabytes of data every day, it's going to be hard. So we need parallel computations. No, okay, so let's get this job. So here you see that the computation run now in parallel, and we have the results of both locations, Lisbon and Mansfield. And let's check Mansfield, I guess. And again, you see something similar, but no. Let's try also the rain, or no, wind speed. So wind is even more difficult. Wind is one of the more chaotic phenomena. So again, you can see some models like the blue line is really, really off compared to what happened in reality. And we've seen this in many projects that we've done, which affect, let's say, the wind turbines. You need to know the wind speed there in order to know how much output they will produce. So it's a big pain for the energy industry not being able to predict the wind correctly. Okay, so I think we should close now. Thank you very much. And just a final note, because people have been asking us throughout Lab Week that half of the team is here. Where can we buy one of your stations? Right, I forgot to show it. Thanks, Manolis. So this is one of the stations. This one is not officially out yet. You can pre-order it. We'll be launching this like in a month or so, yeah? So this is the helium version. It's standalone. You can just put it out on your balcony, and it connects to the helium network. And we put up this form in this URL for people here in CoD Summit. And you can just skip the invitation queue by subscribing today. Thank you very much again.
Hey, question from over here. Thanks for that talk. I'm curious, on average, like how much data per day does one of these stations produce?
Okay, good question. I'm not sure of the exact amount right now, but we estimate in a more mature phase of the network to produce like 100 gigabytes per day just from the stations. But this is only a small part of our needs in data storage, because we are going to also store on Filecoin and IPFS large data sets produced by meteorological companies, because as engineers, we want to evaluate these forecasts, and also they are going to feed our engine to help us produce better forecasts. And these are, again, very large gigabyte, large files produced multiple times per day.
Hi. Thanks for that. That was good. Is there a scope for running any of these computations on the device, on the node, on the weather station itself?
Okay. We have Nikos here that might want to answer this, our hardware guy and CTO. Actually, no, right? They are very low-power devices. We're using ESP32, and it's for basic computations only. So essentially, we're using it for reading the data from the weather station and sending the data to IPFS directly and to our cloud platforms. It's not like Linux or Raspberry Pi and such things. Okay. Thanks. See you tomorrow here. Right there. Great.
Hi, everyone. I don't need a slide to talk a little bit about me and tell you who I am, so go ahead and get started with that. I'm Peter Wang. I am the CEO and the co-founder of a company called Anaconda. We've been oh, there it is, great. So I work in the data science and open source software and the Python world and all that stuff. So if you like Python, love data science, you probably have touched something that we use or know of what we do. If you don't like any of those things, then you probably either don't know who I am or don't like anything we do. But I come to sort of decentralized computing, de-webcamped kinds of things because for a long time I've had a personal interest in well, that whole technology space, this whole technology space. And so here I'm going to talk a little bit about Python bits, but not too much. This is really talking about WebAssembly. And what's interesting is that I think there's an intersection between sort of my day job in the Python data science AI space and my long time personal interest in decentralized computing and peer-to-peer technologies. And I think they intersect in a very interesting way with WebAssembly. So I'm going to talk to you a little bit about that today. And the title of my talk is Our Portal to Portable Computing, which is a little hard to say, especially if you have a little bit of wine. But before we sort of investigate the question of portable computing, we can start by asking the question, what makes software not portable? Well, and what makes it not portable is that when we write software, we're sitting on top of a stack of other things, right, in the most idealized way. So this is true now, of course, from a Python perspective, we have an explicit language runtime, it's an interpreter, but people working in compiled languages recognize that, of course, there are core language bits from the compiler that also get loaded in as a runtime. So when you see runtime there, it doesn't just mean interpreter, and it's certainly not just an interpreted language ecosystem's problem. This is really true for everyone. And this, hopefully this is not too controversial of a stack. And what I would say is that what makes software not portable is that every single one of these blocks is a leaky abstraction. And by leaky, it means that if you're programming at that level, you're going to stumble over holes in it, but also means that you can poke through that hole and touch something underneath you're not supposed to touch, and make software that then becomes very unportable. And then between each layer, there's something else that's a little subtle, but if you think about it, it's true. Between every layer of abstraction, there's usually this install or compile or configure step to kind of mate these things together. So it's not like a stack of Legos that just have like, sub-millimeter precision that just snap together. You always gotta jam them together a little bit with a YAML file or an INI file or a Docker file or something, right? Something kind of like smacks these together. Make file, configure, autoconf thing. And this configure step usually it usually includes a lot of opinionated sort of configurations about the layers below. So it's not, again, the bottom layers that show up, they don't just give you perfectly spaced studs that are in the right spaces all the time. You can choose to have the studs show up in a different place or have 10,000 new studs over here in a different directory. And so that set of configuration options is, again, one of those things that happens. And so by the time that we take these Lego pieces together, what we've actually done is glued them all together into the like horrible melted blob of plastic, and that's why it's not portable. And so the question, I think, if you start from go back to the very, very beginning, you say, what's the point of all of this? Why do we do all this stuff? And I would say the reason we have software at all is because we want people to harness the power of computers. We want to let them express their ideas at a level that they're interested in without being encumbered by any unnecessary complexity. Like in an ideal world, if you could wave a magic wand, this is what you would just give to everyone. So a school child wanting to make some art thing can do it. A teenager wanting to make their own custom game can do it. Scientific software developer who wants to harness a supercomputer and just write exactly like the 10 lines of math that they want to write, they can do it, right? In an ideal world, that's the software ecosystems that we'd have. That is not the software ecosystem we have, but that's ultimately the point of it. Like, why do we code? It's because of this. This is why we don't all just write low-level machine code for precisely the chip that happens to be in our laptop this year. And so our approach to this, our fundamental approach to solving this problem, has been the same approach since about the 60s, which is that we create these abstract concepts above the hardware. Right? The hardware only has binary. The hardware doesn't even have floats or ints. It kind of does, but you can kind of like, people jury-rig that stuff. It's just got bits. And so anything we put above those bits, those are these attempts to build this ladder of abstraction, and it works reasonably well. And it's an interesting footnote, actually. I put that here parenthetically. There's an actual time when the computer science, field, they didn't know if compilers were possible, right? So there was this language called Algol that was developed, and these people were trying to figure out, can we make an Algol compiler? And some people thought no, others were like, well, it'll take a long time. Then they hired the summer intern in, and he built it in the summer. And the intern's name was Don Knuth. So they were like, wow, this is a really bright kid. But now we know we can make compilers, right? So this is not something, and this is in the 60s. So we've sort of pulled the same hat trick over and over and over again, making compilers. And so since then, the 70s, we just live in this long shadow of the 70s. So much of what we use is still dated from that era. And of course, I have the 80s in here as well, and the 90s. But just to give you a sense of, we still use Ethernet. We still use Unix. Many of us have to support users on DOS. Even though we call it Windows now, there's a whole lot of DOS in there. So, and every single one of you gets paid out somehow through VisiCalc, although we call it Excel now, right? So there's a lot of the groundwork of how we think about computing in the act of software construction that's been anchored in the 70s. I would say that we've certainly moved beyond. We've moved into a post-PC era now. I think that's not really a controversial statement. But all of these blurred lines that happen is because we've had this continuous economic revolution. Let me say that again. Continuous economic revolution from the PC, and the PCs kept improving, and then consumer broadband came in. And that kind of kept getting better, speeds got faster, and then Web 2.0 came in with interactive client-server computing. And while that was going, part of that mutated into social platforms. And while that was going, we got portable supercomputers in our pockets, right? And then it just keeps going. Cloud, AI, all these things keep happening. And the really interesting thing about all this stuff is that at no point do we stop and say, oh, well, you know what, this is really, we have rickety ladders stacked on rickety ladders stacked on rickety ladders. We should stop and maybe build a really good concrete stairwell and then build from there, maybe. But no, we do not. We just keep slapping stuff on top. And because it hasn't led to the collapse of civilization just yet, we believe this is an okay thing to continue doing. But the important thing to say is that this is all frozen accident, right? This is all frozen accident. And there's this great quote I love, which is that science makes progress by, because scientists stand on each other's shoulders, computer scientists progress by standing on each other's toes. And this is okay, because they get paid handsomely for it, and it's still better than not having working software. But all of us, I think, in this room as technologists, we've played with this stuff enough, we've looked at this stuff enough to understand that there is no spoon. Operating systems are a myth. Programming languages are a myth. Floating point is a myth, right? The most cutting-edge AI today, they're using what? 16 and 8-bit integer math. They use fixed point, not integer, sorry, fixed point math to make things go fast inside those CUDA cores. So every single thing you thought you knew about what any of this stuff was or why we needed it, it's basically, you can decide today to stop believing in all of it. All right, I give you that freedom. I sometimes choose to exercise that freedom. And the reason it's important to exercise this freedom is because we're now in a really interesting time where we can rethink this. If we start backing into that question of why do we do computing? Why do we write software instead of soldering things together to make cool blinking lights? And the reason is because there's all these different things people want to do. Some people want to make games. Some people want to make interactive art. Some people want to do, like, spreadsheets, all sorts of stuff. So if we start from there and then we figure out, going backwards, what is the minimum set of abstractions we need between the hardware and the application in order to, actually have this work, then it's a very different question, right? It's then sort of saying, let's say we find ourselves in this part of space, let's burn down all the ladders, control Z, remove all the ladders. How much, what do we actually need to do to go from ground plane to where we're at for this application? And this picture on the side is something that's from a talk I gave in 2013 when I talk about that when I was giving a talk at a PyData conference in New York. And I had this thesis that we could build dynamic compilers and just-in-time compilation that would take Python and take it to at different levels of abstraction down. And we succeeded in doing that. And we have a project called Numba, which is a dynamic just-in-time compiler. It can target GPUs, it can target CPUs, but it actually takes your Python code that a data science novice 2 weeks out of a boot camp could write, and it takes that code and it can make it into machine code faster than if you hand-tuned some C++, right? And the reason we can do that is because there's all sorts of things that the computer knows how to do once it actually has the actual code and the actual values coming through and the actual types. It can do all sorts of great stuff for us. And so the reason for thinking about it from this perspective is because my assertion is that this technology, WebAssembly, that's just recently become a standard in the last couple of years, WebAssembly completely changes the game. Literally, it changes the game. It flips the script on 40 years of software infrastructure. 40 years of frozen accent, 40 years of PC, Wintel duopoly. WebAssembly changed, wait, this is being recorded, right? Okay, that's fine. I got friends at Microsoft and Intel, they know what I mean. But the idea here is that WebAssembly, what it actually is, the way it came about was that people had a pile of JavaScript on the web for all sorts of maybe useful things and sometimes maybe kind of creepy, crappy things. But whatever, there's a pile of JavaScript on the web, and people kept realizing this JavaScript, we have to optimize it, we have to optimize it, we have to optimize it, and the JavaScript runtimes in the browsers got better and better and better at optimizing, and the way they got better was because they would take the JavaScript and build shadow classes, they would do lowering, they would do all sorts of stuff, amazing, theoretical CS compiler stuff they would do. And then people started realizing, wait, if I write my JavaScript in a particular way, I can then hint to the optimizing just-in-time compiler that this is really, really, really an int. Really just treat this like an int. And if I do this thing over here, I'm telling it it's this other kind of value. And if I do the other things, it's telling the low-level thing, the low-level JavaScript interpreter, I'm signaling something else to it. And so eventually there was this little project called asm.js that came about, which was all sorts of goofy syntactic hacks to directly convey to the underlying runtime what you mean in JavaScript. So it's really very interesting and very odd project. But that then evolved into this thing called WebAssembly, which is that now the web interpreter, or the JavaScript interpreter that powers all the browsers, those JavaScript interpreters, they have a front end which actually understands JavaScript, the language, and it converts that into low-level instructions for a virtual CPU. And that virtual CPU is the WebAssembly runtime. But that virtual CPU instruction set is reified. You can target it with a tool chain. You can just, it is a 32-bit CPU, it's a 64-bit CPU with 32-bit memory space. And what's really interesting is this compiler tool chain built on LVM called mscripted has come around that can compile most C or C++ to target this WebAssembly. So that's super interesting, right? You don't have to write JavaScript anymore to target the web. And the other thing about this is, even though it sounds like a super like cutting edge, goofy thing, it actually runs everywhere. It runs on mobile Safari, it runs on Android, it runs on every major desktop browser, it runs on like the Opera Mobile. 4 billion installed devices worldwide have this completely portable, highly optimized, highly secure runtime available. Because keep in mind, the security of this thing, it is what powers Gmail, Amazon.com, everything that you access through the web runs inside the same enclave. So this is really the CPU at the heart of every single browser tab you have. So this is what's really cool. You can use tools like Emscripten to provide a pseudo-POSIX environment and take any of your legacy code, well, not any of it, but a lot of it, and compile that to target this virtual CPU in the browser. This means you can run C code in the browser. So there's projects like DOSBox, which do our DOS emulation. They compile the whole thing to WebAssembly. It loads in a web page. You load in, then you hook up a virtual file system to it, and now you're running Doom and SimCity and everything. In all the games that I grew up with that I loved, I can run them in the browser. Not because people recoded them in JavaScript, but because people compiled them. Actually, people didn't compile them. People compiled DOS, a DOS emulator, to target this virtual CPU, and then they just load in those game binaries and exes unmodified. It's kind of a trip. So the other thing is, for servers, this is the game changer. And if you go to things like KubeCon and you look at the amount of interest in WebAssembly, it's because this is actually the thing that's like much better than Docker for a lot of purposes. Is much better because this is an isolation. This is isolation truly at a below the OS level. But anyway, it spins up super fast as well because browser tabs have to be fast. So the key thing here, that's the really, really big takeaway, is that with this technology, every single person that can run a web browser tab, which is a lot of people on the planet, they actually have a uniform runtime that's congruent with every other person that has a browser tab. Until this point, we did not have that. Because you would have a Windows box, and I've got a Linux box, and they've got a Mac, and someone else on a Chromebook, and someone else on an old Android tablet, and like none of these, you can't ship a single payload to all of these people and have it work until now. So earlier in the year, I created a thing called PyScript, and PyScript takes advantage of this. It takes advantage of the fact that you can compile the standard C Python runtime interpreter and a lot of the data modules that power PyData and SciPy and things like this. You can compile all of that to target this WebAssembly CPU, and now you can run these in the browser. And so there's a project called Pyodide that did this for a couple of years. Really, really cool. Awesome project. And then we sort of wrapped it with some framework so that you can interleave Python in HTML. I think someone joked once at one point, they're like, oh, I guess you looked at PHP and thought it was awesome, so you made Python like PHP. I'm like, you know what? Whatever works, right? But what's really cool about this is that you just have HTML. So the universal EXE now is HTML. And this is what this code I don't know if you guys can read from back there, but you just put a bracket py-script tag. It's a web component. And now you can just write Python code. And so the WeatherXM demo, right? That you wouldn't need a container, right? I think that was Python because I saw a matplotlib graph. But you should be able to run that whole thing with just an HTML file with PyScript. And so it's a layer and a stack of things. And what's really interesting is that the Python can call the JavaScript, and the JavaScript can call the Python, and the JavaScript can touch and frob the heap of the Python process because it's just one big old JavaScript array. Your entire memory in WebAssembly is a JavaScript array. It's really amazing. So now every single person, not only does every single person in the world with a web browser tab have a uniform computing environment, they can truly be peers to each other because you can use things like WebRTC and you have access to WebSockets, things like this. So you don't have to get them to install Docker. You don't have to like port your code to run on whatever Alpine Linux is in the Docker. You literally just can run the stuff you know how to run. And there's Rust that's compiled to WebAssembly. There's all sorts of stuff that compiles to WebAssembly, not just Python. Although the Python side of the world is what I'm sort of really trying to push forward on WebAssembly. And it's not just cheesy little hello world things. This is full on. So for instance, these are some of the demos we have at pyscript.net. The one in the very front, that is the New York taxi cab data set, a very large data set, loaded into an interactive pandas and DeckGL 3D analytical environment. In the back, that's Python, PyScript talking to WebGL, doing, again, interactive 3D sort of stuff. On the left, you can't really see, it's a little obscured, but it's actually an interactive machine learning example with scikit-learn. Again, all running client-side. All of these are single HTML files that I can give to somebody on a USB stick, somebody anywhere in the world, they can load it up and it runs. And this is really the amazing thing. I will quickly go through why Python matters and why I'm interested in the Python side of this, and I'll loop this back around to why, maybe you guys already see where I'm going with this on the WebAssembly thing, but the reason why I'm so interested in Python, this ties back to that thing about why do we do software at all. It's to empower people to do whatever it is they want to do with computers. If you guys ever go back and look at old, like 1970s magazine advertisements or newspaper advertisements for computers, the idea was that you would write the code to do the thing you wanted to do. So you would buy an Apple II or something, set it up in the kitchen, and you'd punch in like a recipe software for like in BASIC, and you'd have your recipe cookbook thing on your computer. And this is like a reasonable thing that people expected others would do. And so this idea that computers are tools of creation, not merely swipe left, swipe right, get mad, get thirsty. This idea that computers are tools for creation and that they're bicycles for the mind and all this stuff, that actually is part of what motivates our mission here, at Anaconda, which is to empower lots and lots of people to do data analysis, lots and lots of people to be data literate. So Python as a language has proven to be easy to learn, designed for readability, people can sort of casually take it up and then program by example. But something for this crowd to be aware of is that Python is not like a lot of the other scripting languages, and that one of the really cool things about the Python runtime, the interpreter CPython, is that it has a very consistent and simple low-level ABI at the C level, at the C code level. So you can build extensions kind of beneath the waterline and tag in, like couple into this like iceberg set of features underneath the Python interpreter and extend it to do deeply performant, really large-scale computation for math. And so that's why Python has taken over for data, for numerics and things like that. This is the thing. And the reason I bring this up to whoever I can is because I realized after reading Hacker News for many years now that no one really understands this. And so I have to keep telling everyone this. It's not the same as Ruby. Python is not just a less efficient Perl or whatever. Python is very unique in that its runtime is extremely extensible, and it showed up at the right time that a bunch of scientific computing engineering nerds took it and extended it with all these semantics for doing large-scale vector and tensor math. And so it is a Honda Civic with these mounting bolts for the warp drive, and that's why people use it for AI and for all sorts of large-scale computation today. But where that leads us to, since I brought up AI, where the world is going is back to the future in the sense of we originally created computers to do prediction. That's what they were about. Whether it was predicting where the gun of a battleship should point, or whether it's predicting the entire economy of was it Chile or Peru, whatever the Cybersyn thing was. The point is we use computers to do prediction because that was like the single most important thing. Tallying things, counting things, basic statistics, that was not the most important thing at this time. And then, adding like all sorts of fun computer, consumer entertainment kinds of things, that was completely ancillary. We're back now to a time where everyone cares about prediction again. Prediction in the large for entire economies, prediction in the small for robots trying to navigate a factory floor. So the entire world we're steaming into, just like running into full speed, is a world of connected sensors, actuators, computing-rich environments everywhere at the edge, everything running predictive loops. And so with all of that being out there, everything shedding data exhaust, everything making predictions, we really have to empower the world's population with data literacy. It's not just good enough for a few people to know how to build this stuff and everyone else just uses it and just like chills. It's really, really important that we see data literacy, not software development, but data literacy as a fundamental human skill. Just like being able to type on a computer, just like being able to read a book, or being able to be basically mathematically literate. If we don't solve this problem, if we as a species do not intentionally tackle this problem to solve it, we will end up in a horrifically terrible state of affairs. It will not end well for any of us. We will do well, our grandchildren will get guillotined, right? So that's what we have to avoid. And so to give you a really concrete picture of this, there's many measures and analyses of how many programmers there are in the world. Some people say 20, some say 40 million. I like to take the number about 25 million, I think, is about reasonable. Like coders, not people who can write a little bit of code, like real coders, 25 million. Well, there's 8 billion people in the world. So if you do the math, it's less than 0.5%. And out of those 25 million coders in the world, there's a lot of them that don't know math or stats, or they can't do statistics, they can't do basic data science. So we're talking about like 0.1%, 0.15% of the population able to understand all of these things that affect everyone's lives. And that is not a good state of affairs, full stop. So coming back around to WebAssembly, we have this universal virtual machine that everyone has. You don't have to, you can get started by going to a web page, and you've got it. You've got all the runtime you need to play with stuff, to hack with something, to take it and remix it. And the reason I think WebAssembly succeeds as a universal VM is because it didn't start the way that all the other universal VM projects started, like the JVM or the Microsoft CLR, DLR stuff with .NET. All those started with trying to build like the grand abstraction that will run all the languages. But every time they try to do that, there are many other things that are more vertically integrated and specialized tool stacks that would outcompete them. But WebAssembly instead comes around and it sort of fell in our laps because it started with this huge install footprint of basically everyone who uses the web, and then it builds in and it sort of distilled out what is the minimum reproducible portable runtime that's good enough to run everyone's JavaScript fast enough, right? So the dream, and the reason I'm here at Compute Over Data, is because everyone has these machines that can run this portable runtime. Everyone can be a peer. And we have a language and a language environment, language tooling now with PyScript that makes it so everyone has a zero install ability to start writing code that runs on data locally, or that can easily move with a button click into the cloud. So no, you don't need Docker. You don't need to install, I mean, ironically, I'm the Anaconda guy, but you don't even have to install Anaconda. You literally just write bracket PyScript, and you're rocking and rolling. So this is ultimately the dream, is that taking advantage of WebAssembly, taking advantage of this super portable new concept of this, this new runtime, we can create really, we can kind of accelerate past the 40 years of ossified, frozen accident, and really try to intentionally build out better architectures to compute. Local, edge, offline first kind of capabilities, and then putting in the hands of, again, the important thing here, putting in the hands of everyone. So it's not just a few people who know how to have the access permissions to touch a big data center and things like that. So with that, thank you very much, and I think we might have some time for some questions.
Excuse me, I just had a sandwich. So I'm loving what you're saying about the getting people involved in the system so they get to learn it. I wonder what your thoughts are on getting them, whether it's more valuable to have them be literate or have them be actual builders in the system. So in science, we have the concept of science literacy, but with distributed computing, everyone can become a participant in the system and actually contribute to building these things that affect your life everywhere.
Yeah, I think the best stakeholding is participatory stakeholding,
Yes.
right? So, so definitely, in fact, I would say that if literacy is simply interpreted in a very surface kind of way in terms of like you can read the thing and maybe grok it or convince yourself you can grok it, then you don't know when your read is too shallow, right? Until you go and try to build it and use it and put it in practice, then it could just be that you end up really in a very shallow part of the water and you don't really have deep understanding at all. And for some things, maybe that's okay, but I think for a great deal of things, it really matters a lot that people do get their hands dirty on some of this.
Yeah, at least for more than 0.5%.
More than 0.5%, right, right. There will be a gradient, for sure, of expertise.
Hi, thanks for the talk. It was really fascinating. One, I guess, kind of low-level question I have is you'd mentioned one of the beauties of Python being able to plug into C++, Fortran, libraries, whatever. I'm just curious to know if in WASM, if that's still the case or if it's only pure Python at this point.
No, that's the point, is that it's the whole thing, man. It is the whole thing. So we have Matplotlib, we have SciPy, scikit-learn. There are some libraries that have built sort of native JavaScript things. So there's like TensorFlow.js and some of these things, and we can of course talk to those, right? Kind of at the high level JS FFI. But for the low level stuff, absolutely, yeah. In fact, the thing that we're struggling with right now is that there's not really a good modern Fortran compiler that can target WebAssembly. So in order to get some of SciPy working, Pyodide had to do a Fortran to C translation and then compile the C with the mscript and toolchain. But absolutely, that's the real beauty of this stuff, is that you can get that C code in there.
Thanks.
So two quick questions. One, if you ask the average very productive data scientist today how much they know about Python innards, right, the GIL or whatever the hell, probably pretty low, and they're very, very productive. What percent of people ever even know that WASM exists? That's kind of like even at the limit where we are very happy and everyone's using it. And two, you have a bunch of really smart people in this room. If you could wave a magic wand and in 1 month, 6 months, a year, had something that existed in the world, anything, tool chains, bindings, I don't know, you name it, what would you like to see?
Wow, okay, so the first question, if I understand it correctly, is most people don't understand the innards. How many of them need to know that this is WebAssembly? Is that the question?
I mean, to some degree, how many need to know that WebAssembly even exists, or the innards of
None of them, because none of them know what x86 mean, and they use it all the time, right? It would be interesting to do a little Twitter poll and ask people, like, does the new Apple M2 chip, which instruction set which ISA does it use? I won't even say instruction set, right? Select the ISA of the new Apple M2 chip, right? And so, no, people don't need to know that's WebAssembly. All they will know is that it is awesome, because they just go to a web page, and every data set they get has a corresponding HTML file. They double-click the HTML file, and now instead of spending hours wrangling with the CSV, reading some text file that describes the columns and trying to figure out what pandas command they need to use to like munge something, they double-click the HTML file, and up comes a rich analytical environment that has all of the views baked in, that has all of the interactive transformations they want, right? So DuckDB, right? Take your SQL database, move it anywhere, and query over data, right? Thematically very related to this conference. That's right there. And so this idea of get the user what they need at the point of use and pull this in dynamically. So that's really the theme here. And so no, all they know is just all of a sudden a lot of pain went away. There's a ton of people, of course. Everyone here is, I would assume, familiar with Docker and quite comfortable with it, or maybe not everyone, but a lot of people are. But if you look at the data scientists, it's something they struggle with, because it's not just Docker, it's all the other stuff, right? You all know what I mean. And so, and when something fails, figure out what went wrong, like that's all very complicated for people, and all of that goes away, because you're literally just going to email HTML files back and forth, and you'll be fine. So that's the question number one. Question number two, waving a magic wand, what would I wish could happen? I would, for this room, for this crowd, I think what would be really amazing is if people started thinking about, well, I'll just go out on a ledge. I'll say this, right? I've been a big supporter of decentralized computing for a very long time, but I've not been a big supporter of like crypto hype, all right? And I think I've found many people in the decentralized web community who are of a similar flavor, that we see what blockchains could be good for, we see what they're totally not good for, and we see what crypto hype is, and yet there's this thing here that we need to build really, diligently build good, credible technology. There's something very, very good there to be built. And so what I'm trying to, the reason I'm here, right, and tomorrow as well, I'd love to have conversations with folks, really think about, okay, no kidding, I think this stuff is ready now, where we can put computing alongside the data. We can put this in people's hands, we put this in people's weather stations, which looks awesome, right? I'm gonna have to get one of those things, because Austin gets lots of interesting weather. But this is the thing that, can we build some really, really cool use cases to get people into citizen data, citizen science, into really putting this stuff back in their own hands. I have a 12-year-old son, well, an 8-year-old daughter, but my son is at the point where he's programming and playing around with this stuff, and watching him try to do things and seeing the place that he gets stuck is really, really interesting, because he comes at it from the perspective of, I remember when I was 12, first learning programming, a lot of things were, hard, I had to learn them, but the encumbrances that he has to go through today are just stupid, right? There's no reason for them. And so that's what I'm really hoping in 6 months' time, to make it very concrete, I would love for us to have some use cases that people are saying, oh, I got this thing, I stood this thing up, and it's effortless, and I don't have to learn all of cloud to do something very simple that I can share with a colleague.
Thank you. On this mission with you. So once we've got our tabs and the peers and the little example you just gave, how do we coordinate each other? How do we find the other peers? Have you done any thinking or a vision how that might evolve?
A little bit. Well, a little bit. I think if we produce the right kind of infrastructure, then a number of different kind of registries could emerge. Okay, so here it is. So the idea here is, I would love for us to emerge some concept, produce some concept that is not just pure data and not just code in a GitHub repo, but it's actually some combination of the two. So it's like almost like a live data set endpoint. And then anyone else wanting to compute on that has code and data lineage and provenance. And so you would put the registries of these things then, this is actually then the Merkle DAG or the blockchain or whatever you want to call it, right? And we're so close, we're almost there. You know, there's no reason we can't just build something like that. And so that's why I'm trying to push people here kind of in that direction a little bit. But I think the registry is the data index, is the global data catalog, and it should just be a URI, right? And the key thing is compute over data. It's compute and data. It's fusing these together, so you never lose track of what data set yielded some result. And when you look at a derived data, you never lose track of what code ran to produce this from its sources, right? And today, that's almost impossible. And I did consulting at a big bank 15 years ago, and they were building an internal system to do this kind of data provenance, data tracking. It was a huge, amazing system. If you guys Google for this bank Python thing, there's a blog post about this written up that was, I don't know, Hacker News years ago. It was an amazing system where the data was live, and there was full provenance of every data change. Like, the data catalog was the database, was the distributed key value store, was the CVS code repo. Like, it was all one giant thing. So I would love for us to build a global, externally decentralized version of that with these components that I'm talking about here. And that, oh, no, one more.
Thanks. So you said at the start that WASM is almost like an opportunity to rethink the stack, which is really great, and I agree that it's all gone a bit wrong. When I see people doing stuff with WASM, particularly on the server side, what they seem to be doing is starting with this vanilla substrate and then slapping POSIX on it.
Right.
And POSIX has got lots of assumptions about computers maybe being mainframes and having file systems and all that sort of stuff.
Yep.
And I'm worried that we're missing a trick by just slapping POSIX on top, and actually we could come up with something better. Do you think I should be worried, or do you think that's fine?
If you have a vision for something better, you should always be worried that crappy stuff will come along and take all the oxygen out of the room, right? So in general, yes. But in this particular case, I will be pushing very hard from the data side, and many data practitioners as well will be pushing very hard from the data side to keep it at that level and not just do the WASM is just like a different kernel for your same old crap of like overburden of like POSIX stuff. And so to give you a concrete example of this, when we look at what data scientists want to do today, their data is in all sorts of different places. There will be cloud buckets. There will be CSV files locally. There will be maybe an API endpoint they want to read out of an Airtable or a Google Sheet somewhere, right? There's going to be a big table or some like database they have to query. Their data sources are in all these different places. What they don't want to do, the last thing they want to do, is to ETL all this data out of there into some giant local hard drive somewhere and then run a bunch of stuff on it. What they would really love to do is express their ideas across these different data sets in a nice way. And so at Anaconda, one of the open source projects we created, there's sort of two that go hand in hand. One is called Intake and the other is called FS Spec. FS Spec is now baked into Pandas itself. as the way to reference data sources, whether it's S3 here, whether it's something else over there. So the idea is to give data scientists an expression layer where they can express the what they want to do, not the how. And as long as you keep the users at the what level, then we have the opportunity to go and synthesize the appropriate how, given the computing context, given the overall scope of the problem. And that includes scheduling certain parts of the compute graph, in data local ways, all these kinds of things. And so that I would say would be a countering movement towards that. Now, at the same time, both of these can happen. All of the server side WebAssembly folks and WebAssembly, the edge and CDN kind of stuff, those guys are going to keep doing what they have to do because they have a lot of workloads that will come in expecting POSIX. So that's going to be what it is. But yes, you're right. If that becomes if that's all it ever is, then we've lost a moment. We lost an opportunity.
Hi. Yeah, awesome talk, and thank you for coming. And thank you also for PyScript, because we built support into Bacalhau for running Python with Pyodide, and I'm grateful that PyScript has got a lot of library authors to make their stuff work with Pyodide. So that's awesome. Thank you. I have I guess it's kind of like a low-level question. Pyodide targets Emscripten, as I understand it, which meant that for our Pyodide support in Bacalhau, we had to run a Node.js container. Do you see Pyodide supporting WASI in the future, or?
That is a topic. Yeah, WASI is a topic of active conversation. We are actively now. We've been supporting the Pyodide project, like funding some of the work, and then moving forward, we'll continue doing that. And that is one of those things that we're trying to help. So PyScript, from a certain perspective, it added very little on top of Pyodide. But from a certain other perspective, it added just enough to open up many people's eyes to the possibility, right? And get a lot of interest. And sometimes that's a good thing, right? That's actually a very critical thing. And where we're going now is there are multiple runtimes. So there's a blog post that'll be coming out in about 4 days. So I'll preview for all of you some announcement we'll be making. But one of the things we've added in PyScript is the ability to support different kinds of runtimes. One of the runtimes is Pyodide. Another runtime is the official CPython WebAssembly build, right? Another runtime is Emscripten Forge, which is like Conda Forge, but with Emscripten and with all these packages. So it's not the way that Pyodide has a monolithic sort of distribution, and Emscripten Forge is more of a a piecemeal one. And then we're also adding MicroPython, which is about, I think, 1/100th the size of Pyodide. So now you have no reason to write JavaScript again if you can write Python.
Nice.
So it will be, these are some game-changing things we'll be announcing in a week. But all of these then, to actually answer your question, is that they will force us to think about, okay, what does the file system API look like? What does the worker and web worker dispatch look like? What is a socket level API that we want to provide? All these runtimes, right? So that's going to motivate a lot of that kind of discussion.
Awesome, thank you.
And we're at happy hour time, so if yeah, we're good. Okay, great. Thanks, everyone.